Hello everyone and God bless you. Welcome to function analysis. Let's start with elementary function types. Elementary functions form the foundation of calculus and mathematical modeling. Before studying limits, derivatives, integrals, it is essential to understand the behavior of the most common functions or classes of functions. In this module, we examine constant, linear, quadratic, polynomial equations, rational, radical, absolute value, and piecewise functions. For each type, we study its algebraic form, graph, domain of definition, range, and important properties. Constant functions. A constant function assigns the same output value for every input. So f of x is equal to c for whatever value of x where c is a constant. Example, fx equal to 5. So for each and every value of x, f of x would be constant, equal to 5, like a DC current, by the way. So that would be the graph. For whatever x value, you would have the height of the function, or the amplitude would be 5, which is the value of y. So it is a constant value. It's not varying. It's not changing. Properties, domain, all real numbers. Range is c. This is the range of the function, meaning this is the ceiling, the floor, everything. So the function, it's not changing from or between 2 points in the height. No, it is stable, like a leveled flight of an airplane. Graph, horizontal line, and slope is 0. What is slope? Slope is that of the tangent against the curve, meaning the angle formed by the tangent that is applied to the curve and the x-axis. Here, it is a stable line parallel to x-axis, so the slope is 0, meaning that the angle between this function, which is y equal 5, and the x-axis is 0. So it's not climbing or descending. It's neither rising nor plunging, hence the slope is 0. As an example, f of x is equal to minus 3. The graph is a horizontal line passing through y equal minus 3, which would be like this. This is x. This is y minus 1, minus 2, and minus 3. And this is how you draw the function. Exercise 1. Determine the domain and range of f of x is equal to 7. First, the domain is from minus infinity to plus infinity, meaning that for whatever value of x, there exists a value of f of x, which is y. So y is a line equal to 7. It's a height or altitude equal to 7 in this case, spreading from minus infinity all the way to plus infinity, which is the domain. The domain of definition is minus infinity to plus infinity. And the range is one value, a singleton, which is plus 7, a positive height or altitude plus 7. Can you imagine it as an airplane at an altitude of 7,000 feet, and it can go everywhere. It doesn't have a limitation when it comes to the domain. So it goes from minus infinity to plus infinity. It's a line forever going and starting from also an eternity back. Evaluate f of 10 for f of x is equal to minus 4. Now, given that the function is constant, f of 10 would also be equal to minus 4, because for whatever value of x, and the domain of definition here is also from minus infinity to plus infinity. So also for x equal 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The function would also have minus 4 as a value. So also f of 10 is equal to minus 4. And from minus infinity to plus infinity, the function is constant. It has the same value, which means the same height, also with a slope equals 0, meaning that notice that the angle formed between the function, between the y and the x-axis is always 0. So the slope is 0. Linear functions. A linear function has the form f of x is equal to mx plus b, where m is the slope, meaning this is tan alpha, by the way. This is what the slope is about. So m is, let's say this is the function and this is the tangent. Okay, so the slope is rise over thread, meaning that how much it is being elevated, which is y2 minus y1, correct, divided by the horizontal step, which is x2 minus x1. So m equal delta y over delta x, which is also what? Tan theta, the tangent of the angle formed by the tangent, to the curve, and also the horizontal line, the horizontal axis, because tan theta is equal to y2 minus y1, which is the rise, okay, which is the height, divided by delta x, or which is the opposed, like the opposing segment divided by the adjacent segment. This is what tan theta is. And this is m, or in other words, the slope. So the slope measures the rate of change. As for b, it is called the y-intercept, meaning that when you have a function mx plus b, it would have an intercept with the y-axis equal to b. This is the point at which the function or the curve clips the y-axis. Okay? Actually, yeah, this is the height of the function in respect of the y-axis in respect of the x-axis, or the elevation of the curve from the x-axis. As an example, f of x is equal to x plus 3. So the domain, all real numbers, right? For whatever value of x, you have a value of y, of f of x. So it is defined throughout minus infinity to plus infinity. This is the domain. Range, all real numbers, meaning that for negative x values, you would have a negative f of x. For positive values of x, you would have a positive value of f of x. So the function also has a range from minus infinity to plus infinity. And as for the graph, it is a straight line. Now, this is how we draw the graph. One easy way to draw the graph is to select 2 points. So, let's say for x equal to 0, f of 0 is equal to 2 times 0 plus 3 equal to 3. So this is the first point, 0, 3. For x equal to minus 1, let's say, f of minus 1 is equal to minus 2 plus 3 equal 1. Hence, another point is minus 1 plus 1. Let's plot it. So for x equals 0, f of 0 is equal to 3, meaning 1, 2, 3. That's the first point. For x equal to minus 1, f of minus 1 is equal to plus 1. That's the second point. And you draw the line by connecting these 2 points, because you need only 2 points to draw a line, and this is the equation of the function. Another way to approach it is by looking here at this line equation. Plus 3 is b, okay? So this function has a form of f of x is equal to mx plus b, where b is the y-intercept. So 1, 2, 3, this is b. So this is the point at which the function clips the y-axis. So we have the first point. Now, 2x, what is the slope? M is the slope of the function, which is equal to rise over run. Okay, rise over run. So for 2, so to speak, okay, So delta y over delta x is equal to 2. Meaning that for each 2 steps on y, you have 1 step on the x-axis. So this is 1 step for 2 steps, and you connect it together. Actually, you need 2 points to draw it. Okay, you need 2 points. So finding intercepts. Again, it is 2x plus 3, right? This is the function. Okay, for the y-intercept, meaning for x equals 0, so you place x equals 0, and hence f of 0 is equal to 3. This is the y-intercept. This is how we find the y-intercept. You set x to 0, and you get the height at which the function clips the y-axis. Thus, 0, 3 is the y-intercept. For the x-intercept, meaning at which point does the function clips the x-axis this time. This is where the function would be at a height equal to 0. So you said 2x plus 3 is equal to 0, right? And you solve it. 2x is equal to minus 3, and x is equal to minus 3 over 2. So minus 3 over 2 and 0, that would be the x-intercept. Another one, find the slope and intercepts of f of x is equal to 5x minus 10. First, the slope is 5, which is the part multiplying x. So m equal delta y over delta x is equal to 5. As for the y-intercept, you set x to 0, so it is equal to minus 10. Hence, the y-intercept is 0 minus 10. The x-intercept, meaning that at which does the function, at which point clip the x-axis, that would be the point at which the function or the height of the function becomes equal to 0, right? So you set f of x is equal to 0, hence 0 equal to 5x minus 10. When you set f of x equal to 0, so 5x equal 10, and x equal to, thus it would be the point to 0. So in order to plot it, x equal to y equals 0 in such case. This is the first point. Second point is m equal 5, which is, for x equal to 0, this is the y-intercept. Y becomes minus 10, so minus 1, 2, 3, 4, 5, all the way to 10. Minus 10 almost here. And these are the 2 points, and you connect them together to form the equation of the line. Find the equation of the line passing through 1, 2, and 3, 10. Okay, so the equation of the line is given by y is equal to mx plus b, and we simply need to find m and b. First, you replace the first point within the equation, right? So for y equal to x is equal to 1. Hence, 2 equal m times x, which is 1, plus b. And for the second point, for y equal 10, x is equal to 3, so 3m plus b. And we need to solve it like this. So let's at first multiply the first line by minus. So you end up with minus 2 equal minus m plus minus b. Then 10 equal 3m plus b. And we add the first 2 equations. So you add equation 1 with equation 2. So minus 2 plus 10 is equal to 8, equal 3m minus m, 2m, plus 0, because b minus b, okay? Hence 2m equal 8, and m is equal to 4. Okay, so now you replace the value of m in one of the equations. Let us retrieve the first equation. 2 is equal to m plus b, with m equal 4, so 2 is equal to 4 plus b. Hence, b equal 2 minus 4, which is minus 2. So we got the values of m and b, then we plug them into the original form of equation, y equal mx plus b equal 4x minus 2, and this is the equation of the line. Another, perhaps easier way to solve it is, we know that m is equal delta y over delta x. Delta y is y2 minus y1 divided by x2 minus x1, or in other words, the coordinates of one of the points minus the coordinates of the other point respectively. Y of first point minus y of the second point, or y of the second minus y of the first, divided by x of the second minus x of the first, which is equal to 10. Okay, this is y2, by the way. This is y1, this is x2, and this is x1. So it is 10 minus 2 divided by 3 minus 1. 10 minus 2 divided by 3 minus 1 equal 8 divided by 2, which is 4. Okay, so y minus 2, the point slope form, y minus 2 is equal to 4 times x minus 1, another form for it, okay, which is, by the way, y minus y0 is equal to m, the slope, times x minus x0. Simplifying, okay, this is equal to 4x minus 2. So he placed one of the points within the equation, okay, which is the first point. The first point having y0 equal to and x0 is equal to 1. So this is the form y minus y0 is equal to m, which we've gotten moments ago, times x minus x0, hence y minus 2 is equal to 4 times x minus 1. So y is equal to 4x minus 2. So a different style, but the same result. Quadratic functions. A quadratic function has the form f of x is equal to ax squared plus bx plus c, where a should be different than 0 for it to be quadratic. The graph would be a parabola. Okay? Example. F of x is equal to x squared minus 4x plus 3. So how to solve it? You see, we have what is called the discriminant, which is equal to b squared minus 4 times a multiplied by c. Okay? So, again, this is of the form ax squared plus bx plus c. So delta is equal to b squared, which is minus 4 squared, or 16, minus 4 times ac, which is 1, the part multiplying x squared, times c, which is 3, equal 16 minus 12 equal 4. So x1 is equal to minus b minus square root of delta divided by 2a. You need to memorize this formula, by the way, equal 4 minus square root of 4 divided by 2. 4 minus 2 divided by 2 equal 1. As for x2 equal minus b plus square root of delta divided by 2a. So 4 plus 2 divided by 2 equal 6 over 2, which is 3. These are the points where f of x would be 0, or in other words, the x-intercepts. As for the y-intercept, meaning that the value of f of x for x equals 0, the y-intercept would be, if you replace x with 0, you get 3. So for x equals 0, the position, or the point at which the function would clip the y-axis would be at height y equal 3. Now, also another way to approach it, x is equal to minus b over 2a, that's the vertex, okay? So for f of x is equal to x squared minus 4x plus 3, x equal to, f of 2 is equal to minus 1, this is the point of the vertex. And based on the points that we found before, we can plot it, we can draw the function basically. He had gotten the points at which the function becomes 0 by factoring out instead of using the delta discriminant style. So how did he factor that out? You see, x squared minus 4x plus 3 is divisible by x minus 1 or x minus 3. This is how you can find it out. So it is a polynomial equation. Let's place P1. Okay, so P1 is equal to 1 minus 4 plus 3 by replacing x with 1, which is equal to 0. Hence, this function is divisible by x minus 1. So let's divide by x minus 1. X squared minus 4x plus 3 divided by x minus 1. So x squared divided by x is equal to x minus x plus x squared. Okay, then you flip the signs. Minus x squared plus x. It becomes minus 3x plus 3. Okay, minus 3x divided by x is equal to minus 3. Then you multiply here. Okay, plus 3 minus 3x. Again, we flip the signs. This becomes plus and this becomes minus. You add them together, they become 0. The remainder is 0. Hence, x squared minus 4x plus 3 is equal to x minus 1 multiplied by x minus 3. And here it becomes easy to pull the values for x. Okay, so for which values of x this entire equation becomes 0? For x equal to 1 or x equal to 3. And these are the solutions or the points at which the function clips the x-axis. Again, don't forget that we have also the vertex, which is x equal minus b divided by 2a, which is equal to, and for x equal to, f of 2 becomes minus 1. Now, how to plot this function? So, remember that we haven't yet introduced the concept of derivative, which would help us be able to plot the function on a graph. So, given what we have so far, we're going to try the best that we can in order to plot the function without going into concepts like derivation and other things. So, we are basically relying mainly on the critical points. What are the critical points? So we have, for x equal 1, we know that the function becomes 0, so it clips the x-axis. And also for x is equal to 3. This is 2. This is x equals 3. These are the points, okay, where the function clips the x-axis. Now, the vertex, remember, is equal to, or given by x is equal to minus b divided by 2a. Equal to vertex, meaning that's the peak at which you get the head of the parabola. All right, so as x is equal to minus b over 2a equal to, and for x equal to, remember, f of 2, if you solve it, is 4 minus 8 plus 3 equal minus 1. So this is the vertex, 2 minus 1. The vertex means this is the head at which the parabola would get and then flips over, okay? So this is the holder of the cup. So the function would be something like that. This is how you draw it, without even introducing the important concept of derivation and other things. Find the vertex of f of x is equal to x squared plus 6x plus 5. The vertex is equal to minus b divided by 2a. And by the way, again, remember the form of the quadratic equation is given by ax squared plus bx plus c. So minus b divided by 2a is minus 6 divided by 2 equal minus 3. So now f of minus 3 is equal to, you replace x by minus 3, you get 9 minus 18 plus 5, 10, 11, 12, 13, 14, 14 minus 18 is equal to minus 4. So the point is minus 3 minus 4. This is the vertex for the function. Find the roots of f of x is equal to x squared minus 9. In other words, the values of x for which the function becomes 0. These are the roots. We can apply, by the way, the formula I introduced earlier, which is delta is equal to b squared minus 4ac. Given that this quadratic equation and any quadratic equation has the form ax squared plus bx plus c. So b is 0 here. Minus 4 times ac is equal to minus 4 times a is 1 times c, which is minus 9, equals 36. So x1, first root, is equal to minus b, which is 0, minus square root of delta divided by 2a. 36 square root is 6, so it is minus 6 over 2 equal minus 3. x2 equal minus b plus square root of delta, which is 36, divided by 2a. b again equals 0, so it is 6 over 2 equal plus 3. Another easier way to approach it here, so x squared minus 9 can be rewritten as x minus 3 multiplied by x plus 3. And you solve each one of these for 0. Okay, so x minus 3 is equal to 0. So for which value of x minus 3 becomes 0. And once any of these becomes 0, the other one, since you have a multiplication, becomes 0. So these are the roots. Hence, the roots are x equals 3 and x equal to minus 3. Polynomial functions. Polynomial functions are degrees of functions from 3 all the way up. Okay, so for a degree of x squared, like let's say ax squared plus bx plus c, that would be a quadratic equation. Polynomial equations are rather the functions having a degree for the x, okay, or a power for the x would be greater than 2, from 3 and above. So it has the form a n xn plus a n minus 1 xn minus 1, etc. Examples: p of x is equal to x3 minus 2x plus 1. P of x is equal to 4x5 plus x squared minus 7. Properties: the domain is usually also all real numbers, so they are defined throughout R. The scope of real numbers from minus infinity to plus infinity, in other words. This is the domain of definition. Continuous everywhere, so you have values for any value of x, you have a value of y, okay, without a split. This is what continuity means. And smooth curves, so you don't have like a chasm within the curve or a gap. It's continuous and you have a smooth deployment, a smooth variation of the curve. So for example, let's say you have something like that would not be a continuous or a polynomial equation. Why? Because you see the split. Determine the degree of p of x is equal to 7x5 plus 3x squared minus 1. The degree is the highest exponent for x, which is 5. So since the highest exponent is 5, the degree is 5 as well. Evaluate p of 2 for p of x is equal to x to the power of 3 minus 4x plus 1. So you simply replace x with 2, which gives us p of 2 is equal to 2 to the power of 3 minus 4 times 2 plus 1. So 8 minus 8 plus 1, which is 1. Rational functions. A rational function is a ratio of two polynomials given by f of x, this is the format for a rational function, is equal to p of x divided by q of x. So these are two functions divided one on top of the other or over the other, where q of x should be different than 0. Otherwise, the function would blow up. Example, f of x is equal to x plus 1 divided by x minus 2. Now, for the domain, and here's the important thing, the domain could not be R. Why? Because you have a value in the denominator for which the function would be divided, in the numerator, it would be divided by 0, which is impossible. So the function would blow up to infinity, and it cannot be defined at that point. Hence, what that point would be, you solve the denominator, so x minus 2 is equal to 0. Hence, for x equal to plus 2, the function cannot exist. So the domain of the function f is x is defined on R minus the singleton 2, minus this value. Okay? Because for x equal to, the function would blow up, or it can be written as x belongs to the interval from minus infinity, excluded of course, to plus 2. 2 is excluded, union 2 from the other side, which is excluded, to plus infinity. And by the way, these are two disconnected domains here, two disconnected intervals. There's no connectedness because there's a gap. For x equal to, the function cannot be defined. And 2 would become an asymptote, actually a vertical asymptote. Okay? So meaning that for x equal to, the function would have no value. It would be going to infinity, whether plus infinity or minus infinity. We're going to see that later. And hence, for x equal to, there's a gap. There's a disconnection in the function, and it blows up to plus minus infinity. So it would not be defined at that point. Find the domain of f of x is equal to 3 divided by x squared minus 9. Let's solve the denominator. X squared minus 9 can be written as x minus 3 multiplied by x plus 3, or simply x squared equal to 9. Hence, x equal to plus minus square root of 9 equal plus minus 3. So for x equal plus 3 or x equal minus 3, for these two values, the function would blow up to infinity, and it's not defined. In other words, x is equal to minus 3 and x equal to plus 3 are vertical asymptotes, which are two lines that clip the function, that are forbidden. The function cannot touch these two lines. It can approach it, but can never touch these two lines. And the domain can be written in two distinct ways. So R minus 3 and plus 3, R minus these two values, or the function is defined for x belonging to the following intervals, minus infinity to minus 3. Of course, minus infinity is excluded, so is minus 3. Then union, domain between minus 3 and plus 3, meaning minus 2, minus 1, 0, 1, 2, to 3, but with minus 3 and plus 3 excluded. So they are not, the function is not defined at the boundaries. So it is an open set. So for x equal minus 3 or plus 3, the function cannot exist. Union 3 to infinity, with also 3 being excluded, and infinity, which is not a number anyway. Infinity means for any number, but infinity itself as a term is excluded. Radical functions. A radical function contains roots. For example, f of x is equal to square root of x. Now we know that for the real values, okay, x should always be positive. You cannot get the square root in the real domain of a negative value. Only in the complex domain. For complex numbers, for example, minus 4 can become 4i, okay, 4i squared. But in the real scope, among the real numbers, x should be always greater than or equal to 0. Thus, the domain is given by x belonging to 0, infinity, with 0 included. Okay, so 0 it's included, but starting from 0 all the way to infinity. For any negative value, the function does not exist. Also, the range is positive for f of x, meaning that the values can start from 0 all the way to infinity in the positive range for y. But you don't have any negative results for x. Find the domain of f of x is equal to square root of 2x minus 8. So whatever is within the square root should be greater than or equal to 0. Hence, 2x minus 8 greater than or equal to 0. 2x greater than or equal to 8. Hence, x greater than equal to 4. So the domain is x belongs to the following range, 4 included, all the way to infinity. So plus 4 all the way to infinity. Absolute value functions. Definition: let their f of x be equal to x in absolute value, and this is equal to plus x for x greater than or equal to 0 and minus x for x less than 0. Okay, so in such case, you would have positive values of x like that for x greater than or equal to 0. So from 0 all the way up, that would be the function. And for all negative values, minus x, the function would be, for x less than 0, the function would be minus x, meaning that for whatever value of negative for x, y would be like this. This is the V-shaped spoken about. Example, f of x is equal to absolute value of x minus 2. Okay, so for which value x becomes 0, you simply place x minus 2 equals 0, hence x equal 2, and the vertex, the point, would become, okay, this is the point, the head of the function is equal to 0. So 1, 2, this is the vertex. For x equal to y equals 0, and this is the point at which you have the V shape. Positive, for x positive, you have function like this. For x negative, function like this. Evaluate 5 minus 8 in absolute value. That would be absolute value of minus 3, which is plus 3. You basically invert the sign. Find the vertex of f of x is equal to x plus 4. You simply solve x plus 4 equal to 0. Hence, x is equal to minus 4. And y becomes, okay, 0. Actually, since we solved it for 0, so y is automatically 0. So the vertex point is minus 4, 0. And let's plot it. So for x is equal to minus 4, minus 1, 2, 3, and 4, this is where you would have a positive side like this and a negative side like this. This is the V shape, because for x greater than 4, okay, or greater than minus 4, you would get minus 3 plus 4 is plus 1, right? Now, for values less than minus 4, so minus 5 would be, okay, minus 5 would be, f would become, plus 1, but in this side, from this side. Piecewise functions. A piecewise function uses different formulas on different intervals. So example, f of x is equal to x plus 1 for x less than 0, and x squared for x greater than or equal to 0. So for x less than 0, it would be x plus 1, a different formula. For x greater than or equal to 0, it would become x squared. So this is how it would become. Okay, here for x less than 0, so for x minus 1, it becomes 0. For minus 2, it becomes minus 1. And this is what the function would look like. You see here, notice something, that it's not continuous. Why is that? Because f of 0 to the right, the value of x0 to the right, is equal to x squared, okay? It's different than the value of the function to the left, right? So for f of 0 to the left, it doesn't exist, okay? You have f of minus 1 is equal to 0, okay, from the left. So you have two different equations, basically. Two different formulas, two different curves. They are split, so the function is not continuous at that. By the way, continuous means that the limit to the right is equal to the limit to the left. More than that, the value of the function to the right of 0, let's say, is equal to that to the left. It's equal to f of 0. F of 0, notice something. F of 0 on the left is equal to 1. F of 0 to the right is equal to 0. Since you have two different values, hence the function is not continuous. Now, f of minus 2, okay, is equal to minus 2 plus 1, which is minus 1. F of 3 is equal to 9. So you have different values we are evaluating here. Now, evaluate f of minus 1 and f of 2 for the following function. Okay, so this is what you need to pick out or to conclude from the piecewise function. F of minus 1 is the value of the function at x is equal to minus 1, meaning x negative, strictly negative. Where is x negative? It would be for the first formula. So you need to apply the first formula. X is equal to minus 1 for f of x equal to x plus 1. This is where you need to fill x is equal to minus 1, and you get minus 2 plus 1 equal minus 1. But for f of 2, or f for x equal 2, it is equal to x squared plus 1 for x equal 2. So you need to use the second function. Why? Because in such case, for x equal to, x would be positive. It would be greater than or equal to 0 at least. So we use x squared plus 1, not the first equation. So f of 2 is equal to 4 plus 1 equal to 5. Finally, in this module, we studied constant functions, linear functions and slopes, quadratic functions and parabolas, polynomial functions, rational functions and asymptotes, radical functions and domain restrictions, absolute value functions, piecewise defined functions, and these elementary function families serve as the building blocks for limits, continuity, derivatives, integrals, optimization, and advanced function analysis throughout calculus. 3. Function transformations. Function transformations allow us to generate new graphs for existing ones without constructing them point by point. By applying shifts, reflections, stretches, scaling, and compressions, we can quickly understand the behavior of a wide variety of functions without having to study them all over again. So we can base what's happening, okay, on like the primary function or the root function. And the root function that we already know how to plot and how to analyze, you can shift it to the right, to the left, or magnify it based on what's happening, based on the transformation that is apparent. So we can quickly understand the behavior of a wide variety of functions. Transformations are fundamental in calculus because they reveal how functions are related and help us analyze graphs efficiently. Throughout this module, we begin with a parent function f of x and study how various operations modify its graph. What are the different parent functions? Common parent functions include the first bisectrix, which is the line that clips the first quadrant in half. It has an angle of 45 degrees with the x-axis, which is the function f of x is equal to x. You have f of x is equal to x squared. By the way, this is the graph of f of x is equal to x. For f of x is equal to x squared, that would be the parabola. F of x is equal to absolute value of x. That would be the v function drawn like that. And f of x is equal to root x. And f of x is equal to sine x, which is sine 0 is equal to 0. This is the sine, okay? and it has a period of 2 pi. Starting with vertical shifts. A vertical shift moves a graph up or down, which is the y-intercept, by the way. This is the shift and where it's happening. The value of k that's being added to the function. So if it is a positive value, the graph would be lifted upwards, like on a crane, right? So let's say you have a curve like this. If the value of k, which is again the y-intercept, if you remember, if it's positive, the function would be lifted upwards. If it's negative, it would be pulled downwards. So where k is greater than 0, the graph shifts upward. If it's negative, it shifts downward. And if it's 0, then there would be no shift at all. Starting with f of x is equal to x squared. Consider g of x is equal to x squared plus 3. So this is the function. F of x is equal to x squared. This is what it would look like. So g of x is equal to x squared plus 3. You notice k, it is positive, and this is plus 3. So how would you draw it? The vertex is elevated by 3 units in such case. Let's change the value of the color, rather, not the value, okay? So the new vertex is given by 0, 3, correct? And that would be the function. So it would be the same y is equal to x squared, the same parabola, except it has been lifted up by 3 squares on the xy axis. So on the scale, on this grid, it has been lifted by 3 positive units. And the new vertex, which is again the coordinate of the point where the head of the parabola is lying. It is the tip of the egg, so to speak. The head, the curve of the egg, okay? It is 0, 3. G of x is equal to x squared minus 5. The parabola, in such case, since k is a negative number equal to minus 5, it would shift downwards by 5 units down. So the new vertex would be 0, minus 5. Let's plot it. That would be minus 1, 2, 3, 4, 5. So the function, let me change the color, would be like that. As for the original function, which is y equal x squared, the original parabola, starts from vertex 0. Pardon me for the inaccuracy of the graph, but the point is, it is shifted downward. So g of x is the one in the blue, remember? And f of x is the one in the red. Determine the new vertex after shifting f of x is equal to x squared upwards by 7 units. So basically, how do we shift the function upwards by 7 units? This becomes g of x is equal to x squared plus 7. And the vertex, by the way, is the value of the function, is the height of the function when x is equal to 0. So you simply replace x by 0, and the vertex becomes 7. Hence, the new vertex is 0, 7. So for x equals 0, y equals 7, that would become the new plot of the parabola. Notice that the original vertex was 0. Why is that? Because for f of x is equal to x0, when x is equal to 0, y is equal to 0, meaning that for x equal to 0, the parabola clips the y-axis at y equal to 0 also. But for an upward shift of 7, this becomes that when x is equal to 0, the function would be elevated by 7 units. Let's plot it out. So that would be y equal x squared, the original one. Then 1, 2, 3, 4, 5, 6, 7. That would be the upward shift. And the function shifted upward. And this is, by the way, again, the meaning of the vertex, meaning that in such case, for x is equal to 0, y is equal to 7. So the parabola has been shifted 7 units up. Describe the transformation g of x is equal to square root of x minus 4. Now, k in such case is negative. It is equal to minus 4, so the y-intercept is minus 4. The vertex, by the way, would be 0, minus 4. Why is that? Because for x is equal to 0, y is equal to minus 4. Or g, rather. Yeah, g of x is equal to minus 4, which is y, which is the elevation. Now, how to graph at first square root of x? Let's go from there. First of all, this is a function defined only for x greater than or equal to 0. So for x equals 0, g or f of x, let's say, is equal to 0. Then for 1, 2, 3, 4, for x is equal to 4, that function becomes 2. All the way up, okay? This is, however, f of x, the original function given by square root of x. So it is the root function. But for g of x, it is shifted by minus 4. The vertex is 0, minus 4. In other words, it would sit 4 units beneath the x-axis. This is minus 4. And the new function, g of x, would be like that. That's the difference. Horizontal shifts. Horizontal shifts move graphs left or right. The general form is g of x is equal to f of x minus h, where if h is greater than 0, this would move the graph to the right. If h is less than 0, it would shift it to the left. So you have, let's say, y is equal to x, f of x minus 1, meaning you replace x by minus 1. So it would be y is equal to x minus 1. In other words, where y becomes 0, okay, it would become 0 for x is equal to plus 1, because you solve it, you solve x minus 1 is equal to 0, hence x is equal to plus 1. So in other words, the function that used to clip the x-axis at y is equal to 0 and x equals 0, okay, this function y is equal to x shifts to the right. So this is y is equal to x minus 1. Why is that? Because y is equal to x minus 1 means that for x is equal to plus 1, y becomes 0. So it has shifted to the right. Meanwhile, for h is less than 0, meaning that if this value h is negative, the shift would be to the left. So the direction is opposite to the sign on the inside of the parenthesis. This is an important caveat. Example, g of x is equal to x minus 2 squared. Remember that the root function, the parent function, so to speak, would be f of x equal to x squared. So here in this case, notice that h is equal to plus 2, okay? And this is of the form again of g of x is equal to x minus h squared, okay? So it is of the form f of x minus h. H being positive, so the shift is to the right. Now, what is the vertex? The vertex is the value for which y becomes 0, so it is x equal to and 0. And the graph becomes something like that. So x minus 2, right? We had originally. So this is for x is equal to plus 2. It is for x equal to, that's y is equal to 0. So the vertex becomes here, and this is the function. It is the same, y is equal to x squared, but shifted to the right by 2 steps. As for the second function, g of x is equal to x plus 5 squared of the form f of x minus h, except this time h would be negative because the minus has become positive. So it is x minus h. That gives you x plus 5 on the inside. Okay, what is the vertex or the value of x for which g becomes 0? So x plus 5 equals 0, hence x is equal to minus 5. And in that case, the shift would be to the left, not to the right. So the vertex is at minus 5, 0, and the plot of the function becomes like this. So minus 1, 2, 3, 4, 5. This is minus 5. That's the vertex. And this is y equal x squared. Okay, x plus 5 squared rather. Okay, but yeah, what I meant to say is this is x squared but shifted to the left. Determine the vertex of g of x is equal to x minus 6 squared. First, the vertex is plus 6, 0. And here's how you know. So it is of the form f of x minus h, with h being positive here, h equals 6. Hence, the shift is 6 units to the right. So for which values g of x becomes 0? It is for x minus 6 equals 0, or x is equal to plus 6. Hence, the vertex is 6, 0. And the graph becomes, so for x is equal to 1, 2, 3, 4, 5, 6. This is y equal x squared, shifted 6 units to the right. Exercise 4, g of x is equal to the square root of x plus 3. Here the shift becomes to the left. The vertex is x minus 3. Okay, so it is minus 3, 0. And this square root becomes shifted to the left by 3 units, meaning that it becomes, instead of something like that, it becomes, okay, 1, 2, 3 to the left, something like that, shifted 3 units to the left. Reflections. Reflections flip graphs across an axis. So let's say we're talking about reflection across the x-axis. The general form would be g of x is equal to minus f of x. As an example, g of x is equal to minus x squared, which is the equation of a parabola. In such case, the parabola would open downwards, would be flipped downwards, except or instead of opening upwards. So g of x would be the mirror image of the f of x, and the mirror itself would be the x-axis, so it would be flipped downward. The parabola opens downward instead of upwards. To show you how it works, so the original parabola f of x equal x squared is like this, passing by, of course, x0, y0. But g of x, which is equal to minus f of x, is drawn like this. So for every x value, you have a y value that is negative. That is the mirror image, not negative necessarily. It is the flipped image of the function above. It's like an image in the water being the mirror image of something that is above. So above the x-axis would be what is above the water, and below would be the mirror image for the function. Reflection across the y-axis. The general form is given by g of x is equal to f of minus x. As an example, g of x is equal to minus x to the power of 3 or minus x3. The graph reflects across the y-axis. In other words, for whatever negative value of x, you would have the same y, the same elevation for the graph to the left, and vice versa. So for the positive values, you would have the same y. Okay, so to give you a clearer perspective, let's say you have f of x is equal to x. So g of x is equal to minus x. In other words, for minus 1, g of x would be like this. Okay, minus 1, minus 2, you have minus 2. Minus 3, you have minus 3. And notice, f of x is equal to x is the mirror, actually g of x is the mirror image of f of x equal to x in respect of the y-axis, which is, as you remember, it was the V-shaped function. This is how it's working over here. So for g of x is equal to minus x, the reflection of x is g of x, okay? It is the reflection across, but here in this case, across the x-axis. So the graph becomes an inverted V, okay? As an example also, g of x is equal to square root of minus x. So this is the reflection of square root of x that extends in the negative direction, okay? In the negative x direction. So square root of x is equal to, okay, for 0, 0, for 4, it's equal to something like that, okay? Something like that. So g of x, which is square root of minus x, so for minus 2, 3, 4, you would get the same value of y. For minus 16, let's say, you would get minus 4, plus 4, I'm sorry, because minus minus plus. So you would get plus 4, the same value, but in the other direction. So it is the reflected image of the original function in respect of the y-axis. Vertical stretching and compression, or in other words, scaling. Okay, multiplying a function by a constant changes its height. The general form is given by g of x is equal to a times f of x. Vertical stretch, if a in absolute value is greater than 1, the graph stretches vertically. Example, g of x is equal to 3x squared. So it is being magnified. The y values increase 3 times for each x. That's the main thing about it. Okay, so 3x squared, okay? Let's consider, as we know, this is x squared. So what would become with 3x squared? Let's change the color. For x equals 0, nothing changes. But for x is equal to 1, okay, g of x becomes 3. For x equal to g of x becomes 12. So it is increasing in such a speed much steeper than the original function. It's not, by the way, don't mistake it with, it still starts with 0, by the way, okay? It's not like a shifting, no, it's a scaling, meaning that it becomes much steeper, much higher. This is what the multiplication is doing. It is stretching, or you would have a compression if a, I think, is less than 1. Vertical compression, if the absolute value of a is between 0 and 1, so it would have a small value, if it would be a fraction, and once you start multiplying a function by that, it would compress it instead of stretching it. So for example, g of x is equal to 1/2 x squared. All y values become half of the values of the original y, half as large. So this is the original function. The new function becomes like it starts increasing in a lower manner, you know. They become half of the values. Identify the transformation g of x is equal to 4 times absolute value of x. Okay, so for the original value or plot of x, let me change the color into the red one. You would have a plot like this, the V-shaped plot. For f of x equal to x. Meanwhile, for g of x is equal to 4x. And you'll start noticing something. For x equal 1, g of x is equal to 1, 2, 3, 4. And you go from here. Since it's a line, it's easy to draw it, okay? Because originally for x equals 0, they both have value equals 0. And on the next side, which is the mirror image, it becomes like that. You see? So it became, this v became sharper. Why? Because it's being magnified. That's why. As for g of x is equal to 1/3 square root of x, that would be a vertical compression by factor of 1/3. So the curve would be compressed. It would be pulled down. Here it is being steepened in the above example. Why? Because as you multiply the function by a factor, it increases its steepness. It becomes, for example, for the V shape, it becomes much sharper. Next, horizontal stretching and compression. The general form is g of x is equal to f of bx, meaning that we're not multiplying the function itself, but we are replacing x by n times x or b times x, where b, when it is a value that is greater than 1, you would get a horizontal compression. So when b, the multiplier of x, in absolute value is greater than 1, the function is being compressed. However, it is in the horizontal direction, meaning that let's say you have a function like this. It would be like you are pressing it against the y-axis or in the direction of the y-axis, like inducing or causing a compression. So the graph compresses horizontally. Example, g of x is equal to sine 2x. The graph completes its cycle twice as fast. To give you a picture, so sine x originally, first for x is equal to 0, it is 0. Then for pi over 2, which is 90 degrees, it becomes 1. Then for pi, it becomes 0. Then for 3 pi over 2, it becomes minus 1. Then for 2 pi, it completes the cycle. Okay? Now, what would become of sine when you have 2x? So, for 2x, notice something. First, for 0, it doesn't change. But when you have, okay, pi over 2, pi, 3 pi over 2, and 2 pi, okay? I'm trying to get it as accurate as I can. So, for 0, it is 0. For pi over 2, 2 pi over 2, this is pi. So, it becomes like this. Now, for pi, this becomes 2 pi. So, it becomes also 0. Okay? Then, for 3 pi over 2, like this, for 2 pi. So, you see, it has completed 2 cycles in the same period where for the original function, it would have completed only 1 cycle. The point is, it is like as if we compress the function like this, okay, decreasing its period. So its frequency has become higher. As for the horizontal stretch, in which case the absolute value of b would be a value between 0 and 1, greater than 0, less than 1. In such case, the graph would stretch horizontally instead of being compressed. And as an example for that is g of x is equal to sine x over 2, where the graph would become wider, as if like you pulled the sine wave and you stretched it across the x-axis. Let us check it out. So for the original function, sine x, okay, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so that would be like this. Now, for x over 2, let's check it out. pi over 2, pi, 3 pi over 2, and 2 pi. So for x equals 0, the same thing. Now for pi equal, like for pi over 2 or for pi, okay, to facilitate the drawing. For x is equal to pi, okay, you have g of x is equal to sine pi over 2. So this is where the function becomes 1. And this is, so at 2 pi it becomes half period. You see, it has been stretched. So it would require 4 pi to complete a full cycle. This is how different it is from the original sine x function. It has been stretched, meaning that it would take a longer period, a longer time to complete one cycle, to have one full period. In other words, like from the perspective of physics, this wave has a longer period and a lower frequency. Identify the transformation. G of x is equal to f3x. This is a horizontal compression by a factor of, not 3, factor of 1 over 3, because the factor of compression is the inverse of b, you see, okay? So, because I understand it is an oxymoron, you're multiplying by 3, right? You're multiplying x by 3, however, it's not, it's compressing, not stretching. So you are compressing the function by 1/3. You are reducing its value by 1/3. Now, exercise 10. Identify the transformation. So g of x is equal to f of x divided by 5. You are dividing, dividing by 5, meaning you're multiplying by 1 over 5, which is 0.25. So you are multiplying by a b value, which is between 0 and 1. In other words, you are stretching the function. So it is stretched by a factor of 5. And notice something. You inverse the term, meaning that we're not stretching by 0.25. No, you are stretching by 5, which is the inverse of 1 over 5. Okay? So it is the number in the denominator. This is the stretching factor. Combined transformations. Several transformations may occur simultaneously. The general form is given by g of x is equal to a times f of b times x minus h plus k. Okay, so what do we have here? A is the vertical stretch or compression. If a is greater than 1, then you have a stretch less than 1. Between 0 and 1, you would have a compression. As for b, horizontal stretch and compression. Now, if b is greater than 1, you have a compression. Less than 1 or between 0 and 1, you have a stretching. H greater than 1, you'd have a right shift. Less than 1, you'd have a left shift. That's the horizontal shifting. And k is the vertical shift. If k positive, the function would be going or be shifted upward. If it's negative, it would be shifted downwards. So consider g of x is equal to times x minus 3 squared plus 4. Okay, first you have h is positive and it's equal to 3. Hence you have a shift to the right by 3 units. Also, you have a vertical stretching by factor of 2. More than that, you would have an upward shift by 4 or 4 units. Okay, so this is how we plot it. You have right shift, 3 points, okay? This is the right shift. You have 4 upward shifts vertically. So the function or the vertex would start from here. This is the vertex, by the way. And you have a scaling by 2, meaning that, let's say the original function would be like that. This function would be steeper, meaning it would be narrower, okay? So it would switch like that. Example, consider g of x is equal to minus square root of x plus 1 plus 2. First of all, you have a multiplication with minus, meaning that the function is reflected across the x-axis. This is the first caveat. Then you have a shift to the left. Why? Because x minus h, right? Within the square root, you see, for x to become plus 1, h should be negative. Given that h negative, x minus minus h becomes x plus h, which is h being equal to minus 1 in such case. Hence, you have a shift towards the left in the x direction. So shift left 1 unit, reflection across the x-axis due to the minus 1 multiplication, and an upward shift, which is the y-intercept of plus 2. So k equal to greater than 0, so it is an upward shift. And the vertex, by the way, is, okay, so you have x plus 1, h is equal to minus 1. This is the first point of the vertex. And y equal plus 2, not the first point, but the first coordinate, and y equal 2. Hence, minus 1, 2 is the vertex of the function. Transformation strategy: to analyze g of x is equal to a f of b times x minus h plus k. Follow these steps. You start with the parent function, the original function. Apply horizontal transformations first, the one where you're multiplying x, right? And this is like a shift, horizontal shift to the right or to the left. B is the horizontal stretching or compression, right? So A is the vertical stretching or compression, and K is the shift, vertical shift. Apply reflections, apply vertical stretching and compression, and apply vertical shifts last. So for K, this is the last transformation that you would apply. Analyze g of x is equal to minus 2 times x plus 1 square plus 5. At first, x minus h concerns the horizontal transformation. So you have x minus h, okay, gives you x plus h, which we have here, x plus 1. H is equal 1. This is a left shift of 1. Okay, by the way, 5 is clearly an upward shift, okay, on the vertical intercept. That's the vertical intercept. As for, by the way, the parent function is f of x is equal to x squared. And minus 2 is a scalar. Now, again, shift left with x plus 1. The vertical stretch is 2 because you have 2 times x plus 1 squared. But more than that, 2 is multiplied by minus, meaning that this is a reflection across the x-axis, so it is downward. Shift upward with plus 5, and the vertex is equal to minus 1, 5. This is the vertex. So 2 times x plus 1 equals 0. Hence, x is equal to minus 1, which is h, by the way. H equal minus 1, that's the first coordinate. And y equal 5, which is k, by the way. K equal plus 5. H and k form the vertex. So the vertex is minus 1, 5. This is the point, if you want to plot it. So it is minus 1 plus 5. This is plus 5, supposedly. This is the point where you have the head of the parabola laying. However, it is flipped downward, right? And it's multiplied by 2, meaning you have a scalar. So it is steeper than the usual x squared function. Another one, describe all transformations. G of x is equal to x minus 4 squared plus 2. At first, remember, for x minus h, when h is greater than 0, and in this case, h is equal to 4, you have a shift to the right of 4 units. Then, we don't have any scaling or horizontal stretching compression, but we have an upward shift of plus 2, which is the vertical intercept, by the way. Okay, so shift up, not vertical intercept, it won't be like an accurate term, but it's the vertical shifting, upward shifting of plus 2 units. Hence, the vertex is given by h and k. So k equal plus 2, which is positive. So upward shift, h is positive, which is equal to 4, which is, it's determining the right shift, horizontal shift of right unit, okay, the horizontal right shift of 4 units. So the vertex is given by hk, which is 4, 2. This is the point at which you get the parabola. So 1, 2, 3, 4 plus 2, that's the vertex, and it would be something like this. Describe all transformations. We will start with the horizontal transformation. So x minus h is equal to x plus 2. So h equal minus 2, negative. Hence, you have 2-unit shifts on the horizontal axis to the left. So shift left 2 units. Then we don't have any upward downward shift, but you have a 3 scalar. So vertical stretch by factor of 3. Since it is negative, it is a reflection across the x-axis. So it is flipped downward at first. Okay. So we have shift of 2 units to the left. This is 1, this is 2. You don't have any upward downward shifts, but it is a scalar by 3. Okay, so times 3 scale, meaning that this parabola would be much steeper. Okay, the elevation would be steeper, except it is flipped in respect of the x-axis, meaning that it is reflected downward. This is the y-axis. Hence, the function would be something like that. Describe the transformations for g of x is equal to square root of x minus 5 minus 1. Starting with x minus h is equal to x minus 5. Hence, h equal to 5. You have 5 units shift to the right. After that, it's multiplied by 2. So you have a vertical shifting, or vertical scaling, I'm sorry. The vertical shifting is this one. You have a vertical stretch by a factor of plus 2. So it is twice the size, twice steeper. And you have a downward shift of 1 unit because you have minus 1. Okay, k is negative, which is equal to minus 1. So this function would be lower than the original function by 1 unit. Again, the vertex is formed by h and k equal to, h is equal to 5 and k equal to minus 1. Hence, this is the plotting of the function. So you have 1, 2, 3, 4, 5 units shift to the right, downward shift by 1 unit, which form the vertex, by the way, and a vertical stretch by a factor of 2. So you would get something like that, okay? But it would be steeper than the original square root of x function. Describe all transformations for g of x is equal absolute value of x plus 3 minus 4. As a reminder, x in absolute value is the v function, okay? This is x, which has a symmetry in respect of the y-axis and a v-shaped, and it cuts the origin, okay? So it intercepts the x-axis at y equals 0 and the y-axis at x equals 0, basically on the origin. And for whatever value of x, negative or positive, you would have the same y, the same level. So this would be the root function for which we will apply the transformation. First, x plus 3 is simply equal to x minus h. Hence, h is equal to minus 3. As for k is equal to minus 4, and these form the vertex. Remember, the vertex, let's call the vertex v, is given by hk, which are here minus 3, minus 4. So let's find this point, minus 1, 2, 3, minus 1, 2, 3, 4. This is a critical point called the vertex. But first of all, okay, so h equal minus 3, meaning that you have a shift to the left by 3 units, and minus 4 downward shift by 4 units. And this is the function. It would be v starting from here, okay? So something like this. Describe all transformations g of x is equal to sine 2x. Here we have an horizontal compression by factor of, remember, 1/2. So it is the opposite of what's happening within. So within you're multiplying by 2, but the compression, you don't say a compression by a factor of 2, no. Because times 2 means stretching originally, okay? But since x is becoming 2x, so each value of x is being compressed, okay? So the compression is by a factor of 1/2, meaning that the function is being compressed on the horizontal scale. So what used to take 2 steps to get you to the same y value, it's getting, okay, it's taking half of the steps to get the same y value. You see, because y is equal to x, y is equal twice the value of x. This is why it seems to be compressed. So the compression factor is the inverse of the multiplicator within. This is very important. The period becomes pi instead of 2 pi. Okay, so this is what happens. Again, this is the original function, 0, pi over 2, pi, 3 pi over 2, and 2 pi. The original function would be like this. But here in our case, this is what's happening. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. So, in such case, when we're talking about sine 2 pi, so for pi over 2, 2 pi becomes, 2 times pi over 2 becomes pi. So, actually, the function would get to 0 here, way before you get to the actual pi, because you're multiplying by 2. Then, for pi, it becomes 2 pi. For 3 pi over 2, it becomes, 3 pi and 4 pi, okay? So you see, we have compressed the function in the horizontal direction. So the frequency has become higher. Finally, in this module, we studied how functions can be transformed through vertical shifts, horizontal shifts, reflections across x and y axis, vertical stretching and compression, horizontal stretching and compression, multiple transformations applied simultaneously. General transformation model is given by g of x is equal to a times fb x minus h plus k. And this provides a powerful framework for understanding how complicated functions arise from simple parent functions. Mastery of transformations greatly simplifies graphing, function analysis, and many applications encountered throughout calculus. Function composition and inverses. Function composition and the inverse functions are fundamental concepts in calculus and higher mathematics. Composition allows us to combine multiple functions into a single one, while inverse functions allow us to reverse the effect of a function. By the way, an inverse function is symmetric to the original, to its original, in respect of y equal x, which is the first bisectrous. This is the line cutting the first and third quadrant of the grid in half. Okay, so these ideas appear throughout calculus, differential equations, optimization, physics, engineering, computer science, and mathematical modeling. In this module, we will study composite functions, domains of composite functions, one-to-one functions, horizontal line test, inverse functions, graphs of inverse functions, and applications of inverse functions. Composite functions. Another word for a composite function, it is a nested function, meaning a function within another. Let's see what it means. A composite function is formed when the output of one function becomes the input of another function. So if f of x and g of x are functions, then f not g of x is equal to f of g of x. And this is called the composition of f with gx. Meaning that, let's say f of x is equal to x squared, and g of x is equal to x plus 1. Hence, f of g of x is equal to, you replace x squared by x plus 1. So it becomes x plus 1 squared equal x2 plus 2x plus 1. Similarly, g naught f of x is equal to g of x. Okay, now in general, f of g of x is different than g of f of x. So if you nest one in the other, it is different than nesting the second one in the first. So composition is not commutative. It's not like saying x times y is equal to y times x. It won't produce the same result when it comes to the composition or function nesting. Example, let f of x be equal to x plus 1 and g of x be equal to x squared. Find f naught gx. Okay? F naught gx can be rewritten as f of g of x. We simply replace g of x within x. This is what's happening. So f of g of x is equal to 2 times g of x, wherever x exists, plus 1, equal 2x squared plus 1. Now find g of f of x. G of f of x is equal to, okay, so we have 2x plus 1, this is f, and g equal x squared. We need to nest f within g. So you replace x by 2x plus 1, and then you square it, equal 4x squared plus 4x plus 1. And notice that f of g of x is different than g of f of x, which means that the transaction is not commutative, unlike the product, as we mentioned before. F of x is equal to 3x minus 2, g of x is equal to x plus 5. F of g of x is given by, okay, so we replace x within f by x plus 5. You simply are doing, okay, so this is f of g of x is equal to 3 times g of x minus 2, which is equal 3 times x plus 5. We replace x by x plus 5 minus 2, 3x plus 15 minus 2, or 3x plus 13. And this is the answer. So again, we replace x within f by g. Okay, wherever you find x, you replace it by g of x. As simple as that. So 3 times x plus 5 minus 2 equals 3x plus 15 minus 2, or 3x plus 13. Using the same functions, find g of f of x. Now, g of f of x, here we need to replace x and g by that of f. So f is equal 3x minus 2, g equal x plus 5. Hence, g of f of x is equal to, instead of x, you place 3x minus 2 and plus 5, which is 3x plus 3. Domain of composite functions. The domain of a composite function requires that the inner function is defined. The output of the inner function belongs to the domain of the outer function. So let f of x be equal to square root of x, and g of x be equal to x minus 4. F of g of x becomes square root of x minus 4. You see, almost the same domain. So f of g of x would be like defined, okay, in terms of the square root. And another note is that x minus 4 should also has a domain within the square root. Okay, so it cannot be negative within the square root of f. So for the square root to exist, x minus 4 should be greater than or equal to 0, hence x greater than or equal to 4, and the domain becomes x within 4, the interval 4 to infinity, with 4 included and infinity excluded. So it is closed from the left side, open from the right side. Let f of x be equal to 1 divided by x, and g of x be equal to x squared minus 9. Find the domain of f of g of x. Okay, f of g of x is equal to 1 divided by x, where x becomes equal to x squared minus 9. So it is equal to 1 divided by x squared minus 9. Now remember, we cannot divide by 0, so we need to check for the values for which the denominator becomes 0, because this is where the function blows up, and this is where blows up to infinity, and this is where the function would have asymptotes, which are barriers over which the function can approach but can never get. It would be like boundaries, right? So x squared minus 9 different than 0, so x minus 3 times x plus 3 different than 0, hence x should be different than 3 or different than minus 3. So the domain is given by minus infinity minus 3 united by, okay, minus 3 to 3 united by 3 to infinity. So x is between minus infinity to minus 3, both of them excluded, union, minus 3 to plus 3. So between minus 3 and plus 3, but without these two values. So it is open on both sides, meaning that minus 3 and plus 3 are forbidden values, but the ones between them, like for example minus 2, minus 1, plus 2, plus 1, are acceptable. And union, the value right after 3, meaning 3.1, 3.2, all the way to infinity. One-to-one functions. A function is one-to-one, also called injective, if different inputs produce different outputs. Mathematically, f of a equal f of b implies that a is equal to b, right? Now, one-to-one functions never repeat a y value. So, for a unique value of x, you have a unique value of y. So y equal x squared cannot be injective because it is actually symmetric in respect of the y-axis. It is called an even function. We will get to that later, which is f of plus x or f of minus x is equal to f of plus x, okay? So the values are being repeated. They are being mirrored in respect of the y-axis, hence it would not be injective. f of x equal to x plus 3, for example, is one-to-one or injective because every output is unique and corresponds only to exactly one input. And by the way, the graph for 2x plus 3, as you remember, this is an upward shift. You have the vertical intercept, okay, of 1, 2, 3. And for y equals 0, x is equal to minus 3 over 2, which is minus 1.5. Okay, for x equal, for y equals 0, minus 3 over, minus 1 half, meaning minus 1 half. This is minus 3 over 2. So these are two critical points, and this is the function. And as you notice, for any x value, for each x value, you have a unique y value. No repetition. Meanwhile, and another thing I wanted to say, so for x equals 0, y equals 3, this is the y-intercept. But meanwhile, for f of x is equal to x squared, it's not one-to-one because f of 2 and f of minus 2 is equal to 4. So you have a symmetry, and for two different unique values of x, one being positive, actually, you can consider them unique because even if they are of the same absolute value, but one is 2, the other is minus 2. So one positive, one negative, you have the same height, the same altitude. So it's not injective, okay? Two different inputs produce the same output. This is why. Determine whether f of x is equal to 5x minus 7 is one to 1. Yeah, solution. Okay, so linear functions usually would not repeat a value. Okay, so with non-zero slope are 1 to 1. Therefore, f of x is equal to 5x minus 7 is 1 to 1 because for each x value you have a unique output. And this is the graph. So minus 7, this is a downward shift by minus 1, 2, 3, 4, 5, 6, 7. First vertex. Okay. Now, for x equals 0, y equals 0. For x equals 0, y equals minus 7. I'm sorry. Now, for y equals 0, 5x minus 7 equals 0. 5x equal to plus 7. X would be equal to 7 over 5. Yeah, so 1 point something. 1.4 something, okay? So that would be the vertex, and this is the function. But for each x value, you have a unique y value, and with no replication, with no repetition, hence it is 1 to 1. Determine whether f of x is equal to x squared plus 1 is 1 to 1. It's so obvious that since x is squared, okay, you can get the same y value for negative and positive x values, meaning that f of 2 and f of minus 2 both are equal to 5, okay, which is 4 plus 1, because minus 2 squared plus 1 and plus 2 squared plus 1 give us both 5, hence the function is not 1 to 1. Horizontal line test. Horizontal line test is used to determine whether a function is 1 to 1. The rule: a function is 1 to 1 if every horizontal line test cuts through the function or intersects with the curve, whatever you want to name it, one time, only once. So the graph of x, y equal x3 passes the horizontal line test, okay? So it only clips it one time, hence it is 1 to 1. So for each x value, you only have one y value. Meanwhile, for y equal x squared, it fails the horizontal line test given the fact that, again, it's graphed like this, and for y equal 4, this is the horizontal line given by y equal 4. It clips the function at 2 points. One is at x equal minus 2, the other as, it passes through the right section or the first quadrant. It's equal to x equal plus 2. So for x equal minus 2 and plus 2 both, you have the same value for y. You have the same altitude for the function. Hence, it's not it's not 1 to 1 because it fails the line test, horizontal line test. For y equal ex, it passes the horizontal line test. Okay, every horizontal line intersects the graph exactly one time. So e of x is 1 to 1. Inverse functions. An inverse function reverses the action of a function. So if y is equal to f of x, the inverse function is written as f minus 1 of x. And as a result, it becomes x as a function of y. Meaning you reverse x and y. Y becomes x and x becomes y. So you are getting the value of x in respect of y. And satisfies f minus 1 of f of x is equal to x. Okay? Or f minus 1 of x is equal to x. Forget about the annotations here. They are a little bit complex, but in practice, things will get much easier to comprehend. Procedure for finding an inverse for a function. First, write y equal f of x. That would be the original function. Interchange x and y, then solve for y instead of solving for x, and replace y by f minus 1 of x. Find the inverse of f of x is equal to x plus 5. First step, you replace f of x with y, so y equal to x plus 5. Then we interchange the values, meaning that y becomes x and x becomes y. So x equal to y plus 5. Then you solve it for y. This is step 3. So it becomes x minus 5 equal to y, then y equal x minus 5 divided by 2. So again, 2y equal x minus 5, then y equal x minus 5 divided by 2. And this is the inverse function. Find the inverse of f of x equal 3x minus 1. Okay, so y equal 3x minus 1. Then we interchange y and x, so it becomes x equal 3y minus 1. So 3y is equal to x plus 1, hence y equal x plus 1 over 3. And this becomes the inverse function f minus y minus 1 of x, okay, or y equal x plus 1 over 3. So the inverse function of f of x is f minus 1 to the power of minus 1 of x equal x plus 1 divided by 3. Verify that the inverse is correct. With f of x is equal to 3x minus 1, f minus 1 of x is supposedly equal to x plus 1 divided by 3. Now, as a side note, we need to know and to understand that an inverse function is a mirror image, meaning it's symmetric to the original function, to its original, in respect of the equation or the line, the first bisectrous, y equal x. Hence, f of minus 1 of x, meaning that the nesting of the second function within the first should produce x. So let's check it out. F of f minus 1 of x is equal to 3 multiplied by, we replace x with x plus 1 divided by 3. So x plus 1 divided by 3 minus 1. We can factor out 3. So what remains is x plus 1 minus 1 equal x. Hence, this is truly the inverse function of f of x equal 3x minus 1. The graph of a function and its inverse are reflections of each other across the line y equal x. This, by the way, would invert everything. So the vertical asymptote becomes the horizontal asymptote in the inverse. The critical points, you invert their coordinates. So if you have a critical point, let's say a 1 minus 3, the inverse point becomes a minus 1, for example, of minus 3, 1. So everything becomes inverted. X becomes y and y becomes x. So for instance, f of x is equal to x plus 1 with the y-intercept in the first function is b equal 1, correct? And for 2x plus 1 equals 0, okay, so for which point it intercepts the x-axis, the function clips the x-axis, for x equal minus 1 over 2. So for the original function, you have minus 1 over 2, 0, and the y-intercept is 0, 1. So for the inverse function, you would have the inverse for that. Okay, point correspondence here is 1, 3, so this becomes 3, 1. The coordinates are also interchanged. For instance, let's say you have a point 4, 10. The corresponding point on the inverse becomes 10, 4. You swap the coordinates. Exponential and logarithmic functions. F of x is equal to ex. The inverse for the exponential function, by the way, which is defined from minus infinity to plus infinity, with y equals 0 being the asymptote, and it clips the y-axis at x equals 0, meaning that e0 is equal to 1. Its inverse is the log x, which is, as we mentioned, so the asymptote which was horizontal becomes the vertical asymptote, or x equals 0 for the logarithmic function. And here you have a characteristic point which is 0, 1. it becomes 1, 0 for logarithm, meaning that for x equal 1, y equals 0, the asymptote becomes a vertical asymptote, and the logarithm stretches from minus infinity, it goes up, clips the x-axis at x equal 1, so for x equal 1, y equals 0, and then goes to plus infinity, and both of them are symmetric in respect of the line y equal x. So f minus 1 of x equal ln x. This is the reciprocal or inverse function for f of x is equal to ex. For the power function, f of x is equal to x to the power of 3, for example, the inverse is not square root, the third root of x. Okay? So it becomes f minus 1 of x is equal to the third root of x. For the quadratic function, such as f of x is equal to x squared, we know that it's not one-to-one on all real numbers, meaning that for both negative and positive x values, you would have the same height, the same y value. So the function is already symmetric in respect of the y-axis. Hence, to get its inverse, we need to consider the function to simplify the plotting, actually. We need to consider the function only from 0 on, okay? From x equals 0 all the way to x going to infinity, okay, for all positive values of x. So, and this is how you get the inverse. This is y equal x squared, correct? This is y equal x. Actually, no, y equal x is on top of it, okay? So normally, the inverse should be symmetric in respect of the x-axis like this, right? So let's check it out, okay. Y equal x squared, we interchange x and y. So x is equal to y squared. Y equals square root of x. And this is the inverse function. Find the inverse of f of x is equal to x to the power of 3. Solution, y equal x to the power of 3. Interchangeable variables. So we replace y with x and x with y. Hence, y is equal to the third root of x, and this is the inverse function. Applications of inverse functions. Inverse functions appear in many scientific and engineering applications. For example, temperature conversion, Celsius to Fahrenheit, F equal 9 over 5, C plus 32, then C equal 5 over 9, F minus 32. Distance time problems. If position is expressed as a function of time, an inverse may determine the time at which a given position occurs. Exponential growth, population model, for example, P equal P0, E to the power of kt, E being the exponential. Using logarithms, the inverse relationship allows us to solve for time. So, T is equal to 1 over k ln P over P0. Actually, this is how this one is solved. So, first, let's divide by P0. Yeah, we transferred P0 from right to left. So you divide it by, okay, you divide P by P0 equal E kt. Then we place a logarithm behind each one of these two components. So ln P over P0 is equal to ln E to the power of kt. Now, ln E to the power of B, let's say, is equal to B. So ln E to the power of kt is equal to kt. Hence, kt is equal ln P divided by P0. So T equal 1 over k times ln P divided by P0. Okay? And if I want to expand even more than that, T is equal to 1 over k times ln P minus ln P0. Because ln A divided by B is equal to ln A minus ln B. The temperature is 95 degrees Fahrenheit converted to Celsius. So C is equal to 5 over 9 times f minus 32, so we inverted everything. It becomes 5 times 95 divided by 9, 5 over 9 times 95 minus 32, 63 times 5 over 9, which is 35 degrees Celsius. Comprehensive exercises. Okay, so let f of x be equal to x plus 2 and g of x is equal to x squared. F g of x is equal to, you place instead of x, x squared. Okay, replacing x with g of x, which is x squared plus 2. G of f of x, okay, so this is fg. G of f is equal to x plus 2, we replace it down in x squared, so it is x plus 2 squared equal x squared plus 4x plus 4, which is different than fg. So f not gx is different than g not fx. And this is the solution. fgx is equal to x squared plus 2. gfx is equal to x squared plus 4x plus 4. Find the inverse of f of x equal 5x plus 10. So y equal 5x plus 10. We swap x and y. So x equal 5y plus 10. 5y equal x minus 10. So y equal x minus 10 divided by 5, which is f minus 1 of x. Determine whether f of x is equal to x to the power of 4 is 1 to 1 on all real numbers. Definitely not. Here's why. f2 and f minus 2 both are equal to 16, so it's not 1 to 1. Or in other words, it's not an injective function. So at the end, in this module, we learned the following: how to form composite functions, determining domains of compositions, definition of one-to-one functions, horizontal line test, inverse functions, geometric relationship between the function and its inverse pairs such as exponential ex and logarithmic functions, and real-world applications of inverse functions. Function composition and inverse functions form the foundation for advanced topics in calculus, differential equations, mathematical modeling, and higher analysis. Understanding these concepts is essential for solving complex mathematical problems, interpreting relationships between variables. 5. Exponential and logarithmic functions. Exponential and logarithmic functions are among the most important functions in calculus, science, engineering, economics, biology, and data science. They are very common and their applications really diverse. Exponential functions describe growth and decay processes, while logarithmic functions provide a way to reverse the exponential relationships. Applications include population growth, radioactive decay, compound interest, signal processing, machine learning, chemical reactions, heat transfer, epidemiology. And in this module, we will study exponential functions, log functions, their properties, graphs, equations, and applications. First, the exponential function has the following form. F of x is equal to a times b to the power of x. A should be different than 0, b greater than 0, right? And different than 1. And x would be a variable or an exponent. The variable appears in the exponent, okay? For instance, f of x is equal to the power of x, or f of x is equal to 5 times 3 to the power of x, where a equal 5 and b equal 3, or 10 times 1 half x, where 10 being a and b equal 1 half. And this is the exponent in the power of the 1 half. Basic properties. F of x is equal to b to the power of x, with b greater than 1. Domain, it's defined from minus infinity to plus infinity. Remember, for ex, as we mentioned, its graph goes like this. First, y equal 0, which is the x-axis being the horizontal asymptote, and the function extends from minus infinity all the way to plus infinity with e0 equal 1, meaning that it clips the y-axis at x equal 0 on y equal 1, okay, at a height of y equal 1. Domain of definition from minus infinity all the way to plus infinity. Range from 0 to infinity, meaning that the value of y is from 0 plus, which is, it's always positive, okay? It has a value above, right above the x-axis all the way to plus infinity. Horizontal asymptote, y equals 0. Y-intercept is 0, 1. As we mentioned, e0 equal 1, or in other words, for x equal 0, y equal 1. This is the horizontal, okay, this is the y-intercept, and the horizontal asymptote is y equals 0. And it is an increasing function, always going up. Example, evaluate f of x is equal to the power of x at x equals 3. Okay, so this is f of 3 equal 2 to the power of x equals 3, x being 3, equal 2 to the power of 3, which is 8. Evaluate f of x is equal to 3 to the power of x, with x equal 4. So this is simply 3 to the power of 4, which is 81. Exponential growth models. Many natural processes grow proportionally to their current size. The general model is given by p of t is equal to p0, which is the initial quantity, times b to the power of t. b is the growth factor, and t is the time, just like the half-life decay for radioactive materials, by the way, so close to that formula. As an example, a population starts at 1,000 and doubles every year. So the model becomes p of t is equal to 1,000 multiplied by 2, okay? Why? Because it is double, to the power of t, which is the time. So after 3 years, it becomes 1,000 multiplied by 2 to the power of 3 equal to 8,000. An investment grows according to the formula a of t is equal to 5,000, 1.1 to the power of t. Find the amount after 4 years. So 40 equal 4. Let's get the amount. It is 5,000 multiplied by 1.1 to the power of 4, which is 5,000 times 1.4641, or around 7,320 US dollars, 0.5 of course. Exponential decay occurs when a quantity decreases proportionally to its current value. In such case, the exponential is a value between 0 and 1. This is how it decays. So p of t is equal to p0, the original or initial quantity, multiplied by b, a value such as 0.003, for example. It is less than 1, greater than 0, to the power of t, which is the time factor. Example, the radioactive material, as we mentioned before. So p of t is equal to 100 multiplied by 1 over 2, which is the half-life, by the way, meaning that at each cycle for that half-life, or this is the time for which half of the material would decay. Half of the mass of the radioactive product would decay. This is what we mean by half-life. So p of t is equal to 100 times 1/2 to the power of t. After 4 years, it is 100 divided by 16. Why? Because 1/2 to the power of 4, meaning 1 over 2 to the power of 4, or 1 over 16, which gives us 6.25. A substance follows the law 200 times 0.8 to the power of t. Find the amount after 5 time units. So again, also here, the amount is decreasing. Solution, p of 5 is equal to 200 times 0.8 to the power of 5. And you evaluate it, you get 65.54. So look at how much the mass had depleted. way more than 50%. The most important exponential function is e of x, where e is approximately equal to 2.718281828, which is Euler's number. The domain for e of x, as we mentioned before, is between minus infinity to plus infinity, with y equals 0, or the x-axis in other words, being a horizontal asymptote. This is why the function starts right after y equals 0, so from 0 plus, and it grows to infinity while passing with x equals 0 at a height of 1, meaning that e0 is equal to 1. So the range is 0 to infinity, 0 being excluded, by the way. So 0, it's not part of the value. Okay, so the function remains strictly above y equal 0. The derivative for ex gives us ex. As for the integral, also gives us ex plus c. And also derivative for e to x, let's say you have e to x, it gives you 2e to x, which is u prime times eu. This is the chain rule. As for the integral of e to x or e3x, whatever, is equal to 1/2 multiplied by e to x plus c. Evaluate e squared. Now e is approximately equal to 2.71 something, so e squared is equal 7.389. Evaluate e to the power of minus 1, which is 1 over e, 1 over 2.713 something, approximately equal to 0.3679. Logarithmic functions. A logarithm is the inverse of an exponential function. Definition: y equal log base b of x. So, okay, so how do you get the value for x, for example, or for y? Okay, so b to the power of y is equal to x. This is how you get them from each other. Okay? Now, again, so it's like y equal ln e x. So, y equal x ln e. Now, ln e is equal to 1, by the way. So, y is equal to x. Anyway, okay, this is how you get them from each other. Example, log base 2 of 8 equal to 3. So, you simply do, okay, 2 to the power of 3 is equal to 8. Actually, this is how we solve it. You elevate both the left side and the right side, okay, as a power of 2. So you place 2 log base 2 of 8 is equal to the power of 3. Now, 2 log base of 2 of 8 is equal to 8. Just like, for example, e ln to the power of ex becomes x. Okay? Hence, 2 log base 2 of 8 becomes 8 equal to the power of 3. Correct? Log base 10 of 1000 becomes also, this is also equal to 3. And here's how you evaluate it. It is 10 to the power of log base 10 of 1000 equal 10 to the power of 3, right? So 10 log base 10 of 1000, this is 1000 equal 10 to the power of 3. Hence, this value here is 3. 1000 is equal to 3. Let me clarify this part a little bit more. So, at first, log base 10 of 10 is equal to 1. Take that as a first and very important note. So, log base 10 of 10 is equal to 1. Now, log base 10 of 1000 is simply equal to log base 10. What is 1000? It is 10 to the power of 3. 3 can be multiplied behind the log, okay? Because ln a to the power of b is equal to b ln a. So this becomes equal to 3 log base 10 of 10. Again, what is log base 10 of 10? 1. So it is equal to 3 times 1, which is 3. I hope it's clear. Another example for that, so let's say log base 10 of 10,000. It is equal to log base 10 of, what is 10,000? It is 10 to the power of 4. So 4 can be multiplied behind the log. It is 4 log base 10 of 10, which is 1. Hence, the answer for that is equal to 4. The inverse of e of x is ln x. So e ln x, exponential of the ln x is equal to x. Correct? Just like we said that 10 to the power of log base 10 of something, of n, for example, becomes n. Okay? So in the same way, e to the power of ln x becomes x. ln ex is equal to x also. Why is that? Because it becomes x times ln e. By the way, ln e is equal to 1. This is due to the fact that when you graph the logarithm, for x equal 1 exactly, the ln function becomes equal to 1 also in height. Okay? Log base 2, 32. Okay. See how simple and easy it is. Log base 2 of 32 is equal to log base 2 of 2 to the power of 5. This is what 32 gives us, okay? So 5 can be multiplied behind the log. You end up with 5 log base 2 of 2. Log base 2 of 2 is equal to 1, so equal to 5. Log base 2 of 32 equal 5. Evaluate ln e4. So it is 4 times ln e, okay? 4 is removed to the behind of the logarithm. It is equal to 4 ln e. ln e is equal to 1, hence equal to 4. Properties of logarithms. The logarithmic laws follow from exponential laws. Log base b of mn is equal to log base b of m plus log base b of n. So the logarithm of the product is equal to the sum of the logarithms. Log base b of m divided by n is equal to log base b of m minus log n. Power rule, log b of m to the power of k is equal to k log b of m. This is the one we used moments ago. And change of base formula, so log b of x is equal to ln x divided by ln b. This is also important. So log base b of x is equal to ln x divided by ln b. Simplify log of x to the power of 3 times y. First of all, this is a product on the inside, so it becomes log x to the power of 3 plus log y. Equal, 3 can be removed to the behind of the log, so it is 3 log x plus log y. Expand ln x squared divided by y. ln a over b is equal to ln a minus ln b. So it is ln x squared minus ln y. Then 2 here can be multiplied behind the logarithm, so equal to 2 ln x minus ln y. Solving exponential equations, same base. Okay, so 2 to the power of x plus 1 is equal to 2 to the power of 5. How do we solve it? Equate components, but let's go a little bit deeper than that. If we place logarithm behind each of the two sides from left to the right, okay? So it is ln2 to the power of x plus 1 is equal to ln2 to the power of 5. So x plus 1, since it is the power here, times ln2 equal 5 times ln2. You can factor out ln2 or divide by ln2 both sides. So we end up with x plus 1 equal to 5. Hence, x is equal to 5 minus 1 or 4. Another example, 3 to the power of x equal 20. So we take the logarithms. ln 3 to the power of x is equal to ln 20. Okay. So ln 3 to the power of x becomes x ln 3 equal ln 20. So x is equal to ln 20 divided by ln 3, which can be also written, actually no, that would be ln 20 over 3, which is not the case here. Pay attention. So it is equal to ln 20 divided by ln 3. Each one is a distinct logarithm. So x approximately equal 2.727. You need the calculator to get that. Solve 5 to the power of x is equal to 125. Okay, so if we place ln 5 to the power of x is equal to, what is 125 by the way? It is ln 5 to the power of 525 times 5 to the power of 3, right? To the power of 3. So this reduces into x ln 5 is equal to 3 ln 5. You divide by ln 5 both sides, and we end up with x equal 3. Solve ex equal 10. Take natural logarithms, ln ex. Okay, so simply ln ex is equal to ln 10. ln ex is x to the power of ln e, which we know is equal to 1, equal ln 10. Hence, x is equal to ln 10, and you evaluate it using the calculator. It becomes approximately, it's equal, approximately 2.303. Solve log base 2 of x equal to 4. We simply raise them as powers of 2, with 2 being the exponential, the exponent. So 2 to the power of log base 2 of x is equal to the power of 4. 2 log base 2 of x is simply equal to x, equal to the power of 4. Hence, x is equal to 16. ln x equal to 3. How to solve that? You place them both as exponents of the exponential. So e ln x is equal to e to the power of 3. E ln x is equal to x. So hence, x is equal to e to the power of 3, approximately 20.086. Solve log base 3 of x is equal to. Solution. Okay, so since we're talking about log base 3, we need to elevate both sides to as powers of 3. So 3 log base 3 of x is equal to 3 to the power of 2. Hence, x is equal 3 squared equal 9. Solve ln x equal 5. So e ln x is equal to e5. Hence, x is equal to e5 or 148.413. The compound interest formula. I think the bank interest, something like that. Yeah. A equal P times 1 plus R over N to the power of NT. P being the principal, R the annual interest rate, N compounding frequency, and T being the time. Let's say we invested $1,000 at 5% compounded annually for 3 years. So A is equal to 1,000 multiplied by 1 plus r over nt, something like that. Yeah, over n, which is 1.05 to the power of 3. Okay, you apply the equation, the formula that we've seen in the previous slide, to the power of 3, approximately $1,157.63. 13. Find the future value of $2,000 invested at 8%. For 2 years compounded annually, being the time interval. So solution is A equal 2,000 multiplied by 1 plus r over n, okay, 1.08, which is the 8%, okay, plus 1 to the power of 2 years, okay? So this is 1 plus 8%, 1 plus 0, 8, to the power of 2, equal $2,332.8. For continuous growth, A would have a formula equal to P ERT. For decay, A would be equal to P times E to the power of minus RT. A population starts at 500 and grows continuously at 4% per year. The model is P of t is equal to 500, if it's going exponentially, times e to the power of 4%, 0.04, times t, with t being the number of years. It can be 1.3 years also. So it's not necessarily a natural number, a natural value. Find the value after 10. So P of 10 is equal to 500 times e to the power of 10 multiplied by 0.04, which is e to the power of 0.4, approximately 745.9, okay, as a value. Some review questions. So log base 10 of 10,000, this is 10 to the power of 4. We've seen that before, okay? So it becomes 4 log base 10 of 10 equal 4. Simplify ln a 5b2, it is equal to ln a squared plus ln b, ln a 5 rather, plus ln b squared equal 5 ln a plus 2 ln b. Solve 2 to the power of x equal 64. By the way, 64 is 2 to the power of 6. So x is equal to 6. As simple as that. 2 to the power of x is equal to 2 to the power of 6. X equal 6. Solve ln x equal to, okay, we elevate through the exponential. E ln x is equal to e to the power of 2. Hence, x multiplied by e ln, okay, so x equal e squared, approximately 7.389. So in this module, we studied exponential functions and their graphs, growth models, decay models, exponential function ex, logarithmic functions and their inverses, properties and laws of logs, solving exponential equations, logarithmic equations, interest applications, continuous growth, and decay models. Exponential and logarithmic functions form one of the most important function families in calculus. They provide mathematical models for growth, decay, finance, population, dynamics, physics, engineering systems, and many natural phenomena. Their inverse relationship makes them indispensable tools for solving equations and analyzing real-world processes. Module 6, Trigonometric Functions. Trigonometric functions are fundamental tools in mathematics, physics, engineering, signal processing, astronomy, and other disciplines. Originally developed to study triangles, but they now play a central role in modeling periodic phenomena such as waves, oscillations, rotations, alternating currents, sound, and light. The 6 basic trigonometric functions are sine x, cosine x, tan, cosecant, secant, and cotan. In calculus, trigonometric functions are especially important because they are continuous, differentiable, periodic, and naturally arise in many physical systems. The unit circle review. Unit circle is a circle centered at the origin with radius 1. So r equal 1, equation x squared plus y squared equal to 1. For theta, an angle, the coordinates of a point on the unit circle are cosine theta and sine theta. So this is the cosine axis, which is the x-axis. The sine axis is the y-axis. So x, the coordinate of a point, okay, which is x here. Remember, cosine theta is equal to the adjacent segment, which is x, divided by r, correct? R being the radius, which is 1, okay? So x is equal to cosine theta in such case if r is equal to 1, y equal r sine theta for r equal to 1 also, and tan theta is sine theta divided by cosine theta. Given that tan theta is equal to the opposing segment divided by the adjacent segment, or y divided by x, with y equal r sine theta, x equal r cosine theta. So in both cases r factors out, so what remains is tan theta equal y over x equal sine theta divided by cosine theta. Important unit circle values. For theta equals 0, sine theta is equal to 0. Why? Because there's no elevation. The sine, okay, which is the elevation, would be 0. But cosine theta would be equal to 1. Why? Because it coincides with the actual radius for the unitary circle. For pi over 6, which is 30 degrees, sine theta would be 1/2, and cosine theta, which is this one, would be equal to square root of 3 divided by 2. For pi over 4, which is 45 degrees from the x-axis, sine theta would be equal to cosine theta because it's dividing the actual first quadrant in half. So x would be equal to y, or actually, yeah, sine theta would be equal to cosine theta equal square root of 2 divided by 2. For pi over 3, which is 60 degrees, here you get an inversion, meaning that sine becomes equal to 1/2. It is the cosine that becomes equal to 1/2, and sine becomes equal, which is the elevation, square root of 3 divided by 2. So it is just like pi over 6, except the values of sine and cosine are flipped. You interchange them. For pi over 2, meaning 90 degrees, the angle in such case would give you a sine equal to 1, equal to the actual radius, and cosine would be equal to 0. Why? Because the projection of the point to the x-axis would be equal to 0 in such case. So find sine of pi over 6. Pi over 6 is equal to 30 degrees. That would be 1/2. Also, cosine pi over 3, that would be 60 degrees. So in such case, the cosine would be the 1/2, not the sine. The sine in such case would be equal to square root of 3 divided by 2. So you need to kind of imagine it based on the elevation of the angle. So if it's 60 degrees, the sine would be half, half of the square root of 3, or square root of 3 divided by 2. And the cosine would be equal to 1/2, meaning half the distance of the radius of the unitary circle. Let's talk about the sine function. Y equals sine x is defined between minus infinity to plus infinity. So whatever x is, you'd always have a value for y being equal to sine x. Okay, so it doesn't matter. Even if it goes beyond the 2 pi, the 360 degrees, it's like it keeps rotating, but you would get a reproduction of the same values for the sine. Now, the range for the sine itself is -1 as a minimum, -1 being included, and +1. So it oscillates or changes between -1 and +1. The same thing, by the way, is for the cosine. The period is 2 pi, meaning that sine 0 is equal to 0, then at pi over 2 it's equal to 1, then it goes back to 0 at pi, then goes downwards to 3 pi over 2. At 3 pi over 2 it goes downward to minus 1, then it goes back to 0. Period 2 pi. Now sine minus x is equal to minus sine x, meaning that it is an odd function. So in other words, it is proportional or symmetric in respect of the origin of the axis. It is an odd function. Okay. Imported values: sine 0 equals 0, sine pi over 2 equal 1, sine of 3 pi over 2 is equal to minus 1, which is can also be written as sine of minus pi over 2. So on the unitary circle, this would be here. Actually, for pi over 2, 90 degrees. Yeah, that would be sine pi minus pi over 2. Minus pi over 2 is equivalent to 3 pi over 2, by the way, except we are rotating from this direction instead of rotating from this direction. Since we're going against the trigonometric sense, which is, by the way, anti-clockwise, so it is minus pi over 2, and here for minus pi over 2 the sign would be minus 1 since it is below the x-axis. Evaluate sine pi. Sine pi is equal to 0 because it is actually, yeah, just like 0 degrees, but from the other side. So it is the 180 degrees. It has a 0 degree with the x-axis, but away 180 degrees from the origin. Sine 3 pi over 2 is equal to sine minus pi over 2, which is equal to minus 1. Cosine function is so similar to the sine function. The domain is from minus infinity to plus infinity. It varies between minus 1 to plus 1. Why? Because just like sine starts from 0. It has a peak of plus 1 and a trough of minus 1. But it cannot go beyond that range, either above plus 1 or beneath minus 1. These are respectively the maximum and the minimum, the upper bound and lower bound. And by the way, the range is minus 1 plus 1 as a closed set, meaning that minus 1 and plus 1 are both parts of the set. Okay, so they are values, actual values that belong to the function also. It's not like a barrier, like an asymptote. No, these are actually also among the acceptable values for cosine and also for the sine. Period 2 pi. Now, cosine is an even function, meaning that it's symmetric in respect of the y-axis. Now, cosine 0 is 1. Cosine minus x is equal to cosine plus x, so it has this form, like this. Notice it's symmetric in respect of the y-axis. Cosine 0 is equal to 1. Okay, cosine pi over 2 and minus pi over 2 is equal to 0. You see the symmetry? Cosine pi over 2 equals 0. Cosine pi equal minus 1 because that would be here on the other side. This is cosine pi. Cosine 0 is the one on this side, which be equal to plus 1. So cosine pi minus 1. Why? Because it is on the negative side of the x-axis. This is the y here. Cosine 2 pi. What is 2 pi? This is pi, and this is another plus pi. 2 pi returns you back to the angle 0. So it gives you plus 1. Evaluate cosine pi. Cosine pi is equal to minus 1. Cosine 2 pi, just like cosine 0, is equal to plus 1. The tangent function is defined by tan x is equal to sine x divided by cosine x. So, provided that cosine x should be different than 0. Why? Because you cannot divide by 0. The function blows up to infinity. It's forbidden. So, for which values of x cosine avoids being 0? X can be everywhere except for any value that is either equal to pi over 2 or a multiple of pi that renders you back to the pi over 2. This is what I mean by that. So it should be different than pi over 2 plus k pi. What do we mean by that? So for k equals 0, you end up with pi over 2. Okay, so this is the first pi over 2. Cosine here becomes 0. So this renders this equation infinity. Sine, right? Sine of pi over 2 is 1 divided by 0. It blows up. Now, what is k? Okay, so k, what can it be? For whatever k being a natural number. So for k equal 1, okay, this is pi, because k pi becomes pi, plus pi over 2, we get back to another angle, which is 90 degrees, that would render cosine 0. For k equal 2, okay, so this is 1 pi, this is another pi, this is 2 pi, we are back to the first quadrant, okay, plus pi over 2, so you are back with, or at 90 degrees in the first quadrant for a sign that is positive 1, but the cosine becomes 0. So x is defined for whatever value that is different than pi over 2 plus any multiple of pi. The range is, what is the range? Now, the range for the tangent itself is between minus infinity to plus infinity. How is that? Because as cosine becomes small, right? Remember, the limit of a number divided by a small number approaching 0 becomes infinity. So hence the range becomes from minus infinity to plus infinity. Now the minus values are when you are dividing by minus 1, you are dividing 0, but in the numerator you have a negative value. So minus 1, limit minus 1 divided by 0, it would give you minus infinity. Now, that would be a forbidden value, but let's say it is 0 point something, okay, it won't blow up completely. It would give you, however, a very large number. The period for tan is pi, meaning it completes 1 full cycle for x equal pi, and it is an odd function, meaning that it's always symmetric in respect of the y-axis. So tan minus x is equal to minus tan x. Important values, tan 0 equals 0. Why? Because it is sine 0 divided by cosine 0, which is 1. 0 divided by 1. Tan pi over 4, given that cosine pi over 4 is equal to sine pi over 4, which is 45 degrees, equal square root of 2 divided by 2. Hence, the tangent is equal to 1. And tan 3 pi over 4, which is the inverse, okay, meaning that it would be pi over 4 from beneath, where the sine would be negative and the cosine positive. So the same value, except the sine would be negative, so it would give you minus 1. Evaluate tan pi over 4. Solution, okay, so tan pi over 4 is equal to sine pi over 4 divided by cosine of pi over 4, which is sine 45 degrees divided by cosine 45 degrees, or square root of 2 divided by 2 divided by square root of 2 divided by 2. It's the same value for both sine and cosine, hence the tangent is equal to 1. 8. Determine whether tan pi over 2 exists. Okay, so tan pi over 2 is equal to sine pi over 2 divided by cosine pi over 2. This is 1 divided by 0, so it doesn't exist. It is undefined, okay? Why? Because 1 over 2 blows up to infinity, so the value does not exist. You're dividing by 0, remember. Fundamental trigonometric identities. Okay, now remember, again, x is equal, in the unit circle, x is equal to cosine theta, y is equal to sine theta. R square, okay, so the radius, which is 1 square, okay, this is the Pythagorean rule. The hypotenuse square is equal to x square plus y square. The first segment square plus the second segment square, which is, okay, if you replace the values, so x is equal to cosine theta and y is equal to sine theta. This is due to the fact that we're dealing with a unit circle, because remember, x is equal to r cosine theta, y equal to r sine theta. But r is equal to 1 in a unit circle. Hence, x squared plus y squared is equal to 1 gives us sine square x plus cosine square x, or cosine square x plus sine square x is equal to 1. This is the first identity. Other forms, 1 plus tan square x is equal to secant square x. 1 plus cotan square x is equal to cosecant square x. Here we have to memorize these main identities so that we can work with them. Given that sine x is equal to 3 divided by 5 and x is in quadrant 1, find cosine x. So how do we solve that? As simple as it is. So remember, cosine square x plus sine square x is equal to 1. So sine square x is simply 3 divided by 5 squared plus cosine square x is equal to 1. Hence, cosine square x is equal to 1 minus 9 divided by 25, which is 16 divided by 25. So cosine x is the square root of 16 divided by 25 equal 4 divided by 5. Inverse trigonometric functions reverse the trigonometric functions. So y is equal to sine minus 1x. This gives us the angle instead of the sine itself. So y is the angle within. Okay? And can be written as, so y equals sine minus 1 of x equal to arc sin of x. Okay? Means that sin y is equal to x. Okay? So the sine of this angle is what gives us the x value. The domain is between minus 1 and plus 1 for the sine range from, meaning that the domain, it is defined between minus 1 and plus 1 for the x value. The range, it varies from minus pi over 2 to plus pi over 2. As for y equal r cosine x, the domain is between minus 1 and plus 1. What does it mean? It means that the maximum, here's the thing. You see, the value of the cosine changes from minus 1 to plus 1. This becomes the domain when you get the inverse instead of the range. So you interchange the range and the domain. As for the range of the values that we can get is between 0 and pi, correct? So the angle is between 0 and pi. Y equal arctan of x. Now tangent is between minus infinity and plus infinity, right? Because when you are dividing by a small number, for example, a very small angle close to 0, you can get actually, plus infinity or minus infinity. The range is from minus pi over 2 to plus pi over 2. The range of the values for the arctan. In other words, it's the angle, for which the tangent can give us minus infinity to plus infinity as values. Exercise 10. Evaluate arcsin of 1/2. Meaning that for which angle we get a sine value of 1/2. That would be plus pi over 6. Remember? Sin pi over 6, which is 30 degrees. Always remember. Sin 30 degrees give us 1/2. So the angle is pi over 6. Hence, arcsin of 1 over 2 is equal to pi divided by 6. Evaluate arctan of 1. So arctan of 1 meaning that for which angle you have a tangent of 1. Since tan of theta is equal to sin theta divided by cosine theta, you need the angle for which sine and cosine are equal, which is no other than pi over 4. So arctan 1 is equal to pi over 4. Periodicity. A function is periodic if it reproduces itself, meaning that fx plus t, with t being a positive constant or the value of the period, is equal to f of x. So after a period t, which is a constant value, the function reproduces itself, meaning that it has a replication effect. It becomes a clone of its shifted version that is located at or behind the period, okay, that we mentioned, behind t, meaning that before the shifting toward the t period, the function is the same clone or copy of the function after t. So it copies or replicates itself. Examples. For sine, sin x plus 2 pi is equal to sin x. Why? Why is that? Because after 2 pi you have completed an entire cycle. So the function repeats itself. Okay, graphically, and this is the period, 2 pi by the way. Graphically, this is how it looks like. 0, pi, at pi over 2 it becomes 1, pi becomes 0, 3 pi over 2 becomes minus 1, and 2 pi becomes 0. After 2 pi, it becomes the same function except it is shifted to the right 2 pi. So the shifting is 2 pi towards the right. That's the thing with shifting, with periodicity. And the period, of course, for sine and cosine is 2 pi. Same concept for cosine. So cosine x plus 2 pi is equal to cosine x, period 2 pi. For tangent, tan x plus pi is equal to tan x. The periodicity or the period is pi, not 2 pi. Now for cosine, by the way, this is what cosine looks like. So cosine 0 is equal to 1. So it starts shifted pi over 2 to the to the left, then it repeats itself after 2 pi. This is one full cycle. Find the period of y equal sin 3x. Formula, t is equal to pi divided by b, which is the multiplicator here in absolute value, which is 2 pi divided by 3, and hence this is the period for the sin function. General sine function, y equal a sine bx minus c plus d. General cosine function, a, which is by the way the amplitude of the function, cosine bx minus c, okay, so c is the phase, b is the pulsation, okay, plus d, which is the shifting. Again, a is the amplitude, meaning, let's say, if this is sine x and a equal 4, that would be the new sine x. So the amplitude would be higher, okay, 3 degrees higher than the first one. 3 like scales higher, not degrees in that sense. Now, as for b, okay, so for b, you can get from it the t value, okay, which is the period, and c, okay, so a times sine bx plus c. C is the phase shift. C actually over b, this is the phase shift value. C alone is the phase, C over b is the phase shift. S for d is the vertical shift. So let's say you have a function sine x like this. If d is equal to, so this function would be shifted 2 locations above, and it becomes like this, shifted 2 scales above the x-axis. This is the vertical shift. Let's analyze y equals 3 sine 2x minus pi plus 1. First of all, the amplitude is 3. The period is t equal 2 pi over b in absolute value. So 2 pi over 2, which is pi. Right? This is the period. Phase shift is equal to c over b equal an absolute value. So it is pi divided by 2. This is the phase shift. And as for the vertical shift, it is plus 1. So let's try to plot it. Given that the period is pi, so you have, instead of 2 pi, this would conclude in 1 pi as a full cycle. However, let me correct something. Okay, before plotting it, so it is the first cycle or the full cycle is at 1 pi, not 2 pi. More than that, So period again is equal to 1 pi. You have an upward vertical shift of +1, so it should start at y equal 1 instead of at y equals 0 on the x-axis. More than that, you have a shift of pi over 2, so shifted pi over 2. Okay. This means that it starts at pi over 2 instead of at x equals 0, okay? So pi over 2, this is where it starts, and it is a sine. Okay, so this is how it's plotted, okay? Find the amplitude and period of y equal 5 cosine 4x. First, the amplitude is 5, and the period is 2 pi divided by 4, which is b. Okay, t equal 2 pi divided by b in absolute value, 2 pi over 4 equal pi over 2. So in pi over 2, let's say this is pi, this is 2 pi, okay? The original function, an original cosine function, starts from here, okay, and over pi it becomes cosine pi, cosine pi becomes -1, then this is like the function becomes like this, actually. I assume I kind of lost. Okay, so basically, let's work immediately on 5 cosine 4x. The amplitude is 5, meaning that 3, 4, 5, the height of the peak is 5. It starts from here. And the period is pi over 2. So let's say this is pi and this is pi over 2. So the full cycle completes at pi over 2. Full cycle, a full period completes at pi over 2. So you see it is compressed. Remember the compression, right? Applications of trigonometric functions. Wave motion, sound waves and electromagnetic waves both are modeled by y equal a sine omega t, with a is the amplitude of the sine wave and omega is the angular velocity given by 2 pi divided by t, okay? Or 2 pi times f, with f being the frequency, because as you know, f is equal to 1 divided by t. It is the inverse, the frequency is the inverse of the period. Alternating current, also electrical current, I of t is equal to I0, which is the original value, so to speak, multiplied by, or the peak value, the amplitude rather, not the original, multiplied by sine omega t, with omega again equal to pi divided by t, and t being the period of the function. Also, for a rotational motion, the model is x equal r cosine t, y equal r sine t, like tracing the movement of a planet orbiting the sun, for example, based on Kepler's law. This is how you can model it as an equation. In this equation, for a wave modeling given by y equal to sine 3t, find its amplitude and period. Okay, amplitude is simply the value multiplying sine, which is 2. As for the period, remember the period is equal to pi divided by absolute value of b, which is the multiplier of t, equal to pi divided by 3. Hence, this is the period of this function. Comprehensive review exercises. Sine pi over 4 is equal to square root of 2 divided by 2, equal cosine pi over 4, by the way. Cosine pi over 6, which is, in such case, it would be, again, this is the 30 degrees angle. Remember, sine 30 degrees is 1/2. Hence, cosine, in such case, would be bigger. It would be square root of 3 divided by 2. So imagine it, and as a rule of thumb, sine of 30 degrees is 1/2. So the cosine would be the exact, like bigger, which is square root of 3 divided by 2. As for the 60 degrees, you flip them. Why? Because In such case, at 60 degrees, the 30 degrees becomes here. So this, it is the cosine that becomes 1/2. As for the sine becomes square root of 3 divided by 2. Verify the identity sine squared x plus cosine squared x equal 1 for x equal pi divided by 3. Okay, so it is sine pi 3 squared plus cosine pi 3 squared equal sine pi 3 pi over 3 squared, it is square root of 3 divided by 2 squared plus 1/2 squared equal 3 over 4 plus 1 over 4 equal to 1. Hence, it is verified. Solve sine x is equal to square root of 3 divided by 2 for x between 0 and 2 pi. Okay, so for which values of x the sine becomes square root of 3 divided by 2? It is for 60 degrees or angle pi over 3, that's the first one, but also you have pi over 2 plus pi over 6, which is here. Okay, so pi over 2, 90 degrees plus 30 degrees. So it is either the 30 degrees from here, which is pi over 3, if you start evaluating it from the x-axis, and pi over 2 plus pi over 6, which is 30 degrees on the next side. So pi over 2 plus pi over 6 equal 3, okay, 6 over 2, 3 pi plus pi over 6. Okay, so 3 pi plus 4 pi over 6, which is 4 pi over 6 or 2 pi divided by 3. So these are the two angles for which sine is equal to square root of 3 divided by 2. Finally, at the end, in this module, we studied the unit circle and angle measurement, sine, cosine, and tangent functions, fundamental trig identities, trigonometric functions, inverse trigonometric functions, periodic behavior, amplitude, period, phase shift, graph analysis of trigonometric functions, applications to wave, oscillations, and circular motion. Trig functions provide the mathematical language for describing periodic phenomena such as the orbit of a planet around the sun or a meteor in the Kuiper belt, so to speak. Their importance extends throughout calculus, differential equations, Fourier analysis, physics, engineering, signal processing, and modern scientific computing. Module 7, Limits and Function Behavior. Limits are the foundation of calculus. They provide a rigorous way to describe the behavior of a function as the input approaches a particular value, especially critical values such as in the case of asymptotes. The concepts of continuity, derivatives, and integrals all rely on limits. In this module, we study intuitive meaning of limits, numerical and graphical approaches to limits, one-sided limits, infinite limits, limits at infinity, algebra of limits, and indeterminate forms. Introduction to limits. Suppose a function f of x is defined near a point A. So let's say this is a function f of x, such as a curve, and this is x is equal to a. So as x approaches a, as x approaches this value, the function f of x approaches a limit or a height which is L. This is called the limit L. So limit f of x as x approaches a is equal to L. So as x gets arbitrarily close to a, the values of f of x get arbitrarily close to L. Importantly, x is approaching a, f of x approaches L. So the value of f of a may or may not exist. It may not necessarily be equal to L. Okay? So the limit is L, but it's not always necessarily that f of a is equal to L and that L exists within the function. Okay? So the function is approaching that limit, but it's not necessarily a value. Now, if the limit exists to the left and to the right, and it's equal to f of a, equal to a value, then the function would be continuous at x equal a. As an example for that, so let's say you have a function f of x, this is the function, and this is a height or an altitude L, a limit L. So the function might be approaching L, but not necessarily getting to L. More than that, to the right at x equal a, for example, okay, the function might have a completely different value, such as -3, for example. So there's no limit to the right. Only the limit is to the left, for example. Okay? And as you notice, the function is not continuous. And here is the criteria for continuity. For a function to be continuous at x equal a, limit f of x as x approaches a minus, meaning that as x approaches a from the left, should be equal to the limit f of x as x approaches the right of a, equal to f of a, okay, meaning equal to the value of f as x equal a. So these three should meet together, should be equal together, and this criteria should be met for the function to be continuous at x equal a, meaning that there's no rupture or gap from left to right. And even specifically and exactly at x equal a, the function has an actual value. Example, consider f of x is equal to x squared. Evaluate the limit of x squared as x approaches 2. So this is equal to limit x squared, x approaching 2, equal 2 squared equal to 4. So hence the limit is equal to 4. More than that, f of 2 actually exists, and limit both to the left of x equal 2 and to the right, meaning that limit x squared as x approaches 2 minus 2 from the left is equal to limit x squared as x approaches 2 from the right, 2 plus, which is right after 2, equal f of 2 equal 4. Hence the function is continuous because the limit is continuous at x equal 2, meaning the limit to the left, to the right of 2 exists, and they are equal each other. Also, they are equal f of 2, which also exists as a point on the function, on the curve. Hence, the function is continuous at x equal 2, having a value of 4. Evaluate limit of 2x plus 1 as x approaches 3. Substitute x equal 3. Okay, so this is equal 2 times 3 plus 1 equals 7. Therefore, the limit is 7. Numerical limits. A limit can be estimated by examining values near the point of interest. Thus, limit of x squared as x approaches 1 is equal to 1. Let's construct a table. So for x 0.9, x squared is 0.81. 0.99, x squared is 0.9801. So we are seeing how for each value of x approaching 1, okay, you have a value that is approaching x squared for x equal 1, okay? So hence, x squared approaches 1 as x approaches 1 based on this table. So as x becomes closer and closer to 1, x squared, which is the function f, also becomes closer to its limit, which is 1. Use numerical reasoning to evaluate limit x plus 4 as x approaches 2. So near x equal 2, x plus 4 approaches 2 plus 4 equal 6, hence the limit is equal to 6. A graph often reveals the value a function approaches. So, for example, limit x squared as x approaches 2 is equal to 4. So if you plot x squared, which is a parabola starting from 0, the vertex is 0, 0. For x approaching 2, yeah, this becomes, let's say this is 2, okay, so this becomes 4, the function becomes 4, the limit becomes 4. So the graph approaches the point 2, 4. As x approaches 2, y approaches 4. And this is from both sides. I'm not talking about from left of the y-axis and the right. No, from both sides, meaning that if we take this chunk here, as x approaches 2, the function on left of 2, okay, to the left of x equal 2, and to its right is equal to 4. So this is the function if we want to blow up the function. Okay, so for x right before 2, at 2 minus, meaning right strictly before x equal 2. So for 2 minus, the limit is 4. For 2 plus, meaning right after x equal 2, also the value is 4, and f of 2 is also equal to 4 as well, and the limit is 2. The limit actually for x equal to is 4, and f of 2 is equal to 4. So the function is continuous at x equal 2. Removable discontinuity example. Consider f of x is equal to x squared minus 1 divided by x minus 1. Okay, here we cannot divide by 0, as you know. So for which values of x, the denominator becomes 0. You solve x minus 1 equals 0, hence x equal 1. X should be different than 1. This is a forbidden value. So another way, by the way, to solve it is f of x is equal to x minus 1 times x plus 1 divided by x minus 1. So f of x is equal to x plus 1 for x different than 1. Thus, limit f of x as x approaches 1 is equal to 2. Okay? Why? Because it has an undefined form in its original format. Because if you want to fill x with 1 in the original form, it gives you 0 over 0, which is undefined or undetermined. But f of 1, okay, the limit f of x as x approaches 1 is equal to, given by this factoring that we've done. So the limit as x approaches 1 is equal to. So let's look at it again. X squared minus 1 is x minus 1 times x plus 1. Because if we want to get the limit as x approaches 1 in the original form of the function, you get 0 divided by 0, which is undetermined. So one way to get around it is x squared minus 1 is equal to x minus 1 times x plus 1. You factor it out, you are left with x plus 1. So limit of that function as x approaches 1 equal 1 plus 1, which is 2. One-sided limits. Sometimes behavior differs on each side of a point, meaning that you have a left-hand limit right before x equal a, meaning to the left of a, which is denoted as a minus. A minus meaning that x is approaching a from the left. It is slightly less than a. Of f of x, okay, that would be the left-hand limit. Right-hand limit is limit of f of x as x approaches a plus, meaning that if this is a, you are approaching from the right. So x is simply slightly bigger than a, which is denoted as a plus. So that would be the right hand or right-sided limit. Okay, means x approaching a from the right. These two should be equal for the limit to exist. So a two-sided limit would exist if limit f of x as x approaches a minus equal limit f of x as x approaches a plus. Let f of x be equal to 1 for x less than 0 and 2 for x greater than 0. In other words, for x negative, y is equal to 1. For x positive, strictly positive, y is equal to plus 2. Here, plus 1, and strictly less than 0, by the way, meaning that it doesn't even touch x equals 0. So the limit of f of x as x approaches 0 minus, meaning that as x approaches 0 from the left, okay, which is for x less than 0, the limit is equal to plus 1. Limit f of x as x approaches 0 plus exactly at the right of 0 is equal to, which is this criteria here. Since they differ, meaning limit f of x as x approaches 0 plus different than limit f of x as x approaches 0 minus, so limit f of x as x approaches 0 does not exist. Determine whether limit of f of x as x approaches 0 exists for f of x is equal to -1 for x strictly negative and 3 for x strictly positive. So for x strictly less than 0, f of x is equal to -1. Now, for x strictly greater than 0, f of x is equal to +3. Hence, limit f of x as x approaches 0 minus, meaning it's approaching 0 from the left, the limit is equal to -1, the left-handed limit. As for the right-hand limit, limit f of x as x approaches 0 plus, meaning approaching 0 from the right, limit is equal to 3. Since they are different, since limit f of x as x approaches 0 minus is different than limit f of x as x approaches 0 plus from the right, hence the limit does not exist. Also, I have to add another thing that we should have noticed, which is the fact that f of 0 does not even exist. There's no value for f when x is strictly equal to 0. Because you notice that you have values of f for x less than 0 and for x strictly greater than 0. But for x equals 0, the function has no value at all. Hence, it's also discontinuous. You have a gap at x equals 0. And actually, another reason why it's discontinuous is because that the limit to the left is different than the limit to the right. To be more clear, the criteria or the condition for the function to be continuous is that the limit of the function as x approaches a minus, 0 minus in our case, should be equal to the limit of the function as x approaches a plus, approaching 0 from the right, equal f of a, which is f of 0 here. In other words, the value of the function for x equal a should exist. Infinite limits. Infinite limits occur when function values grow without bound. As an example, consider f of x is equal to 1 divided by x squared. As x approaches 0, f of x approaches infinity. Why? Because you're dividing by 0. It is 1 divided by 0, which is equal to infinity. Thus, limit 1 over x squared as x approaches 0 is 1 divided by 0, which blows up to infinity, indicating a vertical asymptote. What is a vertical asymptote? So, this means that for x is equal to 0, and by the way, in such case, you draw it in a dotted format. For x equals 0, the function would have no value. So, it approaches, okay, for example, as x approaches 0, from both sides, the function becomes plus infinity. So it approaches plus infinity, okay, and x never actually reaches x equals 0. Example, limit of 1 over x as x approaches 0 plus. Now, what does it mean x approaches 0 plus? It means that x is strictly positive because it's approaching 0 from the right. So it has a positive value because any value right after x equals 0 would be positive. Hence, the limit as x approaches 0 plus of 1 over x, it would be 1 over 0 plus equal to plus infinity. Meanwhile, limit of 1 over x as x approaches 0 minus, meaning approaching x equals 0 from the left, it would still have a negative value, and 1 divided by 0 minus, which is negative, becomes minus infinity. So, right after x equals 0, the function would be blowing up to plus infinity, but to the left of x equals 0, it would go to minus infinity, like this. Given the fact that the one-sided limits, which is the left-hand limit and the right-hand limit, differ, one goes to plus infinity, the other goes to minus infinity. So, hence the limit does not exist. So, limit of 1 over x as x approaches 0 does not exist. Evaluate limit of 5 over x as x approaches 0 plus. X approaching 0 plus, meaning it's approaching 5 over x from the right, okay? So this is how x is approaching 0. So it's still positive, hence it goes up to plus infinity. Limits at infinity. Limits at infinity describe end behavior. Example 1, limit of 1 over x as x approaches infinity. Now imagine you have a cake. If you divide a cake or this cake among 5 people, okay, each one would get a fair chunk, a decent chunk. Among 10, smaller chunks. Among 1,000, you would barely get a crumb. But among an entire city of millions of people, you would get nothing. This is basically what it means, that the limit of 1 over x as x approaches infinity is equal to 0. Meaning nothing is left from the limit, okay? Nothing is left from the value, because you're dividing amongst a very large number of people. Hence, such limit approaches 0. Limit 3x plus 1 as x approaches infinity is equal to 3 times infinity plus 1, which is infinity. As simple as that. Limit x squared as x approaches minus infinity is plus infinity, given that x squared would always produce a positive value, because it's a squared number. Evaluate. Limit of 7 over x as x approaches infinity becomes 7 divided by infinity, which is 0. Limit x3 as x approaches infinity, also infinity, simply because you are raising infinity to the power of 3. So, algebra of limits. Suppose limit f of x is equal to L as x approaches a, and that of g of x as x approaches a is equal to m. Hence, the sum rule postulates the following, that the limit of f of x plus g of x as x approaches a would be equal to L plus m. L being the limit for f of x, and m that of g of x. Difference rule, limit f of x minus g of x as x approaches a is equal to also the difference between L and m, or L minus m. Product rule, limit fx times gx as x approaches a is equal to Lm, L being the limit of fm that of g. Quotient rule as well, limit f of x over g of x as x approaches a is equal to L divided by m. But given that m, or with the criteria or the condition that m should be different than 0. Now, and this is as we suppose that limit f is equal to L and g equal to m. Evaluate limit x squared plus 3x as x approaches 2. It is equal 2 squared plus 3 times 2, which is 4 plus 6 equal 10. Evaluate limit of x squared plus 1 divided by x plus 2 as x approaches 1. Simply, we substitute x by 1, so you get 1 plus 1 divided by 1 plus 2, which is 2 divided by 3, 2 over 3. Some limits cannot be evaluated by direct substitution. Common indeterminate forms include 0 over 0, which means that we cannot determine the value of the limit when we get 0 divided by 0, or infinity over infinity, or 0 times infinity, infinity minus infinity, 0 to the power of 0, also another forbidden form, and 1 to the power of infinity also, or infinity to the power of 0. These are different indeterminate forms. Example, evaluate limit of x squared minus 4 divided by x minus 2 as x approaches 2. This gives us 4 minus 4 divided by 2 minus 2, which is 0 over 0, undetermined, so we cannot solve it using a direct substitution. We need to go around it. Okay, so what is the second form for that? Okay, so you simply, we can factorize the numerator. So x squared minus 4 is equal to x minus 2 multiplied by x plus 2. Or you can solve it using the delta function, delta discriminant method. Delta is equal to b squared minus 4ac, because it is of the form ax squared plus bx plus c, correct? A is 1, b is 0, and c is equal to minus 4. So b4, 0, minus 4ac, which is 16. Hence, x1 is equal to minus b, 0, minus square root of 16 divided by 2a, which is 2 times 1, so minus 2. And the second is plus square root of 16 divided by 2, which is plus 2. So it resolves into x minus 2 multiplied by x plus 2, and x minus 2 factors out from both the numerator and the denominator, and we are left with x plus 2. Now we can substitute, and you get, by substituting x with 2, 4, and 4 is the limit. Another example for that, limit of x squared minus 9 divided by x minus 3 as x approaches 3. So the same thing, if we want to substitute, we end up with 0 divided by 0, which is an undetermined form. So we need to break down the numerator into x minus 3 times x plus 3 divided by x minus 3. X minus 3 factors out, both in the numerator and the denominator, and we are left with x plus 3. We substitute x with the value, which is 3, okay? So hence, the limit is plus 6, or 3 plus 3. The Squeeze Theorem. Suppose g of x is less than or equal to f of x, less than or equal to h of x, and the limit of g of x as x approaches a is equal to L, equal to the limit of h of x as x approaches a. Then, in this case, since f of x is greater than equal to L, less than or equal to L, so it is bounded by L. In other words, the limit of the function f of x as x approaches a is also equal to L. As an example, sine 1 over x is greater than or equal to minus 1, less than or equal to plus 1. Okay, so we need to find the limit of x times sine of 1 over x. We simply multiply by x the entire range, okay, or the three inequalities, or the two inequalities, the components between these two inequalities. So you multiply to the left by x all the way to the right. So minus x in absolute value less than or equal to x times sine 1 over x, less than or equal to x in absolute value plus x. As x approaches 0, the left, which is minus x in absolute value, also approaches 0, and so does the right. Hence, limit of x sine 1 over x as x approaches 0 is equal to 0, given that both sides also have a limit of 0. And limit, or x sine 1 over x, being greater than or equal to 0 as x approaches 0, less than or equal to 0 as x approaches 0, so its own limit is 0 as well. Evaluate limit of x squared sine of 1 over x as x approaches 0. Since sine 1 over x is between minus 1 and plus 1, so we multiply everything by x squared from left to right. So minus x squared less than or equal to x squared sine 1 over x less than or equal to x squared. Both bounds approach 0, so as x approaches 0, this bound approaches 0, and so does this one. Hence, x squared sine 1 over x, so limit of x squared times sine over 1 over x as x approaches 0 is equal to 0. For more definition of a limit, an advanced section, but for me, very important and interesting section. So the rigorous definition states that limit f of x is equal to L as x approaches a if for every epsilon being an infinitesimally small number greater than 0, there exists delta greater than 0, such as x minus a in absolute value, which means that the distance between x and a approaches delta, okay, is between 0 and delta, implies that f of x minus L approaches epsilon, or the distance between the function, the value of the function, the curve, the height of the curve, and its limit approaches epsilon. This is known as the epsilon delta definition of a limit and forms the foundation of real analysis, by the way. So what does it mean analytically? Let's say this is the function. So what does it mean that the limit of the function f of x as x approaches a is equal to L? It means that as x approaches a, this is x and this is a. And the distance between x and a, the distance is x minus a in absolute value, becomes slightly less than delta. So it becomes so small, okay? At the same time, as x approaches a, the function f, the height of the function f of x, okay, and the limit, okay, so the function and the limit, L, which means that the distance between the height of the function and the limit approaches epsilon. So let's say this is the function and this is the limit. This is the height of the limit, okay? So as x approaches a, meaning that x minus a, this distance becomes less than delta, greater than 0, of course, f of x minus L, meaning that the height of the function and the distance between the height of the function and the actual ceiling, which is the limit, becomes less than epsilon. So the distance between f of x and L in absolute value means the distance becomes less than epsilon, which is also a very small number. Comprehensive review exercises. Evaluate limit for x minus 3 as x approaches 5. It is equal to 20 minus 3, which is 17. Evaluate limit x squared minus 1 divided by x minus 1. So we break down x squared minus 1 into x minus 1 times x plus 1, because you have otherwise an undetermined form, which is unresolvable. So as we make it x minus 1 times x plus 1, we factor out x minus 1 and we are left with x plus 1. For x equal 1, the limit becomes 2. Evaluate limit of 1 divided by x3 as x approaches infinity becomes 1 divided by infinity equal 0. As x approaches infinity, 1 over infinity approaches 0. Evaluate limit of 1 over x squared as x approaches 0 plus. It doesn't matter, 0 plus 0 minus, because the denominator is squared. However, in both cases you are dividing by 0, so it blows up to plus infinity. Whether 0 minus, meaning approaching from the right, or from the left, as 0, whether 0 minus from the left, 0 plus from the right. So both from 0 minus or the left, or 0 plus from the right, it produces a limit of plus infinity. It blows up completely. Finally, in this module, we studied the concept of limits, numerical and graphical approaches, one-sided limits, infinite limits, limits at infinity, algebraic properties of limits, intermediate forms, Squeeze Theorem, which is very important, and the rigorous epsilon delta definition. The limits provide the mathematical foundation for differential and integral calculus. They allow us to study function behavior near points, analyze continuity, define derivatives, and measure accumulated quantities through integration. Mastery of limits is essential for all advanced topics in calculus and real analysis. Continuity of functions. Okay, continuity is one of the central concepts of calculus. This is module 8, by the way. Intuitively, a function is continuous if its graph can be drawn without lifting the pencil from the paper, meaning there are no gaps. There's no gap from left to right and at the point as you're drawing. This is the continuity of the function at that point, at x equal to a, for example. Continuous functions exhibit predictable behavior and allow the powerful tools of calculus to be applied. Continuity is essential for differential calculus, integral calculus, optimization, mathematical modeling, physics and engineering applications, and real analysis. In this module, we study the formal definition of continuity, various types of discontinuities, the IVT or intermediate value theorem, continuity on intervals, continuity of piecewise defined functions. So despite the fact that we might have introduced the concept before, but what is a continuous function? What does it mean that a function f of x is continuous at a point x equal a? This would be true if the following three conditions are met. First, f of a exists, plus limit f of x as x approaches a exists. The third condition is that the limit of f of x as x approaches a should be equal to f of a. If any of these conditions is violated or fail to be met, the function is discontinuous at x equal a. Another shorthanded way to write it, so f of x is continuous at x equal a when, and only when, limit f of x as x approaches a minus, meaning approaching a from the left, this limit should be equal to limit f of x as we approach a from the right, as x approaches a plus, equal to f of a. So it should be equal to the value of the function for x equal a, meaning there would be no gaps. So let's say this is the point. So from the left, the height of the function is exactly, for example, plus 1. Also, from the right, the height of the function right after x is equal to a is also plus 1. So the limit is both 1, okay, to the left and to the right of x equal a. Moreover, f of a exists and it is equal to the limit. So it should also be equal to plus 1. And in such case, we can confidently say that the function f is continuous for x equal a, and its value is plus 1. Example, determine whether f of x is equal to x squared is continuous at x equal 3. Let's start with f of 3. So f of 3 is equal to 3 squared equal 9. It exists. Second, let's check the limit of x squared as x approaches 3. So limit x approaches 3 minus f of x is definitely equal to the limit of f of x as x approaches 3 plus, because we have a squared value, okay, equal, actually 3 is positive anyway. So it is equal to 9, equal to f of 3, which is 9. Hence, the function is continuous given that the limit of f of x as x approaches 3 is equal to f of 3, and the function is continuous at x equal 3. Determine whether f of x equal to 1 over x is continuous at x equal 2. Solution, f of 2 is equal to 1 half. 1 over 2, which is 1 half. Limit 1 over x as x approaches 2 is equal to 1 half. Therefore, f of x is continuous at x equal 2. Determine whether f of x is equal to x to the power of 3 minus 2x plus 1 is continuous at x equal 1. First, f of 1 is equal to, we replace x by 1. 1 to the power of 3 minus 2 plus 1 equals 0. Limit f of x as x approaches 1 is also equal to 0. So limit f of x as x approaches 1 is equal to f of 1. Hence, the function is continuous at x equal 1. Continuity of elementary functions. Many familiar functions are continuous throughout their natural domains, such as polynomials. Every polynomial is continuous for all real numbers. Examples, x2, x5 minus 3x plus 7. Okay, so they are definitely continuous throughout R. A rational function is continuous wherever its denominator is non-zero. Example, f of x is equal to x plus 1 divided by x minus 3. Now, for x equals 3, the function blows up to infinity because you are dividing by 0. So you get an asymptote and a like barrier for the function. The function it can approach this asymptote, it would be like a barrier, but it can never reach it. So it would be continuous elsewhere except for the asymptote itself, where it would not have a value. Radical functions. A radical function is continuous on its domain. Example, f of x is equal to square root of x. It's continuous for every x greater than or equal to 0. Okay? Now, for x less than 0, the function does not exist anyway. There's no way in the real number scope for square root of x to have a minus value within the square root itself. So square root of minus 3, for example, does not exist within the real numbers. Now, if you convert it into 3i squared, it can exist among the complex numbers, and this is how you can solve it, but it's not for here, okay? So anyways, the function is continuous for x greater than or equal to 0. Now, for trig functions, whether sine x or cosine x, they are continuous everywhere, so it doesn't matter what value of x you would have, the angle would keep increasing to infinity. It's like you're going about the same circle over and over again. So for any value of x, the angle would be going like alpha plus n to pi. It would be a multiple of different cycles, okay? So it would give you always a value. However, the peak and the trough are respectively +1 and -1. So this is the range of both of these two functions. Determine the interval or intervals where f of x is equal to x plus 1 divided by x squared minus 4 is continuous. First, we need to remove the forbidden values, or to pick out the forbidden values, for which the denominator in such case would become 0, meaning that by dividing by 0, you get two asymptotes where the function would blow up to infinity. So we need to solve the denominator. X squared minus 4 is equal to x minus 2 times x plus 2, or simply you place x squared minus 4 equal to 0, hence x squared equal 4, x equal plus minus square root of 4, or plus minus 2. So it is equal to x minus 2 times x plus 2. Hence, the discontinuities occur at x equal 2 and x equal minus 2. So the function is defined for x is existing between minus infinity, of course, minus infinity excluded, all the way to minus 2, also excluded, union between minus 2 excluded and plus 2 excluded, meaning minus 1 acceptable, 0 acceptable, plus 1 acceptable, all the way to plus 2. But plus 2 should be taken out of the equation, meaning that for plus 2, the function cannot exist. Union, another union, all the way to plus 2 excluded to plus infinity. And of course, plus infinity is excluded, given that plus infinity is not even a number, okay? So this is the definition domain for the function, and it's continuous over 3 intervals, which are the following intervals. But between these intervals, you have gaps. Types of discontinuities. There are several ways continuity can fail. First, what is called removable discontinuity. It occurs when a hole exists in the graph. So for example, f of x is equal to x squared minus 1 divided by x minus 1. Now, for x equal 1, the function cannot exist. Okay? So x should be different than 1. X equal 1 is an asymptote, so it presents a hole within the function, meaning that the function is not continuous there. So, although f of 1 is undefined, limit of f of x as x approaches 1 is equal to 2. Okay? So, a hole exists at 1, 2. So f of 1, yes, correct, it's undefined, but the limit of the function, meaning that as x approaches 1, the function approaches 2. And this is the location of the hole. At x equal 1 and y equal 2, there's a gap where the function does not exist. Classify the discontinuity of f of x is equal to x squared minus 4. This can be rewritten as x minus 2 times x plus 2 divided by x minus 2. Now, remember, x should be different than 2. However, the limit of f of x as x approaches 2 is equal to, okay, so we factor out these two, numerator and denominator. So it is limit of x plus 2 as x approaches to equal 4. So the limit exists despite the fact that there's a hole at 2, 4. So this is a removable discontinuity. And this is the answer. So x should be different than 2. The limit exists, but the function is undefined at x equal 2. Therefore, removable. The other type is jump discontinuity. It occurs when left-hand and right-hand limits differ. As an example, f of x is equal to 1 for x negative, strictly negative, and 3 for x positive. Let's plot it out. So for x strictly less than 0, meaning starting from here all the way to the left, the function is equal to, okay, 1, 2, 3. So the function is equal to 1 for x strictly less than 0. For x strictly greater than 0, meaning right after the y-axis, f of x is equal to 3. Notice that to the left of 0 and to the right of 0, we have two different limits. In other words, limit f of x as x approaches 0 minus, x approaching 0 minus meaning x approaching 0 from the left, the value of the limit is 1. Meanwhile, the limit of the function as x approaches 0 from the right, or in other words, limit f of x as x approaches 0 plus, is equal to 3. Since limit f of x, x approaches 0 minus, is different than limit f of x, x approaching 0 plus, the first one being 1, second being 3, hence the limit does not exist. Classify the following discontinuity. F of x is equal to 2 for x less than 1 and 5 for x strictly greater than 1. So let's plot it. This is x equal 1. To the left of 1, strictly to the left, f of x is equal to, so this is starting from the left of 1 all the way as x go to infinity, to minus infinity, and to the right of 1, strictly to the right of x equal 1, f of x is equal to 3, 4, 5. So y is equal to 5 in such case. The limit of f of x as x approaches 1 minus, meaning as x approaches 1 from the left, this is 1 minus, is equal to limit f of x as x approaches 1 plus, or 1 from the right, this is 1 plus, is equal to 5. So they are different. Limit f of x as x approaches 1 plus, and the limit does not exist because the one-sided limits differ, and this is called a jump discontinuity. Another thing to notice, which we should pay attention to, is the fact that for x equal 1 strictly, f of 1 does not exist. Okay? It does not exist in R, okay? Or it's not even available. In other words, notice something. We have the value of f for x strictly less than 1. We have value of f, which is 5, strictly greater for x strictly greater than 1. Two different limits, so the limit does not exist. More than that, okay, the value of the function at x is strictly equal to 1 does not exist. Infinite discontinuity, the third type, occurs when the function approaches infinity. For example, f of x is equal to 1 divided by x squared. At x equals 0, the limit of f of x as x approaches 0 is equal to plus infinity. It blows up. So x equals 0 is a vertical asymptote where the function cannot approach. So for x equal to 1, you would have 1, okay, x equal to, yeah, it starts depleting. It starts from plus infinity all the way down, okay, from both sides, okay? So as x approaches a high value or a highly negative value, okay, the value of the function is infinity. I don't want to study the function right now. The point is, in such case, the infinite discontinuity, you would have x equals 0 being an asymptote, or the forbidden value is an asymptote that leads or throws the function into an infinite blow-up. Here I want to correct something, because in one of the examples in the removable discontinuity, we have something, yeah, for example, x squared minus 1 over x minus 1, correct? So this becomes x minus 1 times x plus 1. Again, this is the removable discontinuity case over x minus 1. So the limit here becomes, for x approaching 1, for example, it becomes 2, okay? And it's not an asymptote. So I might have mistakenly said that it was an asymptote. No, it's not. It is a removable discontinuity. So the function, so x should be different than 1 in such case in the denominator. And at that point, you have a hole. However, you don't have an asymptote because the limit itself exists. It doesn't throw the function to infinity. Classify the discontinuity of f of x is equal to 1 divided by x minus 4. Now, at x equal 4, limit f of x as x approaches 4 is equal to 1 divided by 4 minus 4, or 1 over 0, which is equal to infinity. So this is an infinite discontinuity where x equal 4 becomes an asymptote, meaning a barrier where the function can approach but can never get through. The function would never have a value on this line, which is x equal 4. So again, x equal 1, 2, 3, 4 is an asymptote. This is how you draw an asymptote. Now, as x itself approaches infinity, the curve approaches 0. But as we approach x equal 4, it blows up to infinity, to plus infinity, after x equal 4. Now, for x approaching 4 from the left, it would be 4 minus, for example, let's say 3.8 minus 4. It becomes in the denominator. So it would give you a negative value. Hence, 1 over 0 minus is minus infinity, meaning the function would be going to minus infinity. And as x go to minus infinity, the function becomes or approaches 0. So this is how you plot the function. And we didn't even need the derivative to get the variation, okay? So f of x equal 1 divided by x minus 4 at x equal 4, limit of f of x as x approaches 4 minus, meaning from the left. In other words, x has a value slightly less than 4. So let's say 3.8. Minus 4 would give you a negative value. So 1 over a very small negative value, 1 over 0 minus basically, becomes minus infinity. As for limit 1 over x minus 4, as x approaches 4 plus, meaning that x would be slightly bigger than 4, so it would have, for example, 4.1, let's say, minus 4, it would give you a positive number, 0.1. And as you divide 1 by 0.1, it would blow up to plus infinity. But in both cases, it is an infinite discontinuity where x equal to 4 is a vertical asymptote. Continuity on an interval. A function is continuous on an interval if it's continuous at every point within that interval. Example, f of x is equal to x to the power of 3 is continuous throughout R from minus infinity all the way to plus infinity. Okay, so it's continuous throughout the entire interval of the real numbers. Example, f of x is equal to 1 over x. Now, we know that for x equals 0, the function blows up to infinity. For x approaching 0 plus, meaning approaching 0 from the right, this becomes 1 divided by 0 plus, which is plus infinity. For x approaching 0 from the left, it would be a slightly minus number, so 1 over 0 minus is equal to minus infinity. Hence, at x equals 0, we have a vertical asymptote, and the function would not be continuous because it won't have a value at x equals 0 straight. Hence, the function is continuous between minus infinity and 0 to plus infinity, or, which is the domain of definition, by the way, it's continuous for x existing between minus infinity to plus 0 excluded, then between 0 also excluded all the way to plus infinity. But at x equals 0, we have a discontinuity or a gap, where the function is not a gap, so to speak. It is a vertical asymptote where the function cannot be defined. It blows up to plus minus infinity. Determine the intervals of continuity for f of x is equal to x plus 1 divided by x squared minus 9. So let's solve the denominator to check for which values of x the function becomes divided by 0 and blows up to infinity. Okay, so x squared minus 9 is equal to x minus 3 times x plus 3, as simple as that. Or you can solve it like this: x squared minus 9 is equal to 0, hence x squared equal to 9, and x is equal to plus minus square root of 9, equal plus minus 3. So the discontinuities are x equal minus 3, x equal plus 3, which are two vertical asymptotes at x equal minus 3 and x equal to plus 3. With that being said, okay, so the intervals of continuity, or in other words, the function exists for x, is within the following scope: from minus infinity to minus 3. Of course, the boundaries are open, they are excluded. Minus infinity is not a number anyway, but the point is, all the negative numbers all the way to minus 3, but minus 3 is not among them. Minus 3 is excluded. Union, minus 3 to plus 3, both excluded, meaning that minus 3 and 3 are forbidden. However, minus 2 point something, for example, minus 2, minus 1, 0, plus 1, plus 2 are acceptable. Union, 3 all the way to plus infinity, and both the bounds again are excluded, meaning x equals 3 is forbidden, and plus infinity means all the way to plus infinity, but plus infinity is not a value anyway. Okay, so this is the scope of continuity, and these are the intervals of continuity. And we can say that these three sets are not connected, meaning we have a gap. We have two gaps between them, between the first and second, and between the second and the third. Continuity of piecewise functions. So piecewise functions often require special analysis to test continuity at the joining point C. We compute at the joining point limit f of x as x approaches c minus from the left, also limit f of x as we approach c from the right, or x approaching c plus, and we compute the value of f of c. If these three are equal, then the function is continuous, given that it has a value at x equals c, and the limit to the left and to the right is equal, or the limits to the left and to the right are equal to each other, and they are equal to f of c, and f of c actually exists. Determine the value of k that makes f of x is equal to x plus 2 for x less than 1, k for x equal 1, and 3x for x greater than 1. Continuous at x equal 1. So for which value of k the function becomes continuous at x equal 1. Solution: limit of x plus 2 as x approaches 1 minus, meaning as x approaches 1 from the left, is equal to 1 plus 2 equal 3. As for the right limit, limit 3x as x approaches 1 plus, or as x approaches 1 from the right, is equal to also 3. Hence, f of x for x equal 1 should be equal to 3 also for the function to be continuous. Hence, k should be equal to 3. Find k so that f of x equal to x plus 1 for x less than 2, k for x equal to, and x plus 3 for x greater than 2 is continuous at x equal to. Okay, so at first, limit 2x plus 1 as x approaches 2 equal 5. You replace x by 2, as simple as that. Okay, this is 2 minus, meaning for x less than 2, or approaching x from the left. As for limit, as x approaches 2 from the right, meaning for x greater than 2, the function changes into x plus 3. So it becomes limit x plus 3 equal 5, which is 2 plus 3, or 5. Hence, for continuity, k for x equal to, meaning that f of 2 should be equal to 5, so k should be equal to 5. And this is the criteria of continuity. Limit f of x for x approaching x approaching 2 from the left should be equal to the limit of f of x for x approaching 2 from the right, x approaching 2 plus, and equal to f of 2. If this criteria is met, then the function is continuous at x equal 2. IVT, or the intermediate value theorem, is one of the most important consequences of continuity theorem. Suppose f of x is continuous on the closed interval ab, and n is any number between f of a and f of b. Then there exists some point c between a and b, meaning that c is not a, neither b, but is between both, such that f of c should be equal to n, meaning that for any c within the interval, the open interval a and b, between a and b but different than a or b, f of c has a value n. So for whatever point, the function between a and b, the function has a value. This is like the proof that it would be continuous between a and b. To clarify it further, let's suppose this is a and b. So we're saying that no matter where c is located between a and b, okay, c should have a value on the function f. So whatever c is, it would have a value on f. So this means that wherever c is moving between a and b, f would be also having its own height, its own elevation, its own value. So consider for each c there will be a dot on the curve. So as you connect these dots on the curve together, you would form a continuous plot between a and b. And this is the definition of the IVT, or intermediate value theorem. So by interpretation, a continuous function cannot jump over values. If it starts below a value and ends above that value, it must pass through an intermediate value between both. As an example, f of x is equal to x3 minus x minus 2 has a root between 1 and 2. So demonstrate that f of x has a root between these two elevations. First of all, f of 1 is equal to 1 to the power of 3 minus 1 minus 2 equal 1 minus 1, 0, minus 2. f of 2 is equal to 2 to the power of 3 minus 2 minus 2, which is 8 minus 4 equal 4. Now, notice something. You have a peak within this interval at plus 4 for x equal 1, and a trough that is negative, which is minus 2 at x equal to, or the upper bound. So at the lower bound, the value is 4. At the upper bound, the value is minus 2. Okay, upper bound of the interval. Hence, 0 is an intermediate value, is a value existing in the function, because to pass from a positive altitude to a negative altitude, you definitely have to pass through 0, meaning that you would clip the x-axis at some point. And the elevation at that point would be 0. Now, since 0 lies between minus 2 and plus 4, and f of x is continuous between 1 and 2, okay, between the lower and upper bound, hence c is a value, an actual value, okay, between 1 and 2, for which f of c has a value, and in this case equals 0. Given the fact that we have passed from a positive height, positive y value, to a negative y value, definitely you have passed through a 0 point. 8. Show that f of x is equal to x squared minus 3 has a root between 1 and 2. So f of 1 is equal to 1 minus 3 equal minus 2. F of 2 is equal to 4 minus 3, which is plus 1. Then definitely 0 is a value between minus 2 and plus 1. So let's say we want to draw this graph. The bounds are between 1 and 2. F of 1 is equal to minus 2. And f of 2 is equal to plus 1. So the function definitely will pass by y equals 0, okay, by clipping the x-axis. So 0 lies between minus 2 and plus 1. Hence 0 is an actual value. And there exists a c for which f of c is equal to 0. Continuity and limits. A function is continuous at a precisely when limit f of x as x approaches a, both from the left and from the right, should be equal to f of a. Actually, for the limit to exist, meaning that for the first term to be correct, this would be, or this would indicate that limit f of x as x approaches a minus should be equal to the limit of f of x as x approaches a plus from the right. So this would prove for us that the limit actually exists. And if this limit is equal to f of a, hence the function is continuous at x equal a. Thus, continuity can be viewed as a direct consequence of limit behavior. Determine whether f of x is equal to x squared minus 1 divided by x minus 1 for x different than 1, and equal to for x equal 1 is continuous at x equal 1. Okay. Now, for the denominator, we know that x should be different than 1. Why is that? Because if x is equal to 1, there would be a gap, okay, a forbidden value. So now let's check the limit. Limit f of x as x approaches 1 is equal to, okay, x squared minus 1 is simply x minus 1 times x plus 1. So limit x minus 1 times x plus 1 divided by x minus 1 equal limit x plus 1 as x approaches 1, which is 2. Okay, so the limit exists, and for x equal 1, f of 1 is equal to, hence the function is continuous despite the fact that we are suspecting, okay, but here, since for x equal 1, the function is equal to, so it actually had negated the fact or the first proposition that x cannot be equal to 1, okay, given from the proposition of the exercise that for x equal 1, the function actually has a value. So since the limit of the function as x approaches 1 is equal to f of 1 equal to, hence the function is continuous at x equal 1. And here's the solution. So For x different than 1, f of x is equal to x plus 1 limit is equal to f of 1 equal to the limit of f of x as x approaches 1 is equal to f of 1 equal to, hence the function is continuous at x equal 1. Continuity theorems. If f and g are continuous at a, then the following are also continuous at a. Sum, which means f of x plus g of x. Difference, f of x minus g of x. The product of the two functions, or f of x times g of x. Quotient, f of x divided by g of x, provided that g a is different than 0. And composition, composition meaning function nesting, which is f of g of x. Determine whether h of x is equal to square root of x squared plus 1 is continuous. Okay, now, for x squared plus 1, it should be greater than 0, but it's always greater than 0 since x squared greater than or equal to, okay? But x is always positive, and it's added with 1, so this is always valid. For whatever value of x, there exists an h of x. Okay, so x squared plus 1 is continuous for all real numbers. The square root function is continuous for positive inputs since x squared plus 1 is greater than 0 for all x, hence h of x is continuous for all real numbers. Comprehensive review exercises. Determine whether f of x is equal to absolute value of x is continuous at x equal 0. Solution. Limit of x, an absolute value, as x approaches 0 is equal to 0, and f of 0 is equal to 0, hence the function is continuous. Classify the discontinuity f of x is equal to 1 divided by x plus 2 at x equal minus 2. Okay, so limit f of x as x approaches minus 2 is equal to 1 divided by 0, minus 2 plus 2, equal plus infinity. So it blows up to infinity, hence x equal minus 2 is a vertical asymptote, and this barrier like forbids the function to pass through it. So the function has no values on this barrier. Actually, it blows up to infinity. Therefore, it is an infinite discontinuity, and the function is not continuous there because at that point it can approach but it can never get through. So the function has no value for x equal minus 2. It goes to infinity. Find the value of k that makes this function continuous at x equal 2. Okay, limit f of x as x approaches 2 from left, from behind. Okay, so as x approaches 2 minus is equal to limit of x squared for x approaches 2, okay, or 2 minus, which is equal to 4. Now, limit f of x as x approaches 2 plus, meaning as x approaches 2 from the right, is the limit of this second function for x minus 4 as x approaches 2 plus, which is equal to 8 minus 4 equal 4. So, k should be equal to 4 at x equal 2. In other words, f of 2 should be equal to 4, so that the function would be continuous at x equal 4. So again, the solution, limit x squared as x approaches 2 minus, is the limit of this function equal 4. As x approaches 2 plus, it is the limit for this function for x minus 4, which is equal to 4. Hence, k should be equal to 4. At the end, in this module, we studied the definition of continuity, continuous elementary functions, removable discontinuities, jump discontinuities, infinite, continuity on intervals, continuity of piecewise defined functions, IVT or intermediate value theorem, and continuity theorems for sums, products, quotients, and compositions. Continuity provides the bridge between limits and differentiation. It guarantees predictable behavior of functions and enables many of the fundamental theorems of calculus. Mastery of continuity is essential before studying derivatives, optimization, and advanced topics, especially in real analysis. 9. Asymptotic analysis and end behavior of functions. Asymptotic analysis. Okay, so one of the most important aspects of function analysis is understanding how functions behave near infinity, near discontinuities, and near singular points. Such analysis helps us understand the global structure of a function, predict long-term trends, identify asymptotes, and sketch graphs accurately. Asymptotic analysis studies the behavior of functions as the independent variable becomes very large, very small, or approaches critical values. Applications include calculus, physics, engineering, computer science, economics, signal processing, and mathematical modeling. In this module, we study horizontal asymptotes, vertical asymptotes, oblique asymptotes, and behavior, dominant terms, and asymptotic approximations. End behavior of functions. The end behavior of a function describes what happens as x approaches infinity or minus infinity. Understanding end behavior helps us determine long-term trends, how the function changes as x approaches infinity, both positive and negative. Horizontal asymptotes, which are the horizontal lines where the function approaches but it cannot touch and it has no values on that line. Okay, it approaches. Growth rates, and graph shapes. Consider f of x is equal to x squared. As x approaches infinity, so does f of x. Actually, both from minus and plus infinity for x approaching plus infinity or minus infinity, f of x always approaches plus infinity. As x approaches minus infinity also, so thus both ends rise upward. This is the parabola. Determine the end behavior of f of x is equal to x to the power of 3. Now, as x approaches infinity, x3 approaches plus infinity. But for x approaching minus infinity, since the power is odd, x3 approaches minus infinity. Horizontal asymptotes. A horizontal asymptote occurs when limit f of x as x approaches infinity is equal to L. Okay, meaning that as x approaches infinity, the function approaches a specific altitude or height that is bounded by a line, a horizontal line. Or limit f of x as x approaches minus infinity is equal to a limit L, which is a finite limit. So for example, y equal 3 can be an asymptote at a height 1, 2, 3, for which as x approaches infinity, the function approaches this line that it cannot cross over. So it is an upper boundary or a lower boundary if the function is approaching that asymptote from above to below. Okay, so if it's descending and it reaches 3, but it cannot cross through it, then it would be also a horizontal asymptote, but the function would be approaching it from above. So L is finite, and the line y equal L is a horizontal asymptote. Example, consider f of x is equal to 1 divided by x. Limit of 1 over x as x approaches infinity, and also as x approaches minus infinity is equal to 0. Why? Because we are dividing 1 by infinity, both plus and minus. It gives you 0. By the way, for plus infinity, it gives you 0 plus, meaning that right above the function, so right above the line, the asymptote, the function would be. And for 1 over minus infinity, it gives us 0 minus, so the function would be strictly below the horizontal asymptote. And in such case, y equals 0 is a horizontal asymptote. What is y equals 0, by the way? It's simply the x-axis. This is altitude y equals 0. So y equals 0 is a horizontal asymptote for which the function would be approaching like this, either from above or from below, based on the function itself here. Okay, so we're not gonna go into the study of the function, but you get the point that actually, yeah, for x approaching to plus infinity, okay, as x approaches plus infinity, the function would be approaching 0 plus like this. Yeah, so the function would be approaching the curve from above. as x approaches minus infinity, it is 0 minus, meaning that the function would be approaching the horizontal asymptote from below. Okay, this is what 0 minus means. It's approaching from below all the way up, but of course it would never reach the horizontal asymptote in both cases. Find the horizontal asymptote of f of x is equal to 5 divided by x. So limit 5 over x as x approaches plus minus infinity is equal to 0 plus for plus infinity and 0 minus for minus infinity, which is in both cases y equals 0 is the horizontal asymptote. So the horizontal asymptotes of rational functions, consider fx is equal to an xn plus etc. divided by bm xn. Three cases arise. So if the degree of the numerator, okay, you have is greater, I think, or different than the degree of the denominator, so actually less here the word is, so n less than m, then y is equal to 0 is the horizontal asymptotes. For example, yes, when the degree of the numerator is less than the degree of the denominator, the limit goes to 0. Okay, so y equals 0 would be the horizontal asymptote, just like 1 over x. Actually, 1 over x that we've seen before can be rewritten as x to the power of 0 divided by x to the power of 1. So x to the power of 0 or anything to the power of 0 is equal to 1. Hence, or therefore, the degree of the numerator is less than that of the denominator. So in such case, y equals 0 would be the horizontal asymptote. Second case, if the degrees are equal, meaning degree of the numerator is equal to that of the denominator. In such case, y is equal to an divided by bm. A and bm are the multipliers of the highest degrees in the numerator and the denominator, which are the equal degrees. So, example, f of x is equal to 3x squared plus 1 divided by 2x squared plus 5. Now, 1 and 5 will be insignificant as x approaches infinity. So, the limit of f of x as x approaches infinity is equal to 3x squared divided by 2x squared. Because x approaching infinity, both in the numerator and the denominator, okay, would render the second part, which is plus 1 and plus 5, insignificant, negligible. So the limit would be equal to that, 3x squared divided by 2x squared, as x approaches infinity. But we can factor out x squared both in the numerator and the denominator. So we are left with 3 divided by 2. Hence, y equal 3 over 2 is a horizontal asymptote. Now, if the degree of the numerator is greater than the degree of the denominator, in other words, n greater than m, no horizontal asymptote exists in such case. Why is that? Okay, so let's take the case, for example, of 3x4 divided by 2x3 plus 6 plus 9 below. Okay, at first, as x approaches infinity, 6 and 9 become negligible, okay, irrelevant. They become so small in comparison to x4 and x3. Okay, so the limit in such case would be equal to limit of 3x4 divided by 2x3 as x approaches infinity equal 3x4 divided by 2x3 is equal to 3 over 2x. So as x approaches infinity, the function also would approach infinity. And no horizontal line can be considered as asymptote in such case, because the function as x approaches infinity has no bounds. It's also approaching infinity. Okay? So there would be another direction for the asymptote. That would be an oblique asymptote, to be revealed later. So find the horizontal asymptote. This is an exercise here of f of x equal 4x3 plus 1 divided by 2x3 minus 7. The degrees are equal in such case. So even without having to memorize the fact that the degree, when the degree are equal or when the degree are not, okay, you simply solve it. So the limit f of x as x approaches infinity is equal to, now 1 and minus 7 become irrelevant. So we are left with limit 4x3 divided by 2x3 as x approaches infinity equal 4 divided by 2, which is 2. Hence, y equal 2 is a horizontal asymptote. Vertical asymptote. Now, a vertical asymptote occurs when limit f of x as x approaches a is equal to plus minus infinity. Now, in the line x equal a would be a vertical asymptote. So, this is what we mean by that. Let's say this is a, x equal a is this line. So, as x approaches a, f of x approaches infinity, it blows up to infinity, either plus or minus, okay, depending on the function, depending on whether you are approaching. At times, you would be approaching the function or the asymptote from the left, the function blows up to plus infinity, but if you're approaching the function or the function approaching the vertical asymptote from the right, from plus infinity all the way back, the function would blow up to minus infinity. Example, consider f of x is equal to 1 divided by x minus 2. Now, we know that for x equal to, the denominator becomes 0, and the function becomes 1 over 0, so it blows up to infinity. However, okay, we need to check both from the left and from the right the behavior of the function. So, limit f of x as x approaches 2 minus, meaning as x approaches 2 from behind, so it would be slightly less than 2. Okay, of f of x is equal to 1 divided by 2 minus 2. Okay, this is what 2 minus means. It is a value that is slightly less than 2, such as, for example, 1.9998, okay, minus 2. Now, since this value is less than 2, then 1, okay, so the answer would be 1 over 0, okay, but it is minus 0.00001. Since the minus part, okay, since the right part, which is minus 2, is greater than 2 minus, which is, again, a value slightly less than 2. So the answer would be negative, because the denominator is negative. Hence, the limit here would be 1 over 0 minus equal minus infinity. This is very important. So, as x approaches 2 minus, f of x approaches minus infinity. Now, the second part, limit f of x as x approaches 2 plus, meaning x approaches 2 from the right. This would be 1 divided by 2 plus minus 2. Okay, 2 plus means a value slightly greater than 2. So, for instance, 2.0001 minus 2. This would give us a positive value. So, you can say that this is equal to 1 divided by 0 plus, and in such case is it equal to plus infinity. So, we have, first of all, x equal to is a vertical asymptote, but we have two different limits, okay? You have two different variations. One, which is to the right of x equal to, which blows up to plus infinity, and one to the left, which blows up to minus infinity. So it would be something like this. This is x equal to 1, 2. And this is the vertical asymptote. Now, as x approaches 2 minus, meaning as x approaches 2 from behind, the function goes to minus infinity. So it would go like this, okay? Now, I'm not fully studying the function because, by the way, as x approaches infinity, the function, so limit x approaching infinity of f of x is equal to 1 over infinity, which is 0. So you have also a horizontal asymptote, okay? So the function, but we're concerned right now with the vertical asymptote. So as x approaches 2 from the left, the function goes to minus infinity. This is the function. Meanwhile, as x approaches 2 from the right, or x approaches 2 plus, the function goes to plus infinity. And this is the graph for the function. And notice that it also approaches the horizontal asymptote, okay? To the right from above, to the left from below, but that would be concerning the horizontal asymptote. Okay, let's check the horizontal asymptote. Limit x approaching minus infinity of 1 over x minus 2 is equal to 1 over minus infinity, so 0 minus. Correct, okay? For x approaching minus infinity, the function, the limit is 0 minus, meaning that the curve remains below the horizontal asymptote. As for the limit of 1 over x minus 2 as x approaches plus infinity is equal to 0 plus, and the function as x approaches plus infinity remains above the horizontal asymptote. 0 plus means that the curve remains slightly above the horizontal asymptote, which is correct. Find the vertical asymptote f of x is equal to 1 divided by x plus 3. First, okay, so x plus 3 should be different than 0. Then x different than minus 3, or in other words, x equal minus 3 is a vertical asymptote. It is the forbidden value for which the denominator becomes 0, and the entire function blows up to infinity. So, limit, okay, so x equal minus 3 at first is a vertical asymptote. As for the limits, limit f of x as x approaches 3 minus is equal actually to the limit f of x as x approaches 3 plus, because in both cases it is equal to plus infinity. So in both cases the function blows up to infinity to the left and to the right because we don't have a minus sign within the denominator. Oblique or slant asymptote. An oblique asymptote occurs when the degree of the numerator is equal to the degree of the denominator plus 1. In other words, when you have, for example, x5 plus 2 divided by 2x3 plus 1. In such case, the limit would give you, as x approaches infinity, 2 and 1 become negligible, of course, x5 divided by 2x3, which is x2 over 2. So it also blows up to infinity. Also 2 becomes insignificant. So the asymptote is obtained using polynomial division. For example, find the asymptote of f of x is equal to x squared plus 1 divided by x. Okay, what is x squared plus 1 over x? You can simply break it down into x squared over x plus 1 over x, which is equal to x plus 1 over x. As x approaches infinity, this goes to 0, so you remain with y equal x. This is the part that approaches infinity, hence y equal x is an oblique asymptote. Find the oblique asymptote of f of x is equal to x squared plus 3x plus 1 divided by x. So let's divide x squared plus 3x plus 1 over x. Okay, x squared divided by x is equal to x times x squared. Okay, so plus becomes minus. We flip the sense and we add up. Okay, so this is 0 and we are left with 3x plus 1. Then 3x divided by x is equal to plus 3. Then 3 times x, okay, so 3x. You flip the sign, 3x minus 3x, 0. And we're left with 1, okay? So this is x plus 3 plus 1 over x. Actually, you can break it down into simply, okay, so x squared divided by x plus 3x over x plus 1 over x. So x plus 3 plus 1 over x. As x approaches infinity, 1 over x becomes 0. So you are left with x plus 3, hence y is equal to x plus 3 is the oblique asymptote. Dominant term analysis. For large values of x, the highest degree term dominates. Okay, so consider f of x is equal to 3x4 plus 5x2 minus 7. So we consider 3x4 for the limits and other calculations. Hence, f of x is approximately equal to 3x4 And the limit of f of x as x approaches infinity is the limit of the highest term, which is 3x4, which is plus infinity, because it is the dominant one. Consider f of x is equal to minus 2x5 plus 4x squared plus 10. Dominant term is minus 2x5, so as x approaches infinity, f of x approaches minus infinity, given that the term is negative. Determine end behavior of f of x is equal to 7x6 minus 2x plus 1. Dominant term 7x6, since the degree is even and coefficient is positive, hence x approaching plus infinity minus infinity in both ways would imply that f of x approaches plus infinity always. Comparing growth rates. Different functions grow at different speeds. So for large x values, ln x grows less than x squared, less than x3, less than ex, less than x factorial, less than x to the power of x, which is very important when you have a quotient to see whether the function is going or approaching 0 or not, okay? This ordering is fundamental in asymptotic analysis. Compare x5 and ex as x approaches infinity. The exponential function eventually grows much faster. Which grows faster as x approaches infinity? x3 or ex? It is ex that grows faster and dominates. Okay, the polynomial grows. Asymptotic approximation. Sometimes a complicated function can be approximated by a simpler one. As an example, square root of x squared plus 1 for large x can be rewritten as x. Okay, so we get x in form of a common multiplier. So this becomes square root of x squared multiplied by 1 plus 1 over x squared. Now, x squared can be removed to the outside of the square root, so it becomes x square root of 1 plus 1 over x squared. 1 over x squared approaches 0 as x approaches infinity. So we obtain square root of x squared plus 1 is approximately equal to x for large x values. Approximate x squared plus 5x plus 2 for very large values of x. The dominant term is x squared, therefore x squared plus 5x plus 2 is approximately equal to x squared for large values of x, because 5x becomes negligible, so does 2. Consider f of x equal to 1 divided by x minus 1 squared as x approaches 1. Okay, so when x approaches 1, 1 over 0 blows up to infinity. This indicates x equal 1 is a vertical asymptote. Another exercise, limit of 1 divided by x minus 2 squared as x approaches 2. So here, whether 2 is being approached from the left or from the right, okay, the final value would be positive. So it would be 0 plus in both ways. Hence, 1 over x minus 2 squared blows up to plus infinity. And of course, x equal 2 is a vertical asymptote. The applications of asymptotic analysis. Asymptotic methods are used extensively in numerical analysis, engineering approximations, signal processing, computer algorithms, fluid dynamics, quantum mechanics, artificial intelligence, and data science. Example, algorithm A requires n squared operations, B requires n log n. So as n becomes large, n log n grows much slower than n squared. So thus, algorithm B is more efficient asymptotically. Okay, requires less strain, requires less burden on the CPU. Okay, less processing requirements. So in other words, the function that grows slower is n log n, grows slower than n squared. So n log n is slower in growth than n squared. Find the horizontal asymptote for f of x equals 3x plus 1 divided by x plus 5. Limit f of x as x approaches infinity is equal to limit. Okay, so 1 and 5 become insignificant. So it is the limit of 3x divided by x as x approaches infinity equal 3. Hence, y equal 3 is a horizontal asymptote. Find the vertical asymptote f of x equal 2 divided by x minus 7. Okay. In this case, as we notice, we need to solve the denominator and to find for which value the denominator becomes 0, which is obvious. X should be different than 7, or in other words, for x minus 7 equals 0, or x equal plus 7, this function blows up to infinity. Hence, x equals 7 is a vertical asymptote. It is a vertical line for which the function approaches but can never clip, and it blows up to infinity. Now, we need to find the variation. Limit f of x as x approaches 7 minus, meaning x approaching 7 from the left, so it would have a value slightly less than 7. In such case, it is equal to limit 2 divided by, okay, so value slightly less than 7 would be something like 6.998, for example, minus 7, as x approaches 7 minus. So this value is less than 7. Minus 7 gives us a negative value, okay, very close to 0. So it is 2 divided by 0 minus, which is equal to minus infinity. Now, as for the limit of f of x as x approaches 7 plus is equal to limit 2 divided by 7 plus means a value slightly greater than 7, for example 7.001 minus 7, so it would give you a positive 0, or a value that is positive, slightly greater than 0 but positive, so that would be 2 divided by 0 plus equal plus infinity. So it is infinity in both cases. However, in the second case would be plus infinity. In the first one, it would be minus infinity because you have a minus sign in the denominator. And this means the following, that as x approaches 7 from the left, the function f of x would go to minus infinity. Okay? It would go to minus infinity, meaning that it would go like this. Meanwhile, when approaching the line, the vertical asymptote, x equals 7 from the right, as x approaches from the right, it would be 7 plus, which is slightly greater than 7. So 7 plus minus 7 would be 0 plus. So the function would go to plus infinity. Determine end behavior f of x equal minus 4x4 plus x. So what matters is the highest degree term within the equation, which is minus 4x4. For x going to plus minus infinity, it always approaches minus infinity, given that here the power of x is even, which means it's always positive, but multiplied by a negative term. So f of x for both negative and positive values of x approaches minus infinity. Find the oblique asymptote f of x equal x squared plus 2x plus 3 divided by x. Okay, we simply break it down. So it is equal to x squared divided by x plus 2x divided by x plus 3 over x as x approaches infinity. As x approaches infinity, 3 over infinity becomes 0, is annihilated. Then 2x divided by x, this becomes 2, and x squared divided by x is x. So we are left with x plus 2. Okay, because this term cancels out. As x approaches infinity becomes 0. So we are left with x plus 2. Hence, the equation of the oblique asymptote is y equal x plus 2. So at the end, in this module, we covered end behavior of functions, horizontal asymptotes, vertical asymptotes, oblique, dominant term analysis, infinite limits, growth rate comparisons, asymptotic approximations, and applications to science and computation. Asymptotic analysis provides a powerful framework for understanding the global behavior of functions. By studying limits, dominant terms, and asymptotes, we gain insight into how functions behave at large scales and near singularity. These ideas play a crucial role in calculus, differential equations, numerical analysis, engineering, and modern applied mathematics. 10. Function transformation and graph analysis. Now, we have already gone into function transformation in earlier chapters. So here, we mainly cover the graph analysis. And if something applies to function transformation, we're going to see it again anyway. But how to analyze a graph? How to sketch a function? When analyzing a function, we first need to identify parent function or functions. Actually, yeah, the parent function. Determine the transformations. Find the domain of definition for x. Find the range of y. So where the function is varying. For example, the range of sine x is between -1 and +1. Locate the intercept. For example, the y-intercept and the x-intercept, where the function clips the x-axis. Identify asymptotes, if any. Determine symmetry, such as in the case of even and odd functions. And analyze the end behavior. Finally, sketch key points or critical points. Analyze g of x is equal to 1 divided by x minus 2 plus 1. Parent function is f of x equal 1 over x. The transformations are the following. Okay, so it is of the form f of x plus h, where h is a positive number, h equal 2. So at first you have a right shift or a shift to the right of 2 units. Then plus 1. This is an upward shift of 1 unit. Okay, based on the parent function 1 over x. So upward shift of 1 unit and right shift of 2 units. This is where we got the right shift. Okay, also you have a vertical asymptote for x equal 2. Horizontal asymptote, which is limit g of x as x approaches infinity equal 1 over infinity 0 plus 1. So it is plus 1. Hence y equal 1 is a horizontal asymptote. The domain is x belongs to minus infinity all the way to 2. Okay, and from 2 to plus infinity, of course 2 being not included, or x exists in R minus the singleton 2. And the range y different than 1, meaning that it approaches y equal 1, but it never gets through it. G of x equal x minus 4 squared. These are review exercises. So here we shift right to 4 units, okay? 4 units right shift. And the vertex is 4, 0, which is the value for which g of x becomes 0. So x minus 4 equals 0, hence x equal 4. And its respective y value would be 0. So the vertex is 4, 0. Okay? And right shift of 4 units. So this is a parabola. By the way, the parent function is x squared. The original function would be like this. But the shifted function, which is x minus 4 squared, would be shifted 4 units, 3, 4 to the right. And the vertex for that is at 4, 0. And this is x minus 4 squared. Describe g of x is equal to minus x plus 3 squared. At first, it is of the form x minus h, with h being negative, h equal minus 3 for this sign to become plus. So you have left shift of 3 units. More than that, we have a flipping of the equation. So the curve is flipped downward. The mouth of the parabola is opened downwards. So the vertex is minus 3, 0, and shift of 3 units. So the graph of the function is, okay, so minus 1, 2, 3. This is the vertex, minus 3, 0. And the function is flipped downward, so it would be like this. Of course, for y equals 0, you can find the value for which, for x equals 0, okay, you can find at which height this parabola clips the y-axis. So for x equals 0, g of 0 is equal to minus 3 square, which is minus 9. So at y equal minus 9, this is not accurate here, of course. So, but at y equal minus 9, the function clips the y-axis or cuts the y-axis. Find the domain and range of g of x equal absolute value of x minus 2. Now, we know that for absolute x, the plot is the V form, okay? For x positive like this, for x negative like this. Okay. Absolute value of x minus 2, so minus 2 means that you have a downward shift, okay? Downward shift of minus 2, so the function would be located at minus 2. That would be its minimum value. So it is the same function except shifted downward minus 2. Now the domain of definition is on OR, meaning x exists, or f of x exists for x within minus infinity to plus infinity for all r, or we can write it as x belonging to the r values, all real numbers. But the range, as for the y variation, is between minus 2 being included, and plus infinity. So no values beneath minus 2. Minus 2 is the trough, or the minimum value, okay, which was found based on the analysis of the function, okay, being shifted 2 units downwards. Determine whether f of x is equal to x5 is even, odd, or neither. Okay, f of minus x is equal to minus x5 equal minus f of x. So it is an odd function. F of minus x is equal to minus f of x. In other words, this function would be symmetric in respect of the origin. Okay, this is not an accurate plot, just for visualization. Okay, just as an example, the function would be symmetric to each, to itself, in respect to the origin of the axis. Finally, okay, so here we studied different transformations. Actually, they were covered more extensively in another chapter. Reflections across the axis, stretches, compressions, also covered more in other chapters. Transformations, graph analysis techniques, this is the main part studied here. Symmetry of functions, domain and range after transformations, systematic graphing strategies. Function transformations provide a powerful framework for understanding entire families of functions. By mastering shifts, reflections, stretches, compressions, we can quickly analyze and sketch complex graphs while gaining deeper insight into behavior of mathematical models used throughout calculus, science, and engineering. 15 or 14, parametric functions and polar functions. Many curves encountered in mathematics, physics, engineering, and computer graphics also cannot be conveniently described by a single equation of the form y equal f of x. Instead, the coordinates of a point may depend on a third variable called a parameter. Likewise, some curves are more naturally described using the distance from the origin and an angle rather than rectangular coordinates. These alternative representations lead to parametric functions, polar functions. Parametric and polar representations are essential in calculus. Okay? So, also in physics, robotics, computer graphics, astronomy, mechanical engineering, electromagnetic theory, and differential equations, such as ODE. In this module, we study parametric equations, elimination of parameters, parametric graph analysis, polar coordinates, polar graphs, symmetry, and applications. Parametric functions. A parametric function expresses both coordinates as functions of a parameter t. X equal f of t and y equal to g of t. The parameter t is often interpreted as time. example, x equal t and y equal t squared. As t varies, the point traces a parabola. One of the applications that come to mind is the equation of a projectile, okay, where x would be equal to v0 times t. v0 is the launch velocity of the projectile, not missile, okay, not missile with thrust, but projectile. And y would be equal to minus 1/2 g, g being the gravitational acceleration, times t squared plus v0 sine theta t, which is the initial vertical velocity, if available. And t is the time parameter or time factor. Determine the point corresponding to t equal 3 for x equal t and y equal t squared. X equal t, so x is equal to 3 for t equal 3. Y equal t squared, so you replace t by 3 squared equal 9. Therefore, it is 3, 9. That's the point, having two coordinates x and y. Eliminating the parameter. To find the Cartesian equation, eliminate the parameter. So, given x equal t, y equal t squared. So, since t is equal to x, you simply replace t in the second equation. Okay, so t equal x, hence y is equal to t squared, which becomes x squared. Thus, the Cartesian equation is equal to y equal x squared. Eliminate the parameter x equal to t for y equal t plus 1. Okay, so we have two equations, one according to x, the other according to y. Okay, so in such case, t is equal to x divided by 2, and then you plug it back in y. So y is equal t plus 1, which is x over 2 plus 1. This is y. And this is how you eliminate the t parameter. Parametric representation of a circle. A circle of radius r centered at the origin can be written as x is equal to r cosine theta, or t, y equal r sine t, where t varies between 0 and 2 pi. Now, notice something. This is x, and this would be y. Now, x squared plus y squared should give us r squared, according to Pythagoras' theorem. So, x squared is r squared cosine squared t plus r squared sine squared t equal r squared as a common factor for cosine squared t plus sine squared t. Cosine squared plus sine squared is equal to 1, so equal r squared. For radius r equal 3, x equal 3 cosine t and y equal 3 sine t, for example. Show that x equal 5 cosine t and y equal 5 sine t represents a circle. Okay, we need to square both of them. So x squared equal 25 cosine t squared. Y squared 25 sine squared t, and x squared plus y squared is equal to 25 as a common factor, cosine squared t plus sine squared t, which is 1, equal to 25. Okay, using cosine squared t plus sine squared t equal 1. X squared plus y squared equal 25. Exactly, this is the radius of a circle. Actually, this is the equation of a circle, having the radius square root of 25 equal to 5. Motion along a parametric curve. When t represents time, x and y would be two functions that are described in respect of time. And these would be the motion functions, or like the position equations, okay, for both x and y. X would be the displacement or the range in respect of x, okay, in respect of the horizon. As for y, it would be the altitude, okay, the change of altitude in respect of time, such as in the example of the projectile, the motion or movement of the projectile. So this describes the motion of a particle. Velocity components are the derivatives of x and y in respect of time, which is the change rate of distance in respect of time. Let's say the distance had changed, or like the person had stepped 5 meters in 2 seconds, that would be 5 meters in 2 seconds. 5 over 2, which is 2.5 meters per second. That's the velocity. So Vx and Vy, Vx is the velocity in the distance, like in distance terms, and the velocity at x, okay, it would be the speed or the rate of change of distance on the x-axis. It is the derivative of x in respect of time. So is Vy dx, dy, the derivative of y in respect of time, or the rated change of the altitude in respect of time. As an example, x equal t and y equal t squared. The velocity Vx is equal dx over dt, which is the derivative of x in respect of t, equal 1 meter per second, for example, if the units are meters and second. dy over dt would give you the velocity in respect of y-axis, so it is equal to t. By the way, the difference between velocity and speed is that speed is a constant value, okay? For example, 5 meters per second, 10 meters per second, but the velocity is a function, okay? It's a function in respect of a variable t, a time variable that would change also. Find the velocity components for x equal 3t and y equal t3. Okay, so Vx is equal to dx over dt, derivative of x in respect of time, which is 3. Vy equal derivative of y in respect of time equals 3t squared. And of course, most of the time they won't be equal to each other because the motion on the x-axis would be different than that on the y-axis. As an example, for the projectile, it would be moving if given that there's no friction or drag from the air, okay? If it's in an empty space, the velocity in the horizontal direction would be the same, meaning that the shadow, if the sun is like casting the shadow from above of the ball on the ground, it would be moving in a uniform constant velocity, constant speed on the ground, okay, in the x direction. But meanwhile, in the y direction, in the vertical direction, it decelerates as it's going up, the projectile, and then once it arrives to the peak, it starts accelerating back again as it falls back to the ground. A point in polar coordinates is described by r theta, where r is the distance from the origin and theta is the angle, right, from the positive x-axis. Very convenient. Conversion formulas, so again, x equal r cosine theta, y equal r sine theta. So what is r? We know that x squared plus y squared is equal to r squared, right? So r is equal to square root of x squared plus y squared. And also you have tan theta, the tangent of theta is equal to the opposing segment divided by the adjacent segment, or y divided by x. Convert r theta equal 4 pi over 3 to Cartesian coordinates. Okay, x is equal to r cosine theta, which is 4 cosine pi over 3. Pi over 3 is 60 degrees. The cosine for 60 degrees is 1/2. Okay? Yeah, it is 1/2. So 4 times 1/2 equal to y equal r sine theta equal 4 sine pi over 3, which is 4 times square root of 3 divided by 2 equal to square root of 3. Hence, these are the coordinates in Cartesian forms. So x is equal 2 and y equal to square root of 3. As to converting from Cartesian to polar form, okay, given xy. Now we know that x is equal to r cosine theta, y equal r sine theta, and r is equal to square root of x squared plus y squared, given that x squared plus y squared is equal to r squared. So this is how you get r. As for theta, now tan theta is equal to y divided by x, which is the opposite segment divided by the adjacent segment on the trigonometric circle. Hence, theta is equal to arctangent of y divided by x, or tan to the power of minus 1, which is the inverse of the tangent of y divided by x. Convert 3, 4 to polar coordinates. Okay, so x equal r cosine theta, y equal, okay, so you have x and y. Okay, first, yeah, no need for these two formulas. We know that r is equal square root of x squared plus y squared, which is square root of 9 plus 16, or square root of 25 equal 5. R equal 5. As for theta, equal arctan of y divided by x, which is 4 over 3. So what is the angle in such case? Okay, you can evaluate the angle. On the calculator, you press shift tan of 4 over 3. Polar equations. A polar curve is defined by r equal f of theta, meaning it is the variation of the radius in respect of the angle. Okay? By the way, for instance, r equal theta would give you a spiral, because as theta increases, r starts increasing, okay, but the theta is turning around a center. So as theta keeps increasing, the radius keeps increasing as well, like a spiral motion. As an example, r equal 2 by itself represents a circle of radius 2. So it is simply a segment of radius 2 with no angle, because theta would be 0 in such case, okay? Because remember, it is r cosine theta, okay? So cosine 0 is equal to 1. Now, r equal 1 plus cosine theta, another example, this represents a cardioid. So what is a cardioid? This function beneath has the form of r equal a times 1 plus cosine theta, where a is equal to 1. This is how we draw it. This is how we draw the function. Actually, let me vacate more space for this function. R equal a times 1 plus cosine theta, and you measure a here, a distance, then a from beneath, okay, and double a across. This is 2a. This is the angle theta, and this is r, by the way, okay. The r is the distance, okay, the radius. So this is the cardioid. So it starts from 0, passes by first a, then goes to a, then comes back, and then clips 0 again. It's like a cardiac shape, like a heart. This is why it's called a cardioid. In our case, a is equal to 1. So for a equal 1, again, you measure from beneath 1, 1, minus 1, rather. Okay, so a above, a below, and 2a horizontally, which is 2. And this is the shape of the cardioid. You start from 0, it clips 1, goes to 2, then comes back, clips minus 1, and goes back here. Describe the graph r equal 4. This is simply a distance from 0 to 4. So it's like a line, okay? From the origin of distance 4, and you can consider it as the radius of a circle equal to 4. Symmetry helps simplify graphing. So when we replace theta by minus theta, we can draw a part of the function, okay, and the other part would be symmetric to it. For example, replace theta by pi minus theta. This is an origin symmetry, so this is theta, and this is pi minus theta, would be like that. So symmetric in respect of the y-axis. Okay? Determine whether r equal cosine theta is symmetric about the polar axis. Okay, so we know that cosine theta is equal to cosine minus theta. Hence, it is symmetric. So r equal cosine minus theta equal cosine plus theta. It is symmetric about the polar axis. Example, r equal to cosine theta. Convert to Cartesian form. Let's multiply by r both sides. And we know that r squared is equal to x squared plus y squared, remember. So if you multiply both sides by r, you end up with r squared is equal to r cosine theta, which is equal to x squared plus y squared. Now, okay, so x is equal to r cosine theta, right? What we have here is 2x. So x squared plus y squared is equal to r cosine theta, which is 2x. We replaced r squared by x squared plus y squared, and 2r cosine theta with 2x. So you remove 2x to the left, we end up with x squared minus 2x plus y squared is equal to 1. Hence, x minus 1 squared, okay, which is x squared minus 2x plus 1, right? And we, plus 1, we need to remove it by adding a minus 1. Plus y squared is equal to 0. So this minus 1 that cancels the plus 1 that is generated by x minus 1 squared is removed to the right of the equation. So we end up with x minus 1 squared, okay, minus 1 plus y squared is equal to 0. So x minus 1 squared plus y squared is equal to 1. Convert r equal 3 sine theta to Cartesian form. Okay, so again, we multiply both sides by r, and we get r squared is equal to 3r sine theta. R sine theta is y, right? So r squared is equal to 3y. R squared is equal to x squared plus y squared. We know that, which is equal now to 3y. So x squared plus y squared minus 3y is equal to 0. And we need to reshape it into the form of a circle equation. So x squared plus y minus 3 over 2 squared equal 9 divided by 4. Because y minus 3 over 2 squared is y squared minus 3y. Okay, why is that? Because minus 2 times y times minus 3 over 2. This is where we've gotten that from, okay? Correct? So minus 3y plus 9 over 4. So we need to negate by minus 9 over 4, adding it to the equation, and you place it on the outside of the equality. Polar curves, rose curves are given by r equal a cosine n theta, or r equal a sine n theta. If n is odd, n is the number of petals, so n petals. If n is even, 2n petals. Okay, you have 2n number of petals. For example, how many petals does r equal cosine 3 theta have? N equals 3, it is an odd number, hence 3 petals. Now this is how you draw it. So 3 petals. The first one is for theta equals 0. Then the second one would be like this. Third one would be like this. They are apart from each other of 120 degrees. Okay, so the same angle, meaning that 360 is divided by 3. This is the angle by which each petal is apart from the other. Another note is that the distance here is 1 for the 3 petals. Polar curves, spirals. One important spiral is r equal a theta, called the Archimedean spiral. As theta increases, r also increases. The distance from the origin increases as well, creating a spiral. Describe r equal to theta. The radius grows linearly with angle, therefore Archimedean spiral. This one in the sketch is r equal 3 theta. You notice that as theta increases, the radius, which is the distance from the origin, also increases linearly and by a factor of 3. Applications of parametric and polar functions include planetary motion, robotics, computer animation, radar systems, navigation, mechanical design, electromagnetic fields, and fluid dynamics. An example for that is satellite orbiting may be represented parametrically as x equal a cosine t and y equal b sine t, forming an ellipsoid. Comprehensive review exercises, and I will get back to how to plot polar equations such as cosine 3 theta, cosine n theta, 1 plus cosine b, something like that. Okay, we will get back to that. So exercise 12, eliminate the parameter x equal t plus 1, y equal to t minus 3. So t would be equal to x minus 1, and we replace this value of t in the second equation. So y equal 2 times t, which is x minus 1 minus 3, equal 2x minus 5. This is how you can get rid of t. Convert r theta equal to pi over 2 to Cartesian coordinates. Okay, so x is equal to r cosine theta, which is 2 times cosine pi over 2. Cosine 90 is 0, so x equals 0. Y equal r sine theta, which is 2 sine pi over 2. Sine 90 degrees is 1. Hence, it is equal to, and the coordinates are 0, 2. Convert 0 minus 5 to polar coordinates. Okay, so 0 minus 5, we need them as polar. R is equal to square root of x squared plus y squared, as you remember, which is square root of 25 equal 5. This is the radius. As for theta is equal to arctan y over x, or tan minus 1 of y, which is minus 5, over x, which is 0. Okay, this would be, okay, it would give us 3 pi over 2, because, you know, since sine over cosine, right? Cosine of which angle is equal to 0? That would be a 90 degrees angle. As for which sine would give us minus 5 over 0, the angle is 3 pi over 2. Determine the radius of r equals 7. Solution 7, as simple as that. Now let's graph polar functions, starting with the first form, which is r equal a plus b cosine theta. Okay, for example, r equal 1 plus 3 cosine theta. Now here we have different rows. If a over b is less than 1, in other words, a less than b, then what we get as a graph is the limaçon. Okay, so what is a limaçon, or what does it look like? First of all, you start from point 0. Okay, now you step a distance of a up and down, and these are the 2 points where this limaçon intersects with the y-axis. Then you rotate. Okay, so you start here, you rotate all the way to a distance which is a plus b, an absolute value. Okay, so this distance is 3 plus 1 equal 4. That would be the outer round, the outer circle. Then once you get back, okay, you need to intersect with minus a, which is minus 1 here. Then you rotate on the inside and you draw the inner circle of a distance a minus b. So once again, let me break it down. We need to establish what you can call the critical or essential points. First point is plus a, second minus a, okay? Then you go a distance of a minus b in absolute value, which is 2. That would be the boundary of the inner circle. Then a plus b, which is 1 plus 3 equal 4. And this is how you draw. So you start from 0, you go up to a, then you go and complete the round all the way to a plus b. Then you go down again. After that, you intersect with minus a. Then you go in to complete the inner circle, which is at a distance a minus b. So to make it simple, you go a, then you complete all the way to a plus b. Then you go, then intersect with minus a here. You go in, intersect with 0, then you complete the inner circle of a distance a minus b. For r equal a minus b cosine theta, okay? So in such case, it is the same concept, except the graph would be inverted, okay? So it would be reflected in respect of the y-axis. So notice here, you have, instead of a minus b, you should have minus a minus b. So a minus b, but in the minus, in the negative area, in the negative section of the system of the axis. So here, minus a minus b. So a minus b in absolute value is 1 minus 3 in absolute value equal plus 2, okay? However, it is multiplied by minus, so it is the negative area, which is minus 2. Then you have a plus b, okay? Now a plus b, yeah, b should be considered as plus 3 here. We're not like subtracting 1 plus minus 3. So you can consider that it would be like a plus b in absolute value, then multiplied by minus, which is minus 4. And here you have a, here you have minus a. So it is minus a minus b, and minus a in absolute value plus b in absolute value. You start from 0, you go up to plus a, then you complete the round. So you have plus a, you go up, then complete plus a, turn around to minus a in absolute value plus b in absolute value. Then you intersect at minus a. Then at the origin, we go another round. That would be the inner round, which is minus an absolute value a minus b. And that would be the graph. So it is 1 plus 3 cosine theta, but inverted in respect of the y-axis. Another form is r equal a plus b cosine theta, with a being equal to b. So as an example, r equal 3 plus 3 cosine theta. Now technically, this would mean that a over b is equal to 1. And in such case, the graph would be what is called a cardioid, because it has the shape of a heart. And this is how we draw it. So you have the usual plus a above, minus a below, and to the right, we don't have an inner loop, but an outer loop, okay? That would be the external loop, which is equal or have a distance from the y-axis equal to a. Now, effectively, this would be a plus b, but given the fact that b is equal a in this case, so it is equal to a. And this is how you draw it. You start from 0, from beneath or from the above. You can draw it both ways. You intersect with the y-axis at y equal a. You go around all the way, then you clip the x-axis at x equal to a, which is in our case 6, right? And a is equal to 3. Minus a, of course, is equal to minus 3. You go around, then you clip the y-axis at y equal minus 3, all the way, then you end up at the origin again. r equal a plus b cosine theta, with a greater than b this time. For example, r equal 4 plus 3 cosine theta. So a over b is greater than 1. In such case, you would get a dent, not a cardioid, like a circle with a dent to it to the left. Okay, so it would have this following shape. Now here you have, as usual, a and minus a. To the right, a plus b, which is 7 in such case. And here, this is how you draw it. So you can start from the 7 all the way to a. Now, instead of going to 0, okay, you continue all the way here to create a dent. Then you descend to minus 4, and the distance of the dent is a minus b. So this is 1, okay, or minus 1 rather. But the distance in terms of distance, it is a minus b. This is how far the dent is from the y-axis, of course. r equal a plus b sine theta. Here we have a similar concept like cosine theta, except the graph would be turned 90 degrees anti-clockwise. So for instance here, you have a and b just like in the case of cosine theta. So a over b is less than 1, so you have a limaçon. This limaçon starts from 0, except it turns upward instead of to the right. So, and by the way, the distances, first, the one for the inner circle is a minus b, which is 3 minus 1 or plus 2. And for the outer circle or outer loop, a plus b, which is plus 4. 3 plus 1 equal to plus 4. And you start turning from 0 all the way up to a plus b. Then you clip the y-axis at 0 again, and you start with the inner loop having a distance from 0, a minus b. r equal a cosine n theta. In this case, a at first would be the radius, which means it is the distance from the origin all the way to the edge of each petal. So you have, for example, from this point, from this edge all the way to 0, for the 3 petals over here in this graph is equal to a. It's like a radius, except it's not here for a circle, but it is the distance from the origin to the edge of each petal. And n is the number of petals only in the case where n is an odd number. So n here is 3, odd number, hence you have 3 petals. If it's an even number, such as 4, 2 cosine 4 theta, for example, in such case, you would have 4 times 2 or 8 petals. So the number of petals would double up. Again, here we have 3 petals. Now, concerning the width of the petal. So here, to get the width, we need to evaluate the angle formed by the 2 edges of each petal, starting with the first petal, the one to the right. Okay, so you have cosine 3 theta, right? Now we know that cosine, cosine pi over 2 is equal to 0, correct? So for pi over 2 cosine is equal to 0, and r is equal to 2 times cosine 0, which would be 0. So for which values of the angle the radius would be 0? Radius 0 is here at this point. You place 3 theta is equal to pi over 2. So we need to find the value of theta for which the angle would be pi over 2 and cosine would be 0. Hence the radius r would be also 0. That would be at the vicinity of the origin of the axis. So 3 theta is equal to pi over 2. Hence theta is equal to pi over 6, which is 30 degrees. And that would be for each of the petals. So you have 30 degrees, okay, for each petal, and the distance from one petal, the angular distance from one petal to another, since we have 3 petals, is 360 degrees divided by 3, which is 120 degrees. For the second case, which is when you have an even number multiplying theta, in such case, given the fact that n is even, you would get 8 petals, okay? So twice the number of petals for an even value of the angle. So 4 theta gives you 8 petals, each one having a radius 2. So you notice here you have 2 for each petal as a radius. Now, what is the angular value, or let's say it this way, what would be the angle between the 2 edges of the petals? So where is the origin? This is the origin, right? We need to measure this angle for the first petal at least. Okay, so for r equals 0, when is r equals 0? When cosine is equal to 0. That would be cosine pi over 2 equal to 0. Here you have cosine for theta, so should be equal to 0, which means 4 theta equal to pi over 2. So you place 4 theta equal pi over 2, theta equal pi over 8, which is 360 degrees, 180 degrees over 8. So around, 2 times 20 degrees something, okay? So that would be around 20 degrees plus or minus, or like slightly above 20 degrees. Finally, module summary. In this module, we studied parametric functions, elimination of parameters, parametric representation of curves, particle motion and velocity, polar coordinates, conversion between Cartesian and polar systems, polar equations, conversion between Cartesian and polar, okay, symmetry of polar graphs, polar circles, roses, spirals, applications in science and engineering. Parametric and polar representations provide powerful alternatives to standard Cartesian equations. They allow us to describe complex curves, rotational motion, periodic phenomena, and geometric structures that arise naturally in advanced calculus, physics, engineering, and computer graphics. Differentiability of functions. Differentiability is one of the most important concepts in calculus. It formalizes the idea of a function having a well-defined instantaneous rate of change at a point. The derivative measures instantaneous velocity, growth rate, slope of a tangent line against a curve, sensitivity of one quantity to another, and local behavior of functions. It is fundamental to optimization, physics and engineering, economics, machine learning, differential equations, and numerical analysis. In this module, we study the definition of differentiability, geometric interpretations, differentiability versus continuity, derivative rules, higher order derivatives, and practical applications. Definition of the derivative. Let f of x be a function. The derivative of f at x equal a is defined by the following. F prime of a is equal to limit fa plus h minus f of a divided by h as h approaches 0, provided the limit exists. This is called difference quotient. But where did we get that from? You see, the derivative is actually the slope of the tangent against the curve at a specific point. Okay? So let's say you have a function like this one, and for x equal, for example, let's say you have an x here, and after a step x plus h, we're checking how much the function has changed, meaning, let's say this is the derivative, okay? So the slope of the tangent means then the slope of the tangent is tangent theta, which is the vertical variation delta y divided by the horizontal variation delta x. Okay, so if we magnify it, this is the tangent here against the curve. So you have x variation, this is the x, and this is x plus h after an h step, and this is, okay, this is on the x-axis, and this is the y variation at that point, which is y2 minus y1, or y2 being f of x plus h minus y1, which is f of x. So the derivative is the limit of the function, okay, as h approaches 0, meaning as the distance becomes so minimal between x and x plus h. So the step is very small. What is the rate of change? Okay, so what is tan theta for f of a plus h or x plus h minus f of x divided by x plus h, which is x2 minus x1, okay, x plus h minus x. X minus x0, so we are left with h in the denominator. Hence, the limit, okay, it is equal to, again, y2 minus y1. y2 is f of x plus h. Okay, so at x plus h, what is the f value? What is the altitude of the tangent? Minus f of x, which is the value for x, divided by the distance, okay, which is x plus h minus x. So basically, the tangent is the rise over run, how much the function is rising, divided by the horizontal distance being traveled during that rise. Okay, so let's say, consider it like a plane. Okay, a plane is rising 2 meters each 3 meters. Okay, so that would be rise over run, which is 2 over 3. That would be the slope of the tangent. Okay, the same way here, it is fx plus h minus f of x, a step behind, divided by the length or the distance of the step, which is x plus h minus x, or h. This is the span, horizontal span. Okay, exercise 1, using the definition, find f prime of x for f of x is equal to x squared. Remember, the formula is the derivative f prime of a or x is equal to limit f of x plus h minus f of x divided by x plus h minus x, or simply h, since x, cancels out automatically. So what is f of x plus h? You replace x in the function with x plus h, which is equal to x plus h squared minus x squared divided by h. So equal x squared plus 2xh plus h squared minus x squared divided by h. Okay, now x squared minus x squared cancel out. We are left with 2xh plus h squared divided by h equal 2xh divided by h plus h squared divided by h, which is h. Now h is a very small value, so it is equal to 0. And we are left with 2xh divided by h. You factor out h, and this is the answer. The derivative for that function is 2x. Let's examine it again, given that the solution here is more neat than what I've written personally. So f prime of x is limit as h approaches 0 of f of x plus h minus f of x divided by h. F of x plus h is simply obtained by replacing x within f of x by x plus h. Okay, so it is x plus h squared minus f of x, which is x squared divided by h, equal limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared. Now these two cancel out, and we are left with limit as h approaches 0 of 2xh plus h squared divided by h equal to x plus h. H is so small, close to 0, so the solution is 2x. We are left with 2x. Therefore, f prime of x is equal to x. Again, the geometric meaning of the derivative, it is the slope of the tangent line to a curve for y equal f of x at x equal a. So the tangent line has slope m equal f prime of a. Example, f of x is equal to x squared, x equals 3. F prime of 3 is equal to x for x equal 3, which is 6. So the slope is 6, which is the ratio between the rise over the run. How much elevation the function is getting in respect or compared or divided by, in other words, technically speaking, the distance traveled during that rise, during that elevation. Find the slope of the tangent line to f of x is equal to x squared at x equals 5. So f prime of x is equal to x, f prime of 5 equal 10. Differentiability implies continuity. So if a function is differentiable at a point, then it is continuous there as well. Symbolically, differentiable also leads to continuous, okay? If a function is differentiable at a point, then clearly and automatically it's continuous. However, continuity does not necessarily imply differentiability. As an example, f of x is equal to the absolute value of x is continuous at 0, but not differentiable over there. Can a function be differentiable but discontinuous? No, because differentiability always implies continuity. What are the non-differentiable functions? A function may fail to be differentiable because of corners. For instance, for f of x equal to x, okay, this had a corner. This is the v function, if you remember. That's why it wasn't differentiable. Cusps, vertical tangents, and discontinuities. These can prevent the differentiability of a function. And it makes sense, by the way, given that at a corner you cannot have a tangent because it's a corner. It has two different sides where there's no way you can place a tangent against that function. Corner example, f of x is equal to x in absolute value. At x equals 0, okay, so you have the left slope is minus 1, which is like this, and the right slope is plus 1. This is the shape of it. And this is at x equals 0. Therefore, the derivative does not exist because it has two different slopes from left to right. So, f of x equal x in absolute value is not differentiable because it has two different slopes to the right and to the left of 0. Basic differentiation rules. Constant rule, derivative of a constant in respect of x is equal to 0. Why? Because there's no change. There's no variation, okay? So, let's say you have f of x is equal to 3. The function always will have an altitude of 3, so it's not changing. It's constant throughout x. Therefore, its derivative is equal to 0 because the derivation gives us the change, the rise or the climb of the function. And it is the rate of change of altitude, technically speaking. Power rule, derivative of x to the power of n is equal to n times x to the power of n minus 1. For example, x3 derivative is equal to 3 times x times 3 minus 1, which is 3x squared. Constant multiple rule, so derivative of c f x is equal to c times f prime of x, meaning that the constant is removed to the outside and you derive the function that is made of variables purely. Differentiate f of x is equal to 7x5. Let's apply the power rule. Now, 7 is a constant, so it's irrelevant. Okay, you multiply by 7 from the outside, then x5 as a derivative becomes 5x4. So, times 5x4 equal 35x4. Sum and difference rules. Derivative of a sum is equal to sum of derivatives. So, f prime of x plus g prime of x is equal to the derivative or differential of f of x plus g of x. Also, same thing for the subtraction. So derivative of f minus g is equal to f prime minus g prime. Differentiate f of x is equal to x3 plus 4x squared minus 7x plus 2. We simply differentiate each term on the side, okay? So x3 is 3x2, 4x2 is 8x, then minus 7x gives us minus 7, and the derivative of a constant 2 is 0. And you add them up, so it is equal to 3x squared plus 8x minus 7. That's the derivative. The product rule. Y is equal to f times gx. Then the derivative for that product, y prime, is equal to f prime times g plus f times g prime. Okay? So let's differentiate f of x is equal to x squared times x3 plus 1. Okay, so the first term is u is equal to x squared. Second term is v is equal to x3 plus 1. According to the formula, the derivative is u prime v plus u v prime. Okay, u prime is the derivative of x squared is equal to x. V prime is 3x2 plus 0. So u prime v times uv prime is equal to x times x3 plus 1 plus uv prime x squared times 3x squared. So 2x times x3 plus 1 plus x squared times 3x squared equal, let's develop it, 2x4 plus 2x plus 3x4 equal 5x4 plus 2x. The quotient rule. Y is equal to fx divided by gx. We'll call it f and g for simplicity. So y prime, the derivative, is equal to f prime g minus fg prime divided by g squared. So differentiate f of x is equal to x squared plus 1 divided by x. Let's consider u is equal to x squared plus 1, v is equal to x, u prime is equal to x, and v prime is equal to 1. So it is u prime times v, which is 2x times x, minus uv prime, which is minus x squared plus 1, divided by v squared, which is the denominator square, which is x squared. So it is equal to 2x squared minus x squared minus 1 equal x squared minus 1 divided by x squared, and this is the derivative. Chain rule. Y equal f of gx when we have two nested functions. So dy over dx is equal to f prime gx times g prime of x. So it is the derivative of f multiplied by the derivative of the inside of f, which is g prime of x. As an example, let's differentiate f of x is equal to 3x plus 1 to the power of 5. So this is of the form u to the power of 5, right? The inner function is 3x plus 1. So it is u5 prime multiplied by the inner function, which is u prime, equal 5 times 3x plus 1 to the power of 4 multiplied by the derivative of u, which is 3, which is 15 3x times 3x plus 1 to the power of 4. So we considered as if 3x plus 1 was u to the power of 5 is equal to 5 times u4 multiplied by the derivative of u itself, which is derivative of 3x plus 1. What is the derivative of 3x plus 1? It gives us 3. So it is 3 times 5u4, which is 15u4, or 15 times 3x plus 1 to the power of 4. Higher order derivatives, meaning it is the derivative of a derivative. It's called derivative of higher order, which means that you derive or you differentiate the function twice. That would be the second or third derivative. Now, the second derivative is very beneficial for us because it would give you the concavity of the function, meaning that when the concavity is upward, okay, the second derivative would be positive, and you would have a trough, okay, like a low point, a minimum. But when the second derivative is negative, it means that it is descending. The concavity would be downward, and in such case, you would have a peak or a local maximum. It is called a local maximum on this curve. The first one for f of x greater than 0 would be called a local minimum, like a dip, a trough. Example, f of x is equal to x4. First derivative is 4x3. Second derivative is 3 times 4, 12x squared. Third derivative, 2 times 12, 24, times x to the power of 2 minus 1, which is x, okay? Fourth derivative, 24. Of course, the fifth derivative becomes 0. Find the second derivative of f of x is equal to x3. First one is 3x squared. Second one is 6x. Straightforward. Velocity and acceleration. By the way, the velocity is the first derivative of the displacement function in respect of time. So let's say that s is the position. The first derivative in respect of time of the position gives us the rate of change of distance in respect of time. In respect of time. Which is called technically the velocity. Now, the rate of change of the velocity itself in respect of time would be the second derivative, also called the acceleration. So the acceleration is the second derivative of the position in respect of time, or the derivative of the velocity in respect, first derivative of the velocity in respect of time. Okay, this is how we get the acceleration and the velocity in mechanics. Given s of t is equal to t3, find velocity and acceleration. So velocity v of t is equal to derivative of s in respect of t, or s prime, the first derivative, equal 3t squared. Acceleration is the second derivative, so it is the derivative of the velocity. Okay, so it would be v prime t, or s second t equal 6t. So hence, the velocity is equal to 3t squared and the acceleration is equal to 6t. Implicit differentiation. Sometimes functions are not solved explicitly for y. This is where you get into, for example, differential equations. So x squared plus y squared is equal to 25. We need to differentiate both sides. So first side is 2x. Second side is 2y in respect of, okay, 2y times dy over dx equal 0. So now, why is the second side 0? Because we have a constant. So we end up with 2x plus 2y dy over dx. Hence, dy over dx is equal to minus x over y. Because simply, okay, so it is 2y dy over dx is equal to minus 2x. You can get rid of the 2, and then you divide by y in the second part. Dy over dx is equal to minus x over y. Hence, okay, what is the value of y? We integrate, okay? In such case, we integrate. But here, okay, so the derivative of y in respect of x is equal to minus x over y. As an example, dy over dx for x squared plus y squared equals 16. So it is 2x. This is the derivative of x, okay, plus 2y dy over dx equal 0. So dy over dx is equal to 2y dy over dx is equal to minus 2x. So dy over dx is equal to minus x over y. And that would be the answer. Review exercises. F of x is equal to 4x7. F prime of x would be 28x6. F of x is equal to x squared plus 5x. So f prime of x is equal to x plus 5. fx is equal to 1 over x. So f prime of x is equal to u prime v minus u v prime divided by v squared. And there's a shorthand to it. It is equal to minus 1 over x squared. Okay? When you have such a function. Okay. Actually, by the way, 1 over x is x to the power of minus 1 if you move it from the denominator to the numerator. So its derivative becomes minus 1 times x minus 1 minus 1, which is x to the power of minus 2 multiplied by minus on the outside, or minus 1 over x2. Differentiate f of x is equal to x squared plus 1 to the power of 3. So let's say u is equal to x squared plus 1. Then you have u3 times u prime, derivative. So it is equal to 3 times x squared plus 1 squared multiplied by the derivative of u, which is 2x. So it is equal to 6x times x squared plus 1 squared. And this is the final answer. So again, u prime is the derivative of x squared plus 1, which is 2x, multiplied by 3 times u to the power of 2. What is u? It is x squared plus 1. So 2x times 3 times x squared plus 1 squared, which is 6x times x squared plus 1 squared. Find f second of x, second derivative of x. So for f of x is equal to x to the power of 4. F prime of x is equal to 4x3. F second of x is 12x squared. And by the way, it is positive, so the concavity is opened up and you have a local minimum. At the end, so in this module we studied definition of differentiability, derivative as a limit, geometric interpretation of derivatives, differentiability versus continuity, non-differentiable functions, basic function rules, product rule, quotient rule, chain rule, higher order derivatives, velocity and acceleration, and implicit differentiation. Differentiability provides a mathematical framework for mechanical engineering for different applications, and for measuring change through derivatives. We can analyze motion, optimization, growth, countless physical phenomena. The derivative is one of the most powerful tools in mathematics and forms cornerstone of differential calculus and other applications. Applications of derivatives. So, derivatives are much more than computational tools. They allow us to analyze the behavior of functions, determine maximum and minimum values, study motion, approximate complicated functions, solve practical problems in science, engineering, economics, and physics. In this module, we explored the most important applications of derivatives, including tangent and normal lines, rates of change, related rates, increasing and decreasing functions, critical points, local and absolute extrema, optimization, concavity, inflection points, curve sketching, linear approximation, and Newton's method. Equations of tangent and normal lines. For a function y is equal to f of x, the slope of the tangent line at x equal a is m equal f prime of a, which is also given by the equation y minus y0 is equal to f prime of a multiplied by x minus x0, where y0 can also be written as f of a, which is the value of the function f at x equal a, and x0 is equal to a. This is the equation of the tangent. The normal line is perpendicular to the tangent line. The slope is given by minus 1 divided by f prime of a. Okay, provided f prime of a is different than 0. Example, find the tangent line of f of x is equal to x squared at x equal 2. So let's apply the formula. First of all, let's find f prime of x for x equal 2. This is equal to x when x is equal to, okay? For x equal to, equal 4. This is f prime of a. So the tangent or the equation of the tangent is given by y minus y0 is equal to f prime of a times x minus x0. Okay, so y0 is f of a, f of 2, in other words, which is 4. So y minus 4 is equal to f prime of a, which is 4 also, multiplied by x minus x0, x0 being x equal 2. Okay, so it is equal to, you remove minus 4 to the right, it becomes plus 4. So it is 4x minus 8 plus 4, or 4x minus 4. This is the equation of the tangent line against the curve, x squared at x equal 2. So graphically, this is y equal x squared. Let's say this is x equal 2. This is the tangent against the curve, and this is its equation. It is 4x minus 4. Tangent line to f of x equal x3 at x equal 1. So it is y minus y0 equal f prime of a times x minus x0. A and x0 are the same thing, actually, okay? So y0 is f of 1, f of a, which is 1. x0 is equal to 1. Derivative f prime of x is equal to 3x squared. At x equal 1, it is equal to 3. So y minus 1 is equal to 3 times x minus 1. Y is equal to 3x minus 3 plus 1 equal 3x minus 2. And this is the solution for it. So f prime of x is equal to 3x squared. F prime of 1 is equal to 3. Okay, so the point is 1, 1. Hence, y minus 1, y minus y0 is equal to 3 times x minus x0, 3 being f prime of x0, or a, the same thing, which is 3 times 1 squared equals 3. Hence, y equals 3x minus 2 is the equation of the tangent against x3 at x equal 1. Instantaneous rate of change. The derivative measures the instantaneous rate of change for the velocity, for example, or the acceleration. If y equal f of x, then dy over dx gives how rapidly y changes with respect of x. Find the instantaneous rate of change of f of x is equal to 5x squared at x equal 2. First, the derivative of f of x is equal to 10x, okay, 2 times 5, multiplied by x to the power of 2 minus 1, which is x. Okay, so it is 10x. So f prime of x is equal to 10x. Now, for x equal to, you replace x by 2 and you get 20. So let's say it is a formula for a distance being traveled in respect of time. At t equal 2 seconds, the velocity would be 20 meters per second. Velocity and acceleration. So s, let's say it represents the position. V of t is the first derivative of s in respect of time. The acceleration is the second derivative of s in respect of time. Of course, s should be defined in time, meaning it should be a parametric equation that has t as a variable. For example, t3 plus 1. It would be something like that. Example, s of t is equal to t3. So v of t equal s prime of t, which is 3t squared. Acceleration of t is equal to s second of t. So we derive the velocity in such case equals 6t. Given s of t is equal to t to the power of 3 minus t, find velocity and acceleration. Velocity is the first derivative of s in respect of time equal 6t squared minus 1. Acceleration is the second derivative of t, which is the derivative, we derive s prime of t again, we end up with 12t. And these are the equations for the velocity and acceleration respectively. Related rates. Related rates problems involve differentiating equations with respect to time. Suppose a equal pi r squared. Differentiate with respect to time, so it is 2 pi r, in case r is the time, okay, times dr over dt. The radius of a circle increases at dr over dt equal 3, okay, centimeter per second. Find dA over dt when r equal 5. So the solution is given by dA over dt is equal to 2 pi r multiplied by dr over dt, and based on the proposition of the problem, the radius increases at dr over dt equal 3, okay? It increases by 3 centimeters. The increase is dr over dt, okay, when r is equal to 5. So 2 pi times r, which is 5, times the increase, which is dr over dt equal 3, based on the proposition of the problem, equal 30 pi, hence 30 pi centimeter square per second. Increasing and decreasing functions. The function would be increasing, meaning that the tangent would have a positive slope, in other words, technically, and the function would be increasing. It would be climbing when the derivative of that function at a specific point would be greater than 0. Now, the opposite for that the derivative of the function would be negative, which would mean that the function would be decreasing or plunging. Example, f of x is equal to x squared, f prime of x is equal to x. Now, in such case, the derivative is dependent on the value of x. So if x is greater than 0, then f prime of x would be positive, which means that the slope of the tangent against the curve would be positive. So the curve itself would be climbing. It would be rising in altitude, okay, on the y-axis. Meanwhile, for x negative, the derivative would be negative. So the slope also would be negative. It would have a negative angle, which means that this is what a negative angle would look like, okay? So it would have, okay, this is the curve here. It would have a negative angle in respect of the horizon of the x-axis, which means that, as you notice, the function in such case would be declining. Therefore, what would be happening is that this function would be going down. It would be plunging downwards instead of, so it would be decreasing towards 0 instead of increasing. Determine where f of x is equal to x3 is increasing or decreasing. So f prime of x is equal to 3x squared, which is always positive, because for whatever value of x, this derivative is always greater than 0, so the slope would always be positive, okay, for every value of x except 0. At 0, it would be a flat line, like horizontal or parallel to the x-axis, so the angle in such case for x equals 0 would be 0. After 0, it would be increasing, so the function would be climbing towards infinity. So, except at x equals 0, the function is always increasing towards infinity. And this is whether x is negative or positive. Critical points. A critical point occurs when f prime of x is equal to 0, which means at that point, the function is neither climbing nor descending, and the tangent is at that point parallel to the x-axis, so the slope is 0. So it's like what is called, you would have either a local minimum or a local maximum, but there would be like a change of direction in the curve. So fx is equal to x squared, f prime of x is equal to x, so the critical point is at x equal 0. Find the critical points of f of x is equal to x3 minus 3x. Now, first we differentiate, so f prime of x is equal 3x squared minus 3. And we need to find for which values of x the derivative is equal to 0. In other words, the slope of the tangent would be 0. The tangent would be parallel to the x-axis, and the curve at that point, or these points, if there are many, would be neither climbing nor descending. So it would be a flat line, okay? It would be leveled, just like an airplane that is leveled, okay? It has descended, now it's climbing, at some point it would have a trajectory where the tangent would be parallel to the x-axis. The first derivative test determines whether a critical point is a maximum or a minimum. Okay, so if it's increasing, you have a local minimum. If it's decreasing, meaning that it was above and then it's plunging, you have a local maximum. Okay, so when moving from plus to minus, meaning that you have a local maximum. When moving from minus to plus, from a negative side to a positive side, meaning that you're increasing, but you're increasing from where? From a local minimum, from a trough. It's like you are rising from a ditch. Yes, you are rising, but you are in a ditch, in a place that is a low place. So the same concept applies here. Classify the critical points of f of x is equal to x squared. F prime of x is equal to x. Now for x negative, f prime of x is less than 0. Okay, so the function would be decreasing. For x greater than 0, f prime of x is greater than 0. Okay, the function would be increasing. Classify the critical point of f of x is equal to x squared using the second derivative test. F prime of x is equal to x. Okay, now the critical point is x equals 0. F second of x is equal to, okay, so first of all, it is positive, meaning that the concavity would be like that. Okay, because it's rising. So the function is concaved up. Hence, since it is rising from a lower place, it has a local minimum, given that f second of 0 is equal to, which is a greater value than 0. Okay, it is a positive value. Hence, a local minimum. Optimization problems. Optimization seeks maximum or minimum values. Find the maximum area of a rectangle with perimeter 20. Okay, so let 2x plus 2y equal 20. Y is equal to 10 minus x. The area is equal to x times 10 minus x, which is one of the sides multiplied by y. Okay, x times y. So it is 10x minus x squared. Let's get the derivative. Okay, so it is equal to 10 minus 2x. So x is equal to 5 for a prime equals 0. You have 10 minus 2x equals 0, x equal to 5. Thus, y equal 5, the maximum area is 25. Find the dimensions of a rectangle with perimeter 16 having maximum area. Okay, so we know that the perimeter is x plus x, right? Plus y plus y. X being the width if you want, and y being the length of the rectangle. So 2x plus 2y is equal to 16. Okay, then what is y? 2y is equal to 16 minus 2x. So y equal 8 minus x. The area then is given by a times x, which is 8 minus x. This is y. I'm sorry. Okay, so area is y times x, which is 8 minus x times x, or 8 minus 2x. Okay, so a prime is equal to 0, x is equal to 4. Hence, this is 4 times 4. Okay, this is the area, 4 times 4. So for y equal 4. Concavity, and we have already explained this concept. So concavity is obtained by getting or evaluating the second derivative of a function. So if the second derivative of a function is positive, f second x greater than 0, then the function is concaved up, meaning that it's rising from beneath to an above level. In other words, the mouth is opened up and it has a local minimum. Meanwhile, if the second derivative of f is negative, less than 0, then it's concaved down, which means that it is descending, but also it has a local maximum in such case. Okay, local maximum. Let's determine the concavity of f of x is equal to x2. So f prime of x equal to x, f second derivative is equal to 2. Greater than 0, okay? Right? It is positive, hence it is concave up. And basically, this is the plot of the function. So you see the mouse opening up and having a local minimum. What is the local minimum in such case? It is 0 at x equals 0. This is the local minimum. Inflection points. An inflection point occurs when concavity changes. Okay? Usually when f second x is equal to 0 or it is undefined. Example, f of x is equal to x3. So f prime of x equals 3x2, f second of x equals 6x. f second of x is equal to 0 for x equal to 0. That would be the inflection point. Now, x beneath 0, f second of x would become negative. So concaved down for, this is for x negative, for x positive greater than 0, f second of x becomes greater than 0, so it becomes concaved up. So you have an inflection, meaning that the concavity is changing from down to up like this, and that would be an inflection point at x equals 0 in our case. So 0, 0 is an inflection point. So f second of x is equal to 6x. That would become 0 for x equals 0. And this is the inflection point separating from two concavities. Because for x negative, f second of x negative, and it is concaved down like this. Then you have x equals 0. That's the inflection point. After that, for x greater than 0, f second of x becomes greater than 0, and its mouse opens up, so it becomes concaved upward. And x equals 0 is the inflection point. Curve sketching. To sketch a graph, we need to determine the domain, find intercepts, critical points, determine intervals of increase, decrease, concavity, inflection points, identify asymptotes. Let's determine whether f of x is equal to x squared has a maximum or a minimum. Okay, first derivative would give us 2x, second derivative equal to greater than 0, so it is concaved up and has a local minimum. So the minimum is at 0, 0, okay, which is when you plot f of x is equal to x squared, it has a minimum at 0. Function analysis and graphing. Now in this section, we're going to apply key methodologies and concepts learned in other sections and leverage or exploit them to study and draw the graph of diverse functions. Let's start with f of x equal x squared. First, the domain of definition. F exists for x within R, meaning that for x within the real numbers scope, or in other words, for x existing between minus infinity all the way to plus infinity. Limits. Limit f of x as x approaches both plus and minus infinity is always equal to plus infinity, given the fact that f of x is equal to x squared. So it is a squared number. Hence, for both negative and positive values, it becomes positive, or it remains positive. So it approaches plus infinity for both negative and positive large values of x. Third, derivative, okay, to check or to find where the function climbs, increases, and where it decreases. So, as a reminder, the derivative is the slope of the tangent against the curve. So, if it is positive, it means that the function is climbing. Okay, so this is a positive slope, meaning that the angle formed by this tangent and the x-axis is greater than 0, which means tan theta is greater than 0 or positive. Now, if you have a negative value for f prime of x for the derivative, it means that the angle formed by or between the x-axis, the horizon, and the tangent against the curve, this would be the tangent, is negative, which means that the curve is descending instead of ascending. So to clarify it, the curve would be like that. Theta is a negative angle, and also, of course, tan theta would be negative. This is the curve here, so it is the one in the thick line, and you notice how this curve is descending. It is going downwards in such case. So the derivative of the function f prime of x is equal to x. Let's check for which values of x the derivative is negative, which means that the slope would be negative and the function would be descending. For which values it would be positive with an ascending slope and the curve would be going upwards or climbing. And for which values of x also, okay, you would get f prime of x equals 0, which means that the slope of the tangent at such point would be 0, or the tangent against the curve would be parallel to the x-axis. So the curve at that point would be neither descending nor ascending. So for x less than 0, f prime of x is negative, and the slope would be negative. The curve would be going downwards. For x greater than 0, f prime of x would be greater than 0. So the slope would be positive angle with the x-axis, and the curve would be ascending. What is the critical point, or the point at which the slope of the function or the tangent against the curve of the function would be 0? So the tangent would be parallel to the x-axis and the function would be neither ascending nor descending. So we solve 2x equals 0, which means f prime of x equals 0. Hence, x equals 0. So it is at point 0, 0 where the tangent against the curve would be parallel to the x-axis. So for x equals 0 and y equals 0, this is the point where the function would be or would have a tangent parallel to the x-axis. And the function would look like this, but we haven't gotten to that place yet. So let me remove it. Now let's check the concavity of the function, meaning where the function would be going upward or downward, okay? Or would be concaved up with the mouse opening upward or the mouse opening downwards. So that would be the second derivative of f, which is equal derivative of 2x equal plus 2, greater than 0, hence it is concaved up. So its mouse would open up with a local minimum, and by the way, the local minimum would be 0. Now let's check the variation of the function. So x, it is defined between minus infinity to plus infinity. We have critical point 0, then f prime of x, which would indicate the variation, whether climbing or descending, and f of x, that would be the limit. Okay, so now f prime of x is equal to x for x negative, meaning between minus infinity to 0, f prime of x is negative. Between 0 and plus infinity, it is positive. So negative meaning that as x approaches minus infinity, this would mean that, of course, we know that the limit would be plus infinity. So plus infinity would descend all the way to 0. Now we know that f of 0 is equal to 0, correct? Then it would increase from 0 to plus infinity, which is the limit, by the way, of the function as x approaches plus infinity. So to plot the graph, okay, so from minus infinity, okay, the function begins descending from plus infinity all the way to x equals 0. Then between 0 and plus infinity, okay, based on the derivative, the slope is positive, which means that the function starts climbing all the way to plus infinity. This is what it means to have a positive slope, meaning that the tangent against the curve at this point, trying to be as accurate as I can, so that would be the slope. Notice that it has a positive angle. So the curve in such case is ascending. Meanwhile, for x less than 0, the tangent is this one, okay? And this is the angle with the x-axis, okay? So, or with the horizon, it is a negative angle, so tan theta is also negative, hence the function or the curve is descending. Then it reaches a trough, which is at x equals 0, y equals 0. Another note to be taken is that since the second derivative is positive, which is equal to, so it is concaved up, and truly indeed it is concaved up, meaning that the function has its mouths opening upward, and it has a local minimum. What is the local minimum, which is the overall minimum here? It is 0, okay? 0, 0 is the local minimum. Another function, f of x, is equal to 1 divided by x minus 1. Okay, first of all, for the domain of definition, x should be different than 1. Okay, you solve the denominator, you find out that x minus 1 equals 0, x equal 1. So for x equal 1, the denominator becomes 0, and the function would blow up to infinity because you would be dividing by 0. Hence, first of all, the domain of definition is x exists in R minus the singleton 1, or another way to write it is x exists between minus infinity to plus 1, excluded, of course, the boundaries, union 1 to plus infinity. Now the limits. So limit f of x as x approaches 1 is equal to limit x approaching 1 of 1 over 0, which is plus minus infinity, okay? Which means that x equal to 1 is a vertical asymptote. Let's examine thoroughly this limit. So limit f of x as x approaches 1 minus, meaning for x approaching 1 from the left, it would be a number slightly less than 1. Okay, so that would be equal to limit of 1 divided by, for example, 0.998 minus 1, which would give us a negative value equal to 1 divided by 0 minus equal minus infinity. As for limit of f of x as x approaches 1 plus, this would be equal to limit 1 divided by 1 plus, meaning 1.01, for example, minus 1. So it would be a positive value equal to plus infinity. So far, we have x equal 1 as a vertical asymptote. Okay, let's find the limit of f of x as x approaches infinity. So limit f of x as x approaches infinity is equal to 1 divided by infinity. Minus 1 becomes insignificant, which is equal to 0. Now, for x approaching minus infinity, by the way, it would be 0 minus, which means that the graph would be below y equal 0. And by the way, in such case, y equals 0 is a horizontal asymptote, horizontal barrier. Limit f of x as x approaches plus infinity equal 1 divided by plus infinity equal 0 plus. So the curve would be slightly above y equals 0, which again is the horizontal asymptote. Now let's find the derivative of the function. So f prime of x is equal to u prime v minus u v prime divided by v squared, given that it is a ratio, right? With u equal 1 and v equal x minus 1. So u prime v is 0 minus u v prime minus 1 times x minus 1 prime is 1 divided by v squared x minus 1 squared. Actually, a shortened formula for that would be minus u divided by v squared. Okay? So equal to minus 1 divided by x minus 1 squared. We notice that within the derivative, the denominator is squared, meaning that it's always positive. With negative 1 in the numerator, hence the function or the derivative is always negative. So the slope is negative. It is a function always descending. Apparently no critical points, so no value of x for which the function would be, so to speak, or the derivative would have a 0. More than that, okay, so what can we find? Let's check at which values of x the function clips the y-axis or the x-axis. Now, the function never intercepts x equal or y equals 0. Why is that? Because y equals 0 is a horizontal asymptote, okay? So it never reaches y equals 0. As for, okay, so for x equals 0, meaning this would be, so to speak, the y-intercept, okay? At which point does the function clips the y-axis? So for x equals 0, f of 0 equal to 1 divided by 0 minus 1, which is minus 1. So we have a point that is x equals 0, okay, for x equals 0, y equal minus 1. This is a point belonging to the curve. Y equals 0 is a horizontal asymptote. We draw it like this. And x equal 1 is a vertical asymptote. Now, for x approaching minus infinity, the limit of f of x is 0 minus, meaning that the function is below the horizontal asymptote. For x approaching plus infinity, limit of f of x is 0 plus, which is slightly above the function. Let's now recall the behavior of the function near x equal 1, which is the vertical asymptote. So limit as x approaches 1 from the left, 1 minus, is equal to 1 divided by 0 minus or minus infinity. So from left, the function approaches minus infinity. So it would be somewhere here. From the right, limit as x approaches 1 plus of 1 over x minus 1, it would be equal to 1 divided by 1.01, for example, minus 1. So 1 over 0 plus equal plus infinity. It would be equal to plus infinity, which is this one. And we know that the function intercepts the y-axis at x equals 0 and at a height of minus 1. So this is the function, something like that. And to the right, it is something like that. Now, it is advised to get some critical points, some values for the function to accurately draw it from the right and from the left. So you can get f of 2, for example, f of 7. So f of 2 is equal to 1 divided by, f of 2 equal 1. This is a point. F of 3 equal to 1 half. So it would be over here, you see? So this would plot for you a more accurate representation of the function. At least to the right, this is what we get. You see the function is so close to both the vertical and the horizontal asymptote. So it would be something like that. Let's study and graph the function f of x is equal to square root of x minus 1. Okay. First of all, the domain of definition, we know that x minus 1 should be greater than or equal to 0. Hence, x is greater than equal to plus 1, right? So in other words, x should belong to the following interval from 1 all the way to plus infinity. So any value that is less than 1, okay, on x would have no values in f. So the function is only defined from 1 being included in a closed set to the left, all the way to plus infinity. Limit of f of x as x approaches infinity is equal to square root of infinity equal to plus infinity. Okay? Of course, for minus infinity, there can be no values because the function is not defined to the left of plus 1. And of course, f of 1 is equal to square root of 0. So that would be considered as an interesting point or a point of interest. 1, 0. The derivative f prime of x is equal to, okay, so we consider that u is equal to x minus 1. The derivative of square root of u is equal to u prime divided by 2 square root of u. So it is equal to 1 divided by 2 times square root of x minus 1. Now the root is always positive, right? And numerator and denominator are always also positives. Hence, like the slope is always going up. The slope of the function is positive, whatever x would be, within the domain that is actually where the function is defined. Hence, the function is always going upwards. By the way, notice something that for x equals 0, f prime of x doesn't make any sense. Why? Because it becomes 1 over 0 equal plus infinity, which is impossible, okay? And in fact, x equals 0 does not even belong to the domain of definition. So this would be a wrong presumption, okay, to begin with. So we start with 1, 0 being a point of interest. Then you get some point, okay, for x equal to, it is 1, okay, square root of x minus 1 is 1. For x equal 4, for example, it is square root of 3. So it grows like this. F of x is equal to 3 divided by x squared minus 9. First, the domain of definition. So we know that the function cannot exist for a denominator that is equal to 0. So for what values of x does the denominator become 0 and the function becomes divided by 0, which means it blows up to infinity? X squared minus 9 is equal to 0. Let's solve it. So x squared equal to 9. Hence, x is equal to plus minus square root of 9. So it is for x equal minus 3 and x equal to plus 3 that the function cannot exist. So f exists for x on R minus minus 3 and plus 3, these are the two forbidden values, or x, for x belonging to minus infinity to minus 3, minus 3 of course excluded, union minus 3 to plus 3, minus 3 and plus 3 also again excluded, but minus 2 acceptable, minus 1, 0, 1, 2 acceptable, union 3 to plus infinity. Of course, plus infinity is not a number, also excluded. Now let's find the limit. So limit f of x as x approaches minus or plus 3, the same thing, since it is actually a squared value in the denominator, is equal to 3 divided by 9 minus 9, or 3 over 0, which is plus infinity. Hence, x equal minus 3 and x equal plus 3 are both vertical asymptotes. As a reminder, a vertical asymptote is a line at which the function approaches, but it can never get through. So it only approaches as a barrier, but can never have a value on that asymptote, on that line. Now, limit f of x as x approaches plus minus infinity is equal to 3 divided by infinity equal to 0. Hence, y equals 0 is a horizontal asymptote. Now let's find the derivative of the function. So f prime of x is equal to u prime v 0 minus u v prime minus 3 times 2x divided by v squared, which is x squared minus 9 squared. So it is equal to minus 6x divided by x squared minus 9 squared. Since the denominator is squared, so it is always positive, but the numerator would depend on x, okay? So if x is negative, f prime of x would be equal to plus 6x divided by v squared. So it would be positive, hence a positive slope and an ascent in the function. The curve would be climbing. But for x greater than 0, f prime of x would be equal minus 6x divided by v squared less than 0. So the slope would be negative and the function would be descending for x greater than 0. So it is inverse to the variation of x. Let's find also some significant points. So for x equals 0, f of 0 is equal to 3 divided by minus 9, or minus 1 over 3. 0 minus 1 over 3 is a significant point. So this is the point at which the function clips the y-axis, okay? So 0 minus 1 over 3, that would be a point like that. Now, we can draw the function. First, we have a horizontal asymptote, which is y equals 0. Then two vertical asymptotes, which are x equal plus 3 and x equal minus 3. For x is negative, x less than 0, f prime of x is greater than 0, so the slope is positive. So the function would be going upward between the two asymptotes, both to the left and to the right for every x equal to 0. Now it cuts the x-axis at minus 1, 3, right? Now, to the right, the function would be, okay, so for x greater than 0, the function has a negative slope, so it would be descending on both sides, like this. Now, allow me here to bring some clarification over why is the function, as it approaches, for example, minus 3 from the left, it goes up to plus infinity. but from the right it goes to minus infinity. And it is the opposite for plus 3. So for plus 3, as it approaches from the left, it goes to minus infinity. From the right, it goes to plus infinity. So for x equals 3, this asymptote, limit f of x as x approaches 3 minus, meaning 3 from the left, is equal to 3 divided by a number slightly less than 3, let's say 2.98 squared minus 9. So that would be a number or a value less than 9 equals 3 divided by 0 minus, which goes to minus infinity given that it is a negative number. So this is 3 minus, and the function goes to negative infinity. Now, for the limit, let me erase. For the limit of the function as x approaches plus 3 or 3 plus, in other words, 3 from the right. So limit f of x as x approaches 3 plus is equal to 3 divided by a number slightly bigger than 3, 3.1, let's say, squared, minus 9. So it would give you a positive infinity. That's why to the right of 3, the function approaches plus infinity. Concerning minus 3, okay? So limit f of x, x approaching minus 3 minus, is equal to, okay, what does it mean minus 3 minus? So a number slightly less than minus 3, which would be bigger in absolute value. So it is limit of 3 divided by minus 3.2, for example, squared, okay, minus 9. So it would give you 3 divided by 0 plus, equal plus infinity. That's why it approaches plus infinity to the left here. As for limit f of x as x approaches, minus 3 plus, so it is equal to limit 3 divided, minus 3 plus would be a number less than 3 in absolute value, okay? Minus 3 plus would be minus 2.9 squared minus 9, so a value that would be 3 divided by 0 minus, okay? Negative infinity. That's why to the right, the function approaches negative infinity. F of x equal ln x minus 2. First, we know that ln 0 is equal to minus infinity, and the domain of definition for ln u, okay, for example, is for u greater than 0 strictly, okay? So for u is positive. Now, for ln x minus 2, so x minus 2 should be strictly positive, meaning that x is greater than 2. So the domain of definition is f exists for x is between minus infinity. Actually, this is incorrect. Why? Because minus infinity is negative. So x, it is for x belonging to the interval starting from 2, strictly from 2 with 2 included, all the way to plus infinity. Limits, okay, limit of ln x minus 2 as x approaches 2 is equal to minus infinity. So x equal to is a vertical asymptote. So now limit ln x minus 2 as x approaches plus infinity is equal to plus infinity. So x equal to is the vertical asymptote, and as x approaches 2 from the right here, because from the left the function doesn't even exist, ln approaches minus infinity. Now we know that ln1 is equal to 0, hence x minus 2 is equal to 1. For x equal to minus 1, the function becomes, or yeah, for x equal minus 2 plus 1, which is plus 3. I'm sorry. The function becomes 0. So it clips the x-axis at x equals 3. Then it goes to plus infinity. Another thing to be noted is that the derivative of ln x minus 2 is equal to u prime over u, where u is equal to x minus 2. So it is equal to 1 divided by x minus 2. So, okay, given that x is always positive and like strictly greater than 2, okay, actually for x equal to 2 exactly, it goes to minus infinity as we mentioned before. But for x greater than 2, the function is always positive, the derivative is always positive, the slope is positive, so which means that the curve itself is growing, okay, given that the tangent to the curve would have an angle theta, for example, greater than 0, formed with the x-axis. So the function is growing all the way to plus infinity. Another function, f of x is equal to x divided by x squared minus 1. First of all, the domain of definition is for, okay, the forbidden values are the ones of x that render the denominator 0, right? So x squared minus 1 should be different than 0. Let's solve it. X squared is equal to 1. So x equal to plus minus 1. For x equal to minus 1 or x equal to plus 1, the denominator becomes 0 and the function blows up to infinity. F exists for x existing in R minus 1 and plus 1, or another way to write it is for whatever x is on the following intervals from minus 1, from minus infinity all the way to minus 1 excluded, union between minus 1 and plus 1, the boundary is excluded, but 0 acceptable, 0.3 or minus 0.3 acceptable, union 1 to plus infinity, again also the boundaries are excluded. Now let's find the limit f of x as x approaches minus 1. Now here, okay, so you have minus 1 minus, meaning that a value slightly lesser than minus 1. It is equal to minus 1 in the numerator divided by, that would be, okay, minus 1 minus means something like minus 1.1, for example, okay? Square, so it would give you a positive value, minus 1. So the denominator would be positive, but the numerator negative. So equal minus 1 over 0 plus equal minus infinity. As for limit f of x as x approaches minus 0 plus is equal to minus 1 plus, okay, minus 1 divided by a value, okay, so minus 1 plus a value slightly lesser than, slightly bigger than minus 1. So it would be, since it is negative, okay, minus 0.9 squared, for example, minus 1. So both the numerator and the denominator would be negative. In such case, okay, minus 1 over 0 minus, so it would produce plus infinity. Now, limit as x approaches 1 minus of f of x, that would be, okay, 1 minus is a slightly lesser value of 1. So 1 divided by 0.9 squared minus 1. So it is 1 divided by 0 minus or minus infinity. And limit as x approaches 1 plus f of x equal 1 divided by 1.2, for example, squared minus 1. So 1 divided by 0 plus equal plus infinity. Now, we know that x is equal to minus 1 and x equal plus 1 are both vertical asymptotes. Now let's check limit f of x as x approaches minus infinity. So that would be limit. Okay, we consider only the high powers of x, okay? And minus 1 becomes irrelevant in the denominator, so it is limit of 1 of x divided by x squared, or 1 over x, okay? As x approaches minus infinity. So 1 over minus infinity, so it is 0 minus, meaning that the curve would be slightly below y equals 0. And of course, y equals 0 in such case would be a horizontal asymptote. As for the limit f of x as x approaches plus infinity is equal to 1 over x, 1 over plus infinity, so 0 plus, and the function would be slightly above the horizontal asymptote, which is y equals 0. Alright, so now I made it a little bit neater by clearing the area of the graph. So as a reminder, for x approaching minus 1 from the left, which is minus 1 minus, the function would go to minus infinity. For minus 1 plus, meaning from the right of minus 1, the function would go to plus infinity. Then 1 minus, which is the left of x equal 1, the function would approach minus infinity. 1 plus to the right, it would go to plus infinity. And also you have for x approaching minus infinity, the curve would be above y equals 0. For x going to plus infinity, it would be it would be below. For x approaches minus infinity. For x approaching plus infinity, it would be above. Let's at first draw the asymptote. So this is x is equal to minus 1 and x equal plus 1. This is y equals 0, the asymptote, horizontal asymptote. So for x approaching minus infinity, it is 0 minus below the curve. X approaching plus infinity, it is 0 plus, so above the curve. As for, minus 1 minus, or the left of minus 1, this is x equal minus 1, and x equal plus 1. So to the left of minus 1, you have minus infinity. To the right of minus 1, you have plus infinity. Then to the left of 1, which is 1 minus, you have minus infinity. And to the right of 1, this is x equal 1, to the right of it, the function is at plus infinity. Okay, great, let's check it out. Now, we need to evaluate also the derivative. So f prime of x is equal to, u here is equal to x, and v equal x squared minus 1. So it is u prime v, 1 times x squared minus 1, minus uv prime minus x times 2x, divided by v squared, which is x squared minus 1 squared, equal x squared minus 1 minus 2x squared divided by x squared minus 1, equal to minus x squared minus 1 divided by x squared minus 1, the denominator squared. So the denominator is always positive, given that it is a square. Now, in the numerator, notice something. X squared is always positive, but you have a negative sign behind it, so it is always negative. F prime of x is always negative. It has a negative slope, so the function is always descending. Let's see how it is descending. Let's check also for which x value does the function clip the y-axis. So in other words, what is f of 0? Okay, if we replace x by 0, you get 0 in f, not in the derivative. You get 0 divided by 0 minus 1, which is equal to 0. Hence, 0 here which is 0, 0, is an important point of intersection with the y-axis, okay, by the curve. So let's establish the table of variations. Okay, so x, we have minus infinity. Here we trace the, we place the asymptotes, okay? Minus infinity, minus 1, then plus 1, plus infinity, and you have a point 0 where the function is 0. Here the asymptotes, you draw them like this as boundaries. Okay, so f prime of x is always negative, as we mentioned before. Always negative. Now, here f of x. Okay, so f of x for x approaching minus infinity is equal to 0 minus, and it descends into minus infinity, right? If you look back at the limits, this is true. Then between minus 1 and plus 1, and we have studied how the function varies between minus 1 and plus 1, right? Meaning that to the right of minus 1 and left of plus 1. Right of minus 1, it is plus infinity, and it descends to minus infinity to the left of plus 1. Then from 1 to plus infinity, so this is, okay, the first plot. Here, it descends from plus infinity to minus infinity while intersecting with the y-axis at x equals 0, remember? Then from 1 to plus infinity, the function descends from plus infinity to 0 plus, which is the point or like the area right above the horizontal asymptote. And this is the plot of the function. The linear approximation near x equal a is L of x is equal to f of a plus f prime of a times x minus a. Approximate square root of 4.1 using linearization of f of x equals square root of x at x equal 4. For x equal 4.1, okay, so f of 4 is equal to, starting with that. Okay, because the approximation is given by f of a plus f prime of a times x minus a. We are approximating the value of f at a. So f of 4 equal to f prime of x is equal to square root of x prime. Okay, now square root of x is simply x to the power of 1/2. So its derivative is 1/2 times x to the power of 1/2 minus 1. So it is 1 divided by 2 square root of x. Why? Because x to the power of minus 1/2 is 1 over x 1/2, which is 1 over square root of x. You replace x by 4, you get 1 over 4. So L of x is equal to plus 1 over 4 times x minus a, which is x minus 4. Okay, for x equal 4.1, so this becomes approximately 2.025. This is the value, approximation of the value of the function at x equal 4.1. Newton's method approximates roots of equations based on the following formula. xn plus 1 equal xn minus f of xn divided by the derivative of f at xn. Use one iteration of Newton's method to approximate a root of f of x is equal to x squared minus 2, starting from x0 equal 1. So x1 is equal to x0 minus fx0 divided by f prime x0. So fx0 is f of 1 is equal to 1 minus 2, which is minus 1. F prime of 1 is 2x, where x equal 1, it is equal to, so x1 is equal to x0, which is 1, minus fx0, which is minus 1 divided by 2, equal 1.5. Some review exercises. Find the critical points of f of x is equal to x squared minus 4x. F prime of x is equal to x minus 4. Critical points, as we remember, if you recall, is for the first derivative, not the second, okay? So it is the points at which the first derivative is equal to 0, or in other words, the tangent at the curve would be parallel to the x-axis, to the horizon. So f prime of x is equal to x minus 4, x equal 2. Let's determine the concavity of f of x equal x4. F prime of x is equal to 4x3, f second of x is equal to 12x squared. Always positive or greater than 0, so concave up everywhere. Find the velocity when s of t is equal to t squared plus 3t and t equal 2. So v of t is derivative of s of the position in respect of time equal 2t plus 3. V of 2, so what is the velocity at t equal 2? It is equal to 4 plus 3, which is 7. So finally, we studied here tangent and normal lines, instantaneous rates of change, velocity and acceleration, related rates, increasing and decreasing functions, critical points, first derivative, second derivative test, optimization problems, concavity, inflection points, curve sketching, linear approximation, and Newton's method. The applications of derivatives transform differential calculus from a computational subject into a powerful analytical tool. By studying derivatives, we can model motion, optimize systems, understand geometric behavior, approximate functions, and solve real-world problems across mathematics, science, engineering, economics, and technology. At the end, thank you so much for watching. See you next time. Bye-bye.